All right. Just give me a second. Let me see if every single thing is working properly. Yeah, this is fine. This is also fine. All right, people. So let's get going then. Let's get started. I'll be starting with the basic terminology, right? What is that? That's chemical bond. So my dear students, how do we exactly define the term chemical bond? What this chemical bond exactly is all about? Let's get to know about this chemical bond in detail. Okay. Let me first of all write its definition. My dear students, any force of attraction, that holds the constituent particles. That holds the constituent particles. Guys, just a second. Let me just turn the generator on. I think there was a power cut. Just a second. All right, Buell. Yeah. No, we are not going to study in the dark mode. Nope. Yeah. No, we are not going to do that. Just a second. All right, so I was writing the definition of chemical bond. Any force of attraction that holds the constituent particles, which can be atoms, ions, etc. Any force of attraction that holds the constituent particles, which can be atoms and etc. together in a chemical species. Together in a chemical species is what we call as a chemical bond. So my dear students, what chemical bond exactly is all about? Any force of attraction that holds the constituent particles, which can be either atoms, which can be either ions, right? Any force of attraction which holds the constituent particles together in a species, we call that force of attraction as the chemical bond. So this is the basic definition of the term chemical bond. Any force of attraction that holds the constituent particles, which can be either atoms or ions together in a chemical species, we call that as the chemical bond. Now the point is, why a chemical bond is formed? Before talking about that, my dear students, if you talk about H2 molecule, in case of your H2 molecule, I would say there is some force of attraction which is holding these atoms together over here. For example, if I talk about NaCl, wherein we have got Na positive and Cl negative, I would say there is some force of attraction which is holding these constituent particles together, right? Perfect. For example, if I take HF molecule, right? I would say there is some force of attraction which is holding these atoms together in this molecule. And any force of attraction that holds the constituent particles together in a chemical species, what do we call that as? We call that as the chemical bond. Now the point is, why this chemical bond exactly is formed? What is the reason for the chemical bond to be formed? Okay. Particularly, my dear students, there are two reasons why a chemical bond is formed. There are two reasons why a chemical bond is formed. Why atoms combine to form a molecule. There will be two reasons which you need to know. The first reason, I would say atoms, or let me write in general. Let me write in general constituent particles, which can be either atoms or ions, right? I would say constituent particles combine. Constituent particles, they combine. Why do they combine? To attain stable outermost configuration. To attain stable outermost electronic configuration. What does that mean? I would say constituent particles, they combine to form what? They combine to form the bonds. Why is that? I would say to complete their octets or duplets. To complete their octets or duplets. I'm just talking about the basic stuff right now. For example, if I talk about H2 molecule. In case of H2 molecule, my dear students, why two hydrogen atoms combine? Why two hydrogen atoms combine? Because if you talk about this hydrogen atom, it contains one electron. If you talk about this particular hydrogen atom, it contains one electron. Either the atoms need to complete their duplets or the atoms need to complete their octets, right? So what would happen over here? I would say both these hydrogen atoms, they would give one electron, which will be mutually shared by two atoms. So I would say this hydrogen as well as this hydrogen, both the hydrogen atoms have completed their duplets over here. Similarly, for example, you have got HF molecule. Hydrogen has got one electron, okay? And fluorine in its outermost shell, there are how many electrons in total? There are 7 electrons in total. Fluorine has got 7 electrons in its outermost shell. If I talk about hydrogen, it has got 1 electron. Hydrogen would want to complete its duplet. Fluorine would want to complete its octet, right? So hydrogen wants to have 2 electrons in its outermost shell. Fluorine wants 8 electrons in its outermost shell. So what they are going to do over here, they are going to, hydrogen is going to give one electron, fluorine is going to give 1 electron, and this electron pair, it will be mutually shared by 2 atoms. So I would say this hydrogen has completed its duplet, and similarly this fluorine, it has completed its octet. So why bonding here takes place? Why bonding here takes place? Just to complete their octets or duplets, right? Just to complete their octets or duplets. This is the first reason why bonding between the atoms takes place. But my dear students, I would say this particular logic, why atoms combine? Just to complete their octets or duplets. I would say this particular logic is not 100% correct. Why is that? My dear students, there are some compounds which you call as, for example, hypervalent compounds, which you call as hypervalent compounds, or there is one more set of compounds which you call as hypovalent compounds, which is what you call as hypovalent compounds. Hypovalent compounds. In case of the hypervalent compounds, I would say the total electrons in the valence shell would be greater than 8. In case of hypovalent compounds, the total electrons in the valence shell would be less than 8. For example, I'm pretty much sure you would have heard about this particular compound, PCl5. I'm pretty much sure you would have heard about this particular compound, SF6, right? I'm pretty much sure you would have heard about this particular compound, IF7. Perfect, IF7. My dear students, if you talk about the rough structure of PCl5, phosphorus over here is making 5 bonds basically. So I would say in the outermost shell of phosphorus, there will be 10 electrons. In the outermost shell of sulfur, there would be 12 electrons. In the outermost shell of iodine, there will be 14 electrons, right? Perfect. And octet rule says that there should be 8 electrons in the outermost shell. But here, in case of PCl5, in the outermost shell of phosphorus, there are 10 electrons. Here, there are 12 electrons, 14 electrons. And these compounds, they exist. They exist, right? They exist. Similarly, if you talk about hypovalent compounds, for example, you have got BeCl2. Beryllium is forming 2 bonds. If beryllium is forming 2 bonds, I would say in its outermost shell, there will be only 4 electrons, right? Let's say you have got BF3. In the outermost shell of boron, there will be only 6 electrons because it's forming 3 bonds, 2, 2, 2, 6 electrons, right? Perfect. For example, you talk about AlCl3. Perfect. It's forming 3 bonds, so there will be in total 6 electrons in its outermost shell. Perfect. So over here, I would say this octet rule is not followed. Even here, the octet rule is not followed, right? Perfect. So what do we say? Why do atoms combine? I told you atoms combine to form, atoms combine to get the stable outermost configuration, to get the noble gas configuration. Atoms combine to complete their duplets, to complete their octets, which is not valid everywhere. Over here, the octet rule is not followed. Over here, the octet rule is not followed. Still, these compounds exist. So what is the actual reason? What is the actual reason why atoms combine to form the bonds? Let's get to know about that actual reason. The actual reason, my dear students, why atoms form, why atoms combine and forms the bonds. Why is that? The reason is the tendency to attain minimum energy, the tendency to attain minimum energy and maximum stability. The tendency to attain minimum energy and maximum stability. This is the main reason. This is the main reason why atoms combine, why your constituent particles combine to form the bonds, right? This is the main reason. Now, my dear students, we are going to talk about this particular reason a bit more in detail because entire chemical bonding is based on this particular statement. And I believe this particular statement should be super clear to everyone. Okay? It should be super clear to everyone. By the way, over here, in case of your hypervalent compounds, hypovalent compounds, octet rule is not followed. Similarly, in case of your odd electron species, one more category of species you can write over here, your odd electron species. Perfect. Your odd electron species like NO, like ClO2. In these species also, octet rule is not followed. Still these species exist. Okay? Perfect. Now, the actual reason is not to complete the octet or duplet. Actual reason why atoms combine to attain minimum energy and maximum stability. Well, my dear students, in order to make you understand this particular thing, there are a few basic things which I would want to share with you. For example, imagine that I've got an atom. Let's say this is the atom A. Imagine this is one more atom which I'm calling as atom B. Perfect. Imagine this is the nucleus of A. Imagine this is the electron of A. This is nucleus of A and this is electron of A. For example, this is the nucleus of B and this is the electron of B. Let's assume these are the two atoms which we have. My dear students, first of all, let's get to know what all different forces may exist between the two atoms. Let's talk about what all different forces can exist between two atoms. The first force is the force of attraction between nucleus of A and electron of A. Okay? Nucleus of A, electron of A. Similarly, nucleus of B, electron of B. This is the first type of force of attraction in these atoms. Nucleus of A and, this is the nucleus of B and electron of B. This is something which you all must be knowing, correct? Now, between these two atoms, which all force will exist, right? Between these atoms, which all force will exist. Now, guys, understand. I would say the nucleus of A will be attracting this electron of B towards itself. Nucleus of A would be attracting electron of B towards itself. In the similar way, nucleus of B would be attracting electron of A towards itself. Nucleus of B would be attracting electron of A towards itself. Perfect? Right? Now, there is one more force of attraction. Sorry, there is one more force which is going to arise between these two atoms. What is that force? I would say between nucleus of A and nucleus of B. Between nucleus of A and nucleus of B, there will be force of repulsion. Nucleus of A, nucleus of B, right? Nucleus of A, nucleus of B, there will be force of repulsion. Similarly, my dear students, between electron of A and electron of B, again there will be force of repulsion. Absolutely. Between electron of A and electron of B, again there will be force of repulsion. So between two atoms, there are two forces which are arising. Between two atoms, two forces exist. One is going to be the force of attraction and one is going to be the force of repulsion. Between two atoms, two forces exist. One is the force of attraction, one is the force of repulsion. My dear students, few things I would want you guys to remember over here. What are those? Let me tell you, force of attraction between the atoms. Force of attraction between the atoms. It decreases the energy of the system. Force of attraction between the atoms, it decreases the energy of the system. And as the energy of the system decreases, we can say stability increases. We can say stability increases. Similarly, force of repulsion between the atoms, it increases the energy of the system. And as the energy of the system increases, we can say stability decreases. Basically, from now onwards, you are going to remember one thing. Stability of the system is inversely proportional to the energy possessed by the system, particularly the potential energy. More the energy possessed by the system, lesser the stability. Lesser the energy possessed by the system, more the stability. I believe these two things are super clear to you. So between two atoms, I would say two types of forces arise. Force of attraction, force of repulsion. And you saw what is the force of attraction here, what is the force of repulsion here. Remember one thing, force of attractions, they tend to decrease the energy of the system, right? And increase the stability of the system. In the similar way, my dear students, force of repulsion, it tends to increase the energy of the system and hence decreases the stability of the system. Okay? Perfect, people. Now, let's get into the details of this stuff, which I'm telling you over here. See, guys, the first thing which I just want you guys to understand, what is that? That's super important. That is super important, guys. Imagine that this is an atom. This is one more atom. I'm assuming these atoms are right now at infinite distance apart. I'm assuming these atoms right now, they are at infinite distance apart. Now, my dear students, I believe you should be familiar with the fact force of attraction is inversely proportional to distance. Force of attraction is inversely proportional to distance. More the distance between the atoms, lesser the force of attraction. Lesser the distance between the atoms, more the force of attraction. This is something which I believe you would be knowing already. I am assuming right now these atoms, they are at infinite distance apart. And when atoms are at infinite distance apart, 1 by infinity becomes 0. So I would say the force of attraction between the atoms right now would be 0. Yeah? I would say force of attraction between the atoms right now would be 0 because the atoms are at infinite distance apart. Now, my dear students, as these atoms start approaching towards each other, what would happen? The distance between the atoms will keep on decreasing. The distance between the atoms will keep on decreasing. And if the distance between the atoms decreases, force of attraction increases. Force of attraction increases, right? And remember, whenever there are attractions, energy is released by the system. Whenever there are attractions, energy is released by the system. So when these atoms are approaching towards each other, distance between them decreases, force of attraction increases, energy is released, force of attraction increases. I would say there will be the scenario when these atoms will be at maximum closest distance. There will be a scenario when the atoms will be at maximum closest distance. At that point of time, force of attraction between the atoms would be maximum. And that is the point when we say that bond has got formed. That is the point when we say bond has got formed between the atoms over here. I hope you're understanding all this in detail. Initially, the atoms were at infinite distance apart. Force of attraction was 0. Now the atoms are coming closer. Distance decreasing. Force of attraction increasing. Energy is released by the system. This is the scenario when the atoms are at maximum closest distance. At this particular point of time, I would say force of attraction between the atoms will be maximum, right? Force of attraction between the atoms will be maximum. Or in other words, I would say energy of the system right now would be minimum. And when the energy of the system is minimum, I would say stability of the system would be maximum. Right? So when was the stability of the system maximum? When the atoms were at infinite distance? No. When the atoms are at maximum closest distance. At that point of time, force of attraction between the atoms is maximum. Right? Maximum energy is released by the system. So energy possessed by the system will be the least. If energy possessed by the system is least, stability is maximum. And that particular point, when we say energy of the system is least, we say stability of the system is maximum. And that is the point when we say that bond has got formed between the atoms. Am I clear to everyone? My dear students, remember it like this from now onwards. When atoms are coming closer, distance decreases, force of attraction increases, energy is released. If continuously energy is released, that means continuously energy carried by the system decreases, because continuously energy is being released. Energy carried by the system decreases continuously. Yeah? Perfect? Perfect, people? Now, two things I'm going to frame over here. Tell me one thing. My dear students, when the atoms are at maximum closest distance, force of attraction is maximum, right? Energy of the system is minimum. Stability is maximum. Now, people, if you want these atoms to come a little more closer, what is going to happen? Repulsive forces are going to start now. Right? And let me tell you, repulsive forces, they tend to increase the energy of the system. And decrease the stability of the system. Right? If you want these atoms to come a little more closer, after that repulsions are going to start. Right? And repulsive forces, they tend to increase the energy of the system, decrease the stability of the system. Okay? Now guys, tell me just one thing. When atoms were far apart from each other, which forces were dominating here? When the atoms were far apart, which forces were arising between the atoms? Attractive forces. When the atoms are too close, which forces are arising between the atoms now? I would say force of repulsions at that point of time. So can I say attractive forces? Are long range forces. And similarly, repulsive forces are short range forces. Let me know once in the chats if these two statements are clear to you. Attractive forces are long range forces. They act between the atoms at larger distances. Repulsive forces are short range forces. They act between the atoms at smaller distances. That's the reason Why? I told you, attractive forces, they are long-range forces. Repulsive forces are very short-range forces. Yeah? Right, people? Am I clear to everyone? Am I clear to everyone, people? Perfect. Now. Let's try to understand the same thing in a different way now. Okay? Let's try to understand the same thing in a different way so that it becomes properly clear to you. My dear students, over here I'm plotting a graph. Over here I'm plotting a graph. Over here I'm plotting a graph. Between what? Between potential energy of the system versus the distance between the atoms, or let me call it as versus distance of separation. Versus distance of separation. Potential energy of the system versus distance of separation. My dear students, in order to understand this particular graph, the statement which I told you, that's very important. When the atoms are at infinite distance apart, force of attraction 0. When the atoms come closer, distance decreases, force of attraction increases, right? Energy is released, energy is released, energy is released, force of attraction increasing, energy is released. There is a scenario at which force of attraction between the atoms is maximum, right? At this particular point of time, I would say energy of the system would be minimum, right? Stability would be maximum. I would say at this particular point of time, bond has got formed between these two atoms. Now, if I bring these atoms a little more closer, what is going to happen? Force of repulsion is going to start, which tends to increase the energy of the system, which tends to decrease the stability of the system. I believe it's super clear to everyone. If yes, let me know once in the chats quickly so that I can plot this graph. My dear students, if you talk about this particular point, this is the point at which the distance between the atoms is 0. This is the point at which distance between the atoms is 0. If you go in this direction, the distance between the atoms is increasing. Atoms are going far, atoms are going far, atoms are going far, right? Let's say we are starting somewhere here. Perfect. Let's say we are starting somewhere here. I'm assuming atoms are right now at infinite distance apart. Force of attraction between the atoms right now will be 0. Force of attraction between the atoms right now will be 0. Now, my dear students, tell me just one thing. If I go in this direction, what is happening? If I go in this direction, I would say distance of separation between the atoms, is it decreasing or increasing? Distance of separation is decreasing. That means if I'm going in this direction, atoms are coming closer. If atoms are coming closer, distance between them decreases, force of attraction increases. And if force of attraction increases, energy is continuously released by the system. If continuously energy is released by the system, energy possessed by the system will be decreasing as the atoms will be coming closer, right? So imagine at this particular point of time, atoms were at this particular distance apart, right? When you're going in this direction, that means distance of separation is decreasing. Now, for example, atoms have slightly come closer, right? Similarly, go in this direction, atoms are again coming closer a bit. And as the atoms are coming closer, what is going to happen? Force of attraction is going to increase. Energy is continuously released. And energy of the system will be decreasing with time. So I would say energy of the system would be continuously decreasing with time as the atoms would be coming closer. As the atoms would be coming closer, energy of the system would be decreasing with time. Imagine this is the minimum energy possessed by the system. Imagine this is the minimum energy possessed by the system. And I told you, when minimum energy is possessed by the system, when the atoms are at maximum closest distance. So at this particular point of time, I would say bond formation has taken place between the atoms. That is the reason at this particular point of time why energy of the system is minimum and why stability of the system will be maximum. Perfect. Now, my dear students, if you want these atoms to come a little more closer, which forces are going to start now? Repulsive forces. Repulsive forces are going to increase. They tend to increase the energy of the system. So energy of the system will start to increase now like this. Okay? Perfect, guys. Right? Let me tell you one thing. As the atoms were coming closer, energy was continuously released by the system, continuously released by the system. My dear students, My dear students, the gap from here to here, this is something which I'll be calling as the bond energy from now onwards. This particular gap I'll be calling as the bond energy of the system, right? This is the amount of energy released basically. Okay. Similarly, my dear students, let me tell you the distance from here to here, I'll be calling it now as the bond length, because bond formation has taken place over here. If bond formation has taken place, I would say the distance from this point to this point is something which I call as bond length at this particular point of time. Now, one more important thing. Look at this particular point. This point represents that the energy of the system is minimum now. If energy of the system is minimum, that means bond formation has taken place. Now, people, tell me one thing. If you draw a tangent over here, do you see your tangent is parallel to this r-axis? This is what I'm calling as r-axis. Your tangent is parallel to what? The tangent at this particular point of time, right? The tangent at this point is parallel to r-axis. So I would say slope of this tangent is 0. Slope of the tangent at this point of time is 0, right? How do you represent slope? Mathematically, du by dr, because this axis is your potential energy axis. This is the distance of separation axis, right? So I would say du upon dr at this particular point is 0. And from this statement, which I wrote over here, a question will be asked to you. From this statement, a question will be asked to you. Now, what is the question which will be asked here? What is the question which will be asked? Look at this particular question. Look at this particular question, guys. Understand properly. The variation of potential energy with R, between A and B is given as this much. Calculate the bond length in angstroms. So, my dear students, as per the question is concerned, your potential energy is given to me as 6 r raised power minus 2, plus 3r plus 2. What do I need to calculate? I need to calculate bond length. I need to calculate this distance. I would say whenever I need to calculate bond length, energy of the system at that point of time is minimum, right? Du by dr value is equal to 0. So I'll be just differentiating this u with respect to r. Du by dr is equal to 6. I'm writing as such. X raised power n, nx n minus 1. So n x n minus 1 plus differentiation of 3r will be just 3, and 2 differentiation is going to be 0. So my dear students, it comes out to be minus 12 r raised power minus 3 plus 3. Now we know this value has to be 0. Now people think over it properly. If this value has to be 0, then it means that minus 12 r raised power minus 3 has to be equal to minus 3. So minus cancel, right? So r raised power minus 3 is equal to 3 divided by 12, that means 1 by 4. So I can say 1 divided by r raised power 3 is equal to 1 by 4. I can say r raised power 3 is equal to 4. Perfect. Right, if I take the reciprocal, so r raised power 3 has to be equal to 4. And if r raised power 3 has to be equal to 4, I would say your r has to be equal to 4 raised power 1 by 3 angstroms. So this is going to give you what? This is your bond length which you were supposed to calculate. Perfect, people, perfect. Now let's try to classify these bonds. My dear students, bonds are classified into 2 categories here. Primary bonds, secondary bonds. So let me tell you, on the basis of bond energy, making bond energy as the criteria for classification. I'm going to divide these bonds into 2 categories. Primary bonds, right? Secondary bonds. My dear students, in case of primary bonds are going to be your strong bonds between the 2 constituent particles. Secondary bonds are going to be your weak bonds. Your strong bonds, they include ionic bonds, Covalent bonds, which we have to discuss in detail. Coordinate bonds, metallic bonds. They are your strong bonds. They are your primary bonds, right? Similarly, your van der Waals bonds and your hydrogen bonds, they are going to be your weak bonds, which we are going to discuss in detail, right? So based on the bond energy, we classify bonds into two categories, primary, secondary. Primary are the strong bonds, right? Secondary are the weak bonds. Perfect. Strong bonds include ionic, covalent, coordinate, metallic. Weak bonds include van der Waals force of attraction, hydrogen bonding, etc., etc. Yeah? Am I clear with this? Am I clear with this, people? Quick. Everyone, am I clear with this? Now, one-on-one, we are going to start the things. One-on-one, we are going to start the things. So, my dear students, let's get started with something called as ionic bond. So, what is an ionic bond? What is an ionic bond? My dear students, as you see the definition, the bond formed between the two atoms due to complete transfer of electrons is called as ionic bond. What is meant by this? What is meant by this? Just try to understand what I'm going to say. Okay, just try to understand. For example, people, imagine that I'm taking an ionic compound, NaCl. NaCl is the most typical example of the ionic compound. I've taken an ionic compound, NaCl. Perfect. Can I say in case of NaCl, you have got basically two elements. One is sodium, one is chlorine. Sodium and chlorine. You must be knowing sodium is metallic in nature and chlorine is non-metallic in nature. Right? And you must be knowing metals have got the tendency to lose electrons. So basically metals are electropositive in nature. Non-metals, they have got the tendency to gain electrons. Right? Metals have got the tendency to lose electrons and non-metals, they have got the tendency to gain electrons. Okay? Now, my dear students, if you talk about the sodium atom, sodium belongs to group 1. Sodium is an alkali metal. It belongs to group 1. In the outermost shell of sodium, there is only one electron. In the outermost shell of sodium, there is only one electron. Now, is it easy for sodium to gain 7 electrons? Or it is easy for sodium to lose 1 electron to get the stable configuration? It is easy for sodium to lose 1 electron, therefore getting converted into Na positive and giving away 1 electron completely, right? Now, if you talk about chlorine, in the outermost shell of chlorine, there are 7 electrons, right? So I would say the electron which is completely given by sodium, chlorine is going to gain this electron completely and get converted into Cl negative. So sodium gave rise to Na positive and chlorine gave rise to what? Cl negative. Do you see? You got the oppositely charged species over here. And I would say between the oppositely charged species, there will be electrostatic force of attraction. There would be electrostatic force of attraction over here between these oppositely charged particles. And this electrostatic force of attraction between these oppositely charged particles is something which you call as the ionic bond. Right? So, my dear students, what is an ionic bond? It is the force of attraction between the cation and anion over here. Right? Did you analyze one thing? Sodium lost 1 electron completely. Chlorine gained that 1 electron completely, due to which cation formation took place, anion formation took place, and there was electrostatic force of attraction between them. Perfect. And this electrostatic force of attraction between the cation and anion, I'm calling as the ionic bond. So can I say in short, ionic bond, which is also what we call as electrovalent bond, can I say ionic bond is formed by the complete loss and gain of electrons, or you can say complete transfer of electrons. Yeah? Right? So, that chemical bond which is formed by the complete transfer of electrons, by complete loss and gain of electrons, that is something which you call as ionic bond. Perfect? right? Now, my dear students, if I ask you, what are the conditions, what are the favorable conditions, I would say? What are the favorable conditions? What are the favorable conditions for ionic bond formation? What are the favorable conditions for the ionic bond formation? If I ask you, what are the favorable conditions for the ionic bond formation? My dear students, my first point will be, for the formation of ionic bond, one element should be metallic, another one should be non-metallic. This is the first condition. Simple. One element must be metallic and other one must be non-metallic. Other one must be non-metallic. This is the condition number one. Point number two, my dear students. Point number two. As I told you, one element should be metallic. What does it do? What does this metallic atom do? It loses the outermost electrons to form the cation. Can I say that metallic atom, which can lose its outermost electrons easily, can form the cation easily? Right? And once the cation is formed easily, I would say ionic bond can be formed easily. As simple as that. Right? So I would say the metallic atom, it should lose the outermost electrons easily so that it could get converted into cation easily. And once cation is generated easily, ionic bond can be formed easily. As simple as that. In other words, I can say metallic atom should have, or I'll write must have, low ionization energy. It must have low ionization energy, right? It must have low ionization energy. Perfect. Similarly, if I talk about the non-metal atom, what the non-metal atom does? Non-metal atom, it gains electron, then gets converted into anion, right? So I would say non-metal atom should gain electron quickly so that it could form the anion quickly. And once the anion formation is quick, ionic bond formation is quick, right? So I can say non-metal atom should have high electron affinity. The ones which have got high electron affinity, they accept electron quickly, they form the anion quickly, and once anion is formed quickly, ionic bond is formed quickly. That's all. I believe I'm clear to you, right? So these are basically some conditions, I would call them as the favorable conditions for the ionic bond to get formed. Am I clear with it? Am I clear with it, people? Am I clear with it? Let me know quickly in the chats. This is something which I already told you. One element should be metallic, right? And other one should be non-metallic. The metallic element should have low ionization energy. The non-metallic element should have high electron affinity. Simple and basic. Am I clear with this? Now, my dear students, let's talk about few characteristic things of these ionic compounds. What kind of nature these ionic compounds have? What all special features these ionic compounds have? First of all, these ionic compounds, these are generally hard. Why? Because in case of ionic compound, which force of attraction exists between the constituent particles? It is the strong electrostatic force of attraction which acts between the constituent particles. Since the electrostatic force of attraction is strong force, that's the reason why your ionic bonds are hard. Since there is the presence of strong electrostatic force of attraction, that is the reason why their melting and boiling points are high. That is the reason why their density is high. You're the strong electrostatic force of attraction. between the constituent particles, right? Look at this particular statement. These ionic compounds, in solid state, they behave like insulators, but in liquid and in molten and aqueous state, they behave like good conductors of electricity. What is the logic for that? What is the reason behind that? See guys, if I talk about NaCl solid, in NaCl solid, you'll find Na positive and Cl negative, right? We have got sodium chloride in solid state. Over here, you'll find a strong electrostatic force of attraction between them, which is holding them together. Since the electrostatic force of attraction here is very strong, so it is not going to let these ions to move. It is not going to let these ions to move. Perfect. Due to which, in solid state, it is going to behave like an insulator. Since the ions do not have any tendency to move over here, because the ions are held by strong electrostatic forces, I would say at this particular point of time, when your ionic compound is in solid state, it is going to behave like a proper insulator, because the ions cannot move here. They're held by strong electrostatic force. Now, my dear students, tell me one thing. Imagine you are heating this solid. Imagine that you are heating this solid and you're converting this solid into liquid. You're converting this solid into liquid. Now, this is something which I call as molten NaCl. This is something which I call as molten NaCl. Here also you have got Na positive and Cl negative. But my dear students, tell me one thing. Since you have converted solid into liquid, right? What do you think would have happened? Solid into liquid. In the solid, the constituent particles are very close. When you convert it into liquid, the constituent particles, they'll comparatively go far. They'll comparatively go far. Distance between them increases. Force of attraction decreases. Now the ions can slightly show some movement. And if the ions are showing the moment, I would say it is going to behave like the conductor here. So in the solid state, it was behaving like the insulator. In the liquid state, it is behaving like the conductor. Similarly, my dear students, in the aqueous state, it is again going to behave like the conductor. What is meant by aqueous state? See guys, for example, imagine you're introducing NaCl into water. Imagine you're introducing NaCl solid in water. What is going to happen? What is going to happen here? When NaCl goes into the water, this NaCl first of all breaks down into its ions, Na positive and Cl negative. It breaks down into its ions. As the ions are generated here, these ions are attracted by the water molecules. They are surrounded by the water molecules. Now, my dear students, since these ions are separated, now these ions are surrounded by what? Water molecules. Ions are separated. So I would say now they have got tendency to flow. Now they can show the moment. Since the force of attraction between the ions has been broken down, right? After breaking the force of attraction between the ions, now the ions are surrounded by water molecules, right? So I would say these ions can flow now. They can show moment, right? So I would say NaCl aqueous. Since the ions can show moment, so it's going to behave like the conductor here also. So remember, when you see ionic compound in solid state, right, there would be, it is going to behave like an insulator. In molten state, it's going to behave like a conductor. In aqueous state also, it's going to behave like the conductor. And am I clear, people, to everyone? Let me know once in the chats quickly. Everybody. Let me know once in the chats quickly. Everyone. Yeah? Perfect. Perfect, people, all clear? Let me know once in the chats with some fire emojis. Everybody. And these ionic compounds, they do not have any geometry. Like your for covalent compounds. Trigonal, planar, trigonal, bipyramidal, tetrahedral. Ionic compounds, they do not have such kind of geometry because their bonds are not directional. They are non-directional. Okay? These bonds are non-directional. They are not directional. Quickly in the charts. All clear? Amazing, guys. Now comes certain important things about these ionic compounds, guys. Some important things about ionic compounds. The first important thing, lattice energy. Lattice energy, which we represent with the delta H, lattice. Lattice energy. How do we define lattice energy of the ionic compound? What is lattice energy? My dear students, look at the definition. The amount of energy released when 1 mole of an ionic lattice is formed from its constituent gaseous ions. What does that mean? See, you're taking Na positive in gaseous state. You're taking Cl negative in gaseous state. Since these are oppositely charged species, so there will be attractions between them? Yes. Due to attractions, energy is released. Imagine I have taken 1 mole of Na positive, 1 mole of Cl negative, right? They will lead to the formation of 1 mole of NaCl solid at the end, right? During this process, would energy be absorbed or released? Right now, energy would be released because there are attraction between these ions. The amount of energy released when 1 mole of ionic lattice is formed from its constituent gaseous ions. That amount of energy released, I'll be calling as the lattice energy. Since energy is released right now in this particular process, so I would say delta H lattice would be negative. Whenever energy is released, that means process exothermic. For exothermic processes, delta H is negative, right? This is one way of defining the lattice energy. Another way of defining the lattice energy, which you frequently use. What is that? See, take 1 mole of ionic lattice. Now, this 1 mole of ionic lattice, just break it down into its constituent gaseous ions. Right? What does that mean? Over here, you had Na positive. Here, you had Cl negative. There was strong electrostatic force of attraction between them. Right? Let's do one thing. Let's break this force of attraction. And you know, bond breakage is endothermic. Energy is absorbed during bond breakage. My dear students, the amount of energy absorbed when 1 mole of an ionic lattice is broken down into its constituent ions. The amount of energy absorbed, the amount of energy required to break 1 mole of ionic lattice into its constituent gaseous ions. That is also something which I call as lattice energy. Since in this particular process right now, since you are breaking the force of attraction, so this process is endothermic in nature. So for this, I would say delta H lattice would be positive. In the first case, imagine your delta H lattice was minus X kilojoules per mole. In the second process, you can say your delta H lattice will be plus X kilojoules per mole. So basically, magnitude-wise, both are going to be same, right? It is just the sign is going to be different. That's all. Perfect. You can define lattice energy in this way or this way. The amount of energy released when 1 mole of ionic lattice is formed, or the amount of energy required to break 1 mole of ionic lattice into its gaseous ions. Magnitude-wise, it's going to be same. It is just sign is going to be different. Why? Because you have got 2 different ways of defining it. In the first case, you're saying energy is released when 1 mole of ionic lattice is formed. Here, energy is absorbed when same 1 mole of ionic lattice is broken down again into its constituent gaseous ion. So magnitude-wise, it's going to be same. It is just sign is going to be different. Yeah? Am I clear? People? Perfect. Now, guys, this particular statement is important. That ionic compound whose lattice energy will be more, that will be more stable. Don't you think? That ionic compound whose lattice energy would be more, that would be more stable. What does that mean? I would say that ionic compound whose lattice energy would be more. What does that mean? That means more energy is required to break it. More energy is required to break it. If more energy is required to break it, so more is the stability of this ionic compound basically. It does not want to break down. It does not want to break down. Perfect. The one which does not want to break down, that means it's thermally stable. It is thermally stable. Correct? So remember, my dear students, that ionic compound whose lattice energy will be more, its stability is going to be more as well. Now, there are few factors on which lattice energy depends upon. My dear students, when you talk about lattice energy, first of all, you know, electrostatic force of attraction. Electrostatic force of attraction between the ions is directly proportional to the charge present on the ions and inversely proportional to the distance between them. The electrostatic force of attraction between the ions is directly proportional to charge between them, inversely proportional to distance between them. Perfect. More the charge on the ions, more the force of attraction between the ions. More energy is required to break that attraction, hence more the lattice energy. Similarly, more the distance between the ions, lesser the force of attraction between the ions. Lesser energy is required to break that attraction. So lesser is the lattice energy. Right? Again, I'm repeating the same thing. The electrostatic force of attraction between the ions is directly proportional to charges on the ions, inversely proportional to distance between the ions. More the attraction between the ions, more the charge present on the ions, more is going to be force of attraction between the ions. More attraction between the ion means more energy is required to break that. If more energy is required to break that, that means more is going to be the lattice energy. So I can clearly say your lattice energy, it is directly proportional to what? Charge on the ions. Similarly, my dear students, more the size of the ions, more will be the distance between the ions. If more is the distance between the ions, less will be the force of attraction between the ions. If less is the force of attraction between the ions, I would say less energy is required to break that attraction. So less will be the lattice energy. In short, so lattice energy is inversely proportional to what? Size of the ions. Right? I believe this is clear as per this particular formula. Right? So tell me, in this particular question, give me the order of the lattice energy. Give me the order of the lattice energy. My dear students, just see one thing. Here you have got basically La positive, Cl negative, Na positive, Cl negative, K positive, Cl negative, Rb positive, Cl negative. So Cl negative everywhere is same. So you are not going to decide on the basis of Cl negative. Decide on the basis of cation here. Li positive, Na positive, K positive, Rb positive. Charge on every cation is same. But, no doubt, charge on every cation is same. But, is the size of every cation same? No. Size of every cation is not same. You have got Li positive. You have got Na positive. You have got K positive. You have got Rb positive. You have got Cs positive. As you move from top to the bottom, what happens to ionic size, guys? Quickly. What happens to ionic size? Ionic size increases, right? Ionic size increases. So among all these cations, which one will be having maximum size? Here you will find maximum size. More the size, lesser the lattice energy. Lesser the size, more the lattice energy. So this is the order here. This is the order here. Correct? This is the order here. Now people tell me the answer of this question. Mg di positive, O di negative. Na positive, Cl negative. Li positive, Cl negative. First of all, in the first case, the charges on the ions is more. More the charge on ions, more the lattice energy. So number 1 has got maximum lattice energy. Now among 2 and 3, anion is same. Talk in terms of cation now. Charge on cation is same. So do not decide on the basis of charge. Decide on the basis of size. Lesser the size, more the lattice energy. So 3 would be greater than 2. So this is the order of the second one. I believe I'm clear with this. I believe I'm clear to everyone. Quickly, let me know in the chats. Everyone in the chats, quick. Perfect. Amazing. Let's talk about one more thing when it comes to the ionic compounds. That is their hydration energy. Hydration energy, which I'm representing with delta H hydration. Hydration energy. Before talking about the hydration energy, what is meant by hydration? What is meant by hydration? What is meant by hydration? See guys, what hydration exactly means. Imagine you have got a container. Imagine you have got a container. In this container, for example, you have got water molecules. Imagine in this container, you have got water molecules like this. Right? You have got water molecules like this. Perfect? You have got water molecules like this. These are the water molecules in the container, right? My dear students, imagine that you are introducing what exactly? Imagine that you are introducing 1 mole of gaseous ion here in the container. For example, you are introducing 1 mole of Na positive gas here in the container, right? Or leave 1 mole, 2 mole, that's aside. For example, you are introducing 1 Na positive here in the gaseous state. You are introducing 1 Na positive here. Perfect. When you introduce Na positive here, or when you introduce Cl negative here in this container, what is going to happen? If you talk about water, look at its structure. Oxygen is more electronegative than hydrogen. If oxygen is more electronegative than hydrogen, this bond pair will be shifted towards oxygen, due to which oxygen carries delta negative, hydrogen carries delta positive. This particular bond will be also shifted towards oxygen, delta negative, delta positive. So, can I say this oxygen, can I call this oxygen as the negative end of water? Yes, this is the negative end of water. Can I call these hydrogen atoms as the positive ends of water? Yes, these are the positive ends of water. Perfect. Now you have introduced Na positive over here. Can I say towards Na positives, the negative ends of water are going to come? The negative ends of water are going to come. Negative end of water is oxygen. Perfect. Negative ends of water are going to come. And towards Cl negative, positive ends of water are going to come. Positive ends of water are going to come. Perfect. So do you see attraction taking place between the ion and the water molecules? Yes, attraction taking place. Due to attractions, energy is released. Tell me one thing. Can I say this ion is surrounded by the solvent molecules here? Can I say the ion is surrounded by the water molecules here? Yes. Can I say this ion is also surrounded by the water molecules? Yes. This phenomenon is something which you call as hydration. This phenomenon is what you call as hydration. The surrounding of an ion by the solvent molecules, which are particularly the water molecules. The surrounding of an ion by the water molecules is what you call as hydration. During hydration, you'll see attractions between the ions and these water molecules. Due to attractions, energy is released. Look at the definition now. Look at the definition now. The amount of energy released when 1 mole of a gaseous ion, undergoes hydration. That amount of energy released when 1 mole of a gaseous ion undergoes hydration, you call that amount of energy released as the hydration energy. Since energy is released, any such process in which energy is released, you call that as exothermic process. So hydration is exothermic in nature. If hydration is exothermic in nature, therefore I would say for every exothermic process, delta H is negative. So delta H hydration, you will always find to be negative. Am I clear with this? Am I clear with this, people? Quickly let me know in the chats. Am I clear with this? Everybody in the chats. I believe yes. Yeah? So this was your hydration energy. The amount of energy released when 1 mole of a gaseous ion undergoes hydration. Since energy is released during hydration, so the process is exothermic. If it is exothermic, delta H hydration will be always negative. Right? Now this hydration energy, it also depends on 2 factors. This hydration energy, it also depends on 2 factors. Let me tell you, this hydration energy, as you can see over here, it is directly proportional to charge on an ion. inversely proportional to the size of an ion. Hydration energy, it is directly proportional to the charge of an ion. Inversely proportional to what? Size of the ion. So basically, I can say, more the charge present on an ion, more water molecules will be attracted towards it. More energy is released. I would say more will be the hydration energy. As simple as that. Right? More the charge on the ion, more water molecules will be associated towards it. More the water molecules associated, more the energy released. More the energy released means more the hydration energy. Simple. Correct? Point number one. Point number two. Lesser the size of an ion, more is the charge density on the ion. Remember this. Lesser the size of the ion, more is the charge density of the ion. More the charge density on the ion, more water molecules will be associated towards it. More the water molecules associated, more the energy released. More the energy released, more the hydration energy. Am I clear with this? Am I clear with this, people? Am I clear with this, people? Am I clear with this? So in short, remember this particular stuff. Hydration energy is directly proportional to charge, inversely proportional to size. Now guys, you are going to tell me the answers of all these questions here. Li positive, Na positive, K positive, Rb positive. Okay, leave the first one aside. Look at the second one first. Li positive, Na positive, K positive, Rb positive. What is the order of these ions? What is the order of size of these ions? As you move from top to bottom in the periodic table, ionic size increases, right? Ionic size increases. So their size order is going to be this. Perfect. Their size order is going to be this. Now, what is the order of the hydrated size? Say, Na positive, when it's attracted by water molecules, after being attracted by the water molecules, this complete size, which is Na positive plus the surrounding water molecules, this I'll be calling as hydrated size of Na positive. The size of Na positive plus the size of the water molecules which are surrounding it, I'll be calling it as hydrated size. Now you have to give the order of hydrated size over here. Tell me first of all, among all these ions, which one would have gone maximum hydration? Which one among these would have shown maximum hydration? The one which has a lesser size would be hydrated more. So more water molecules will be associated with that. So with Li positive aqueous, more water molecules will be associated. So more would be the hydrated size. So this is the hydrated size order. Right? Can I say the one which has got hydrated the maximum? Its hydration energy will be more. So what will be the order of hydration energy? This is the order of hydration energy. So more hydration means more energy release. More energy release means more hydration energy. Right? Now guys, if this Li positive has undergone maximum hydration, so maximum water molecules are attached with this Li positive. Right? Since its size is maximum now. Hydrated size of Li positive is maximum. So hydrated Li positive is more bulky. Hydrated Li positive is more bulky than that of hydrated Na positive. If hydrated Li positive is more bulky, what about its mobility? Will it show more moment or lesser moment? The one which is more bulky will show lesser moment, right? So I would say this is the order of the mobility of these hydrated ions. Lesser the mobility, lesser the conductivity. Lesser the mobility, lesser the conductivity. So you'll be asked these sort of questions, which I believe you can easily solve now. Yeah? Am I clear, people? Is all this clear? Quickly in the chats, everybody. Quickly, everyone. Everyone in the chats. Yeah? All clear, people? All clear, all clear? Let me know in the chats with some fire emojis. Everybody in the chats. In the chats. In the chats. Perfect, guys. Perfect. Now, let's talk about the covalent compounds, which is the actual stuff that has to be discussed in this chapter, right? The actual stuff that has to be discussed in this chapter. What is that? Covalent compounds. Okay? Covalent compound. Covalent compounds. Covalent compounds. Is try to understand each and everything in detail. There are certain theories basically which we have to discuss related to covalent compounds. There are certain theories which we have to discuss related to the covalent compounds. Solubility we are not going to discuss here. Okay? Just wait. Solubility we are not going to discuss here. That will be discussed in another chapter. Wait for it. Here we'll be discussing only the bonding part. Okay? See, guys. So first of all, the first theory that we are going to discuss here, that is your Lewis theory. Lewis theory, right? Lewis theory. So this particular theory is going to explain how a covalent bond is formed. It is going to explain what is a covalent bond. It's going to explain what is a covalent bond. My dear students, something which you all would have studied from your class 6th, 7th, 8th. Covalent bond is formed between the two atoms by the mutual sharing of electrons. Bond formed between the two atoms by the mutual sharing of electrons, so as to complete their octets or duplets. The bond which is formed between two atoms by mutual sharing of electrons, that bond formed is what we call as covalent bond, right? That bond formed is what we call as covalent bond. Perfect. And why this mutual sharing of electron happens? Just to complete the octets or duplets of the atoms. Perfect. Just to attain the stable electronic configuration, as per Lewis theory. As per Lewis theory. Number 2, the number of electrons contributed by each atom is something which you call as covalency. Let's try to understand this. See, guys. For example, I'm talking about, let's say, F2 molecule. Let's say I'm talking about F2 molecule. Since this is, for example, your fluorine atom, this is one more fluorine atom. This is one more fluorine atom. This fluorine atom has got 7 electrons in its valence shell. This fluorine atom also has got 7 electrons in its valence shell. So if I ask you, is the octet of this fluorine atom complete? No. Is the octet of this particular fluorine complete? No. It has got 7 electrons in its valence shell. It should have 8. This also should have 8. So what they are going to do, they are going to give away one electron. This fluorine is going to give 1 electron. This fluorine is going to give 1 electron. Perfect. And this electron pair over here, this electron pair, it will be mutually shared by both the fluorine atoms. It will be mutually shared by both the fluorine atoms. And my dear students, this electron pair, which is mutually shared by both the atoms, this electron pair, I'll be calling as bonding pair of electron. I'll be calling this as bonding pair of electron. Number 1. Number 2. These electron pairs, which belongs to the valence shell of fluorine, these electron pairs, which belongs to the valence shell of fluorine, but do not participate in the bonding, you call them as the non-bonding electron pairs. You call them as the non-bonding electron pairs, or you can call them as the lone pair of electrons. You can call them as the lone pairs. You can call them as the lone pairs. Now one more thing. If I ask you how many electrons are contributed by each fluorine, one electron is contributed by each fluorine. One electron is contributed by each fluorine. And the number of electrons contributed by each atom while the formation of the covalent bond, that defines the covalency. So covalency of fluorine over here is 1. Covalency of each fluorine atom over here is 1. Correct? Simple. For example, let's talk about, okay, and finally, how do we represent this F2 molecule? F, single bond F, right? This is how you represent it at the end. F single bond F. Okay, F single bond F. Perfect. When each atom contributes one electron, perfect, a single bond is formed. When each atom contributes one electron, a single bond is formed. You should know it. So since each atom contributed one electron, so a single bond got formed between two fluorine atoms. For example, take the case of O2 molecule. Take the case of O2 molecule, people. Let's say this is one oxygen atom. This is one more oxygen atom. In the valence shell, in the outermost shell of oxygen, how many electrons will be there? There will be 6 electrons in the outermost shell of oxygen. Similarly, 6 electrons in the outermost shell of this oxygen as well. Now, in the outermost shell of this oxygen, there are 6 electrons, but it should have 8. Similarly, there are 6, it should have 8. So what they are going to do? Just to complete their octets, they are going to share these two electrons. They are going to share these two electrons, right? Now these two electron pairs, they'll be shared mutually by both the oxygen atoms. These two electron pairs, they are shared mutually by both the oxygen atoms. Why? Just to complete their octet. Now, do you see the octet of this oxygen is also complete? The octet of this oxygen is also complete. This oxygen has now got 8 electrons in its valence shell. Even this has got 8 electrons in their valence shell. Perfect. Right? So, these two electron pairs, what do you call them? Bonded electron pairs. These electron pairs, which belongs to the valence shell, but do not participate in the bonding, you call them as the non-bonding electron pairs or lone pairs. Right? Since this oxygen is contributing 2 electrons, this oxygen is also contributing 2 electrons. So covalency of both the oxygen atoms here will be 2, right? And at the same time, when each atom contributes 2 electrons, at that point of time, a double bond gets formed. When each atom contributes 2 electrons, a double bond gets formed at that point of time. Okay, all clear? Similarly, people, let's talk about, let's say, N2 molecule. Let's talk about N2 molecule. Let's see how this N2 molecule is formed. See, talk about one nitrogen. Talk about one more nitrogen. How many valence electrons with this nitrogen? 5. How many valence electrons with this nitrogen? 5. Right? Each nitrogen atom has got 5 valence electrons. Now, in order to complete the octet of this nitrogen, it needs 3 more. This also needs 3 more. So that 5 plus 3 makes it 8, so that their octets will be completed. Right? So what they are going to do over here is, they are going to contribute 3 electrons each. They are going to contribute 3 electrons each. This nitrogen is going to contribute 3 electrons. Even this nitrogen is going to contribute 3 electrons. And all these 3 electrons will be mutually shared by both nitrogen atoms. Now check. If you talk about this particular nitrogen, check. Is its octet complete? Is it now having 8 electrons in the valence shell? Yes. Is this nitrogen having 8 electrons in the valence shell? Yes. So octet of both these atoms are completed over here, right? And these 3 electron pairs I'll be calling as bonding pair electrons, right? This is the non-bonding one. This is the non-bonding one, right? Covalency of each nitrogen here comes out be 3, right? Covalency of each nitrogen here comes out be 3 because each nitrogen is contributing 3 electrons. And whenever each atom contributes 3 electrons, at that point of time, which bond gets formed? A triple bond gets formed. I believe this is super clear to everyone. Yes? If yes, let me know once in the chats so that I'll show you how do we draw structures of different molecules as per Lewis theory is concerned. Quickly in the chats, everybody. quickly in the chats, everybody, if all this stuff, if all these things, whatever I've told you till now, if it is super clear to everyone. Yeah? Perfect, guys. Perfect, perfect, perfect. Perfect. Now, guys, understand how Lewis showed the structures of simple molecule, right? See how Lewis showed the structures of simple molecules. So here you are going to understand how to draw the structures of different small molecules, right? As per Lewis theory is concerned. See, guys, how do we draw the structure of carbon monoxide? The first thing, I would want you guys to calculate the valence electrons of carbon and oxygen. Tell me how many valence electrons carbon has. Carbon has 4 valence electrons, you know. How many valence electrons oxygen has? It has 6 valence electrons, you know. So how many total valence electrons are there in CO? There are total 10 valence electrons in CO. If I ask you how many valence electron pairs are there with CO? 5 valence electron pairs. 1 pair means 2 electrons. So 5 pair means 10 electrons. So there are 5 valence electron pairs in CO. Now guys, in CO there are 2 constituent atoms, carbon and oxygen. Perfect. Now, the first thing which I'll be doing, I'll be putting a single bond between 2 atoms. Done. I've introduced 1 single bond. Okay. So 1 single bond means 1 electron pair. 1 single bond means 1 electron pair. So out of 5, I've used 1. So how many are left? 4 electron pairs are left. Right? Now I'll be starting with that particular atom which is more electronegative. So among carbon and oxygen, which one is more electronegative? Oxygen. Let me now start filling the octet of more electronegative element. So 2 already we have here. 4, 6, 8. Right? So I've filled the octet of oxygen. How many total valence electron pairs we had? 5. Out of 5, how many I've used? 1, 2, 3, 4. There is 1 electron pair still left. Give that 1 electron pair to carbon. Given. The octet of oxygen is complete. Check the octet of oxygen now. Check the octet of oxygen now. Is the octet of, check the octet of carbon now. Is the octet of carbon complete? No, have a look. 2 and 4, only 4 electrons. The octet of carbon is not complete. Now we have to complete the octet of carbon as well. So what do? Just remove one of the lone pair here. And instead of that, put a bond. Similarly, just remove one more electron pair here and put a bond. Now check the octet of both the atoms. Octet of both the atoms is complete. This oxygen, 1, 2, 3, 4, 5, 6, 7, 8. This carbon, 1, 2, 3, 4, 5, 6, 7, 8. Octet of both the atoms is complete. So this is the structure of your CO, carbon monoxide. Now guys, there is one more thing. What do we call that as? Do you see any sort of charge here on oxygen? So normally if I see, I don't see there is any charge on oxygen. I don't see there is any charge on carbon, right? Let's get to know if in reality some charge is there on carbon and oxygen or not. And what do we call that charge as? Formal charge basically. So let's calculate formal charge of carbon as well as the formal charge of oxygen. Here only. See the simplest way of calculating the formal charge. Formal charge on carbon. Is there any charge on carbon? Let's check it out. My dear students, in non-bonded state, how many valence electrons carbon has? In non-bonded state, if I've got one isolated carbon atom, how many valence electrons it will have? It will have 4. Minus. Check right now how many it has. Check right now how many it has. But how do you check it now? How do you check it now? Break all these 3 bonds. Break all these bonds. Give 1 electron. Each give 1 electron of all these bonds to carbon. Now check how many electrons are with carbon right now. 1, 2, 3, 4, 5. Right? 1, 2, 3, 4, 5. So 4 minus 5 comes out to be minus 1. So basically on this carbon, there is minus 1 charge. Check about this particular oxygen. In non-bonded state, How many valence electrons oxygen has? How many valence electrons oxygen has in non-bonded state? 6 minus. How many right now? 1, 2, 3, 4, 5. So 6 minus 5 is equal to plus 1, right? So there is basically plus 1 charge on this oxygen. So this is how you calculate formal charges as well. This is how you calculate formal charges as well. I believe I'm clear. If I'm clear, let's have a look on few more. Let's have a look on few more. Yeah. Let's have a look on few more so that you get completely used to all this stuff. See guys, NO2 negative. Let's make it a structure and let's see what kind of charges are present on the atoms. Yeah. Let's have a look. NO2. First of all, calculate the total valence electrons. See guys, nitrogen has got 5 valence electrons. Oxygen has got 6. 6 multiplied by 2 is 12. And there is negative charge. You have to add this negative charge. If there was positive charge, you were supposed to subtract that. See, 5 plus 1, 6. 6 plus 12 is 18. So there are in total 18 valence electrons. 18 valence electron means how many valence electron pairs? 18 by 2 is 9. So 9 valence electron pairs. Okay. Now here we have got 3 atoms, nitrogen and 2 oxygen. Now, how do I select which one is the central atom over here? How do I select? Is nitrogen or oxygen the central atom? Remember, generally, what do we do? Generally, less electronegative element is taken as the central atom. Generally, less electronegative element is taken as the central atom. Or, if in a molecule you have got hydrogen or fluorine attached. If in a molecule you have got hydrogen or fluorine attached. Hydrogen and fluorine is always taken as the surrounding atom. It is always taken as the terminal atom. Surrounding atom, terminal atom. Hydrogen, fluorine. Okay, but right now we do not have any hydrogen, fluorine, so leave it aside. Which one is central atom here? It has to be nitrogen, which is less electronegative. So this is nitrogen, for example. Okay. Now we have got 2 oxygen atoms, so 1 here, 1 here. What is the first thing? Put a single bond between these two. So out of 9 valence electron pairs, I have used 2. How many are left? 7. Start filling the octet of more electronegative element. Which one is more electronegative? Oxygen. So for example, start filling octet of this oxygen. 2 already it has. 4, 6, 8. Done. One more oxygen. 2 already it has. 4, 6, 8. Done. How many we had in total? 9. How many have we used? 3, 6, 7, 8. So there is one more left. Give that to this nitrogen. Now, octet of this oxygen is complete. 2, 4, 6, 8. 2, 4, 6, 8. Is the octet of nitrogen complete? No. The octet of nitrogen is not complete yet. 2, 4, 6. Right? So, in order to complete the octet of nitrogen, what do we need to do? Just remove any of the lone pair anywhere. Just remove one of the electron pair anywhere and put a double bond instead. So, this is the structure of your NO2 as per Lewis. Right? Do you see? See, when I look at this molecule, I do not see any charges here. But in reality, if you want to check, are there any charges on nitrogen? Are there any charges on oxygen? Are there any charges on this oxygen? That means you have to calculate at that time the formal charge. So formal charge of nitrogen will be equal to nitrogen when present in non-bonded state. How many valence electrons it has? 5. Nitrogen right now. First of all, break this bond. Break this bond. Give this 1 electron to the nitrogen. Give these 2 electrons to nitrogen. Now check. 1, 2, 3, 4, 5. So 5 minus 5 is 0. So nitrogen does not carry any charge here. Nitrogen does not carry any charge here. What about this oxygen? Oxygen number 1. Formal charge on oxygen number 1 will be equal to formal charge on oxygen number 1. In non-bonded state, oxygen has got 6 valence electrons. Right now, 1, 2, 3, 4, 5, 6. So 6 minus 6 is 0. This oxygen does not have any charge. Look at this particular oxygen. So formal charge on oxygen number 2. Formal charge on oxygen number 2. In non-bonded state, 6 valence electrons. In bonded state, 1, 2, 3, 4, 5, 6 and 7. So 6 minus 7 comes out to be minus 1. So there is minus 1 charge present on this nitrogen. I believe I'm clear. Yeah? Perfect, people. Perfect, perfect, perfect. Perfect. So this is how you calculate. This is how you draw the Lewis structures as well as the formal charges. Right? For example, you have got HCN. Let's do all the stuff with HCN as well. Calculate the valence electrons first. Hydrogen has got 1, carbon has got how many valence electrons? 4, and nitrogen has got 5. 5, 4, 9 plus 1, 10. So how many valence electron pairs in total? 5, right? Now, the one which is less electronegative has to be the central atom. And do you see hydrogen? Hydrogen has to be the surrounding atom. It has to be the terminal atom. Now, among carbon and nitrogen, which one is less electronegative? Carbon. So keep carbon as a central atom. On one side, give nitrogen. On one side, give hydrogen. First of all, put 1 single bond. Done. How many valence electrons? 5. Out of 5, how many we have used? 1, 2. 2 we have used. So how many are left? 3. Start filling the octet of more electronegative. So 2, 4, 6, 8. How many electron pairs we had? 5. How many have we used? 1, 2, 3, 4, 5. We have used all the 5 valence electron pairs. We have used all the valence electron pairs. No doubt, octet of nitrogen is complete. Duplet of hydrogen is also complete. But is the octet of carbon complete? Check it out. 2, 4. No. Octet of carbon is not completed. So what do I need to do? Remove one of the electron pair. Put a bond. Remove one more electron pair. Put a bond. Now check the octet of this carbon. 2, 4, 6, 8. Check the octet of this nitrogen. 1, 2, 3, 4, 5, 6, 7, 8. Perfect. Now, if you want to calculate the formal charges on different species, you can do that. Formal charge on hydrogen will be equal to hydrogen in non-bonded state has got 1 valence electron minus hydrogen right now in bonded state has got only 1 here. So 1 minus 1 is 0. Talk about this nitrogen. Formal charge of nitrogen in non-bonded state, 5 valence electrons. Break it. 1, 2, 3, 4, 5. So 5 minus 5 has to be 0. No formal charge on this nitrogen. Talk about formal charge of carbon. In non-bonded state, 4 valence electrons right now. 1, 2, 3, and 4. So 4 minus 4 has to be 0. Perfect, guys. So there is no formal charge on any of these atoms. So I believe you can easily do all this stuff now. Okay? I believe you can easily do all this stuff now. For example, O3. O3. Let's talk about O3, guys. See what this O3 is going to do. First of all, how many valence electrons in total? 1 oxygen, 6. 6 3s are 18. So 18 valence electrons in total. So how many valence electron pairs in total? 9 valence electrons in pairs. We have got O3, 3 oxygen atoms. So these are the 3 oxygen atoms, right? Put a single bond everywhere. Put a single bond everywhere. Now, start filling the octet of these terminal atoms. So, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Now come to the middle one. How many we had? 9. Out of 9, how many we have used? 1 electron pair, 2, 3, 4, 5, 6, 7, and 8. So 1 is left as such in the middle. Correct? 1 is left as such in the middle. No doubt, octet of this oxygen is complete. Octet of this one is complete, but the octet of the central one is not complete. So what I'll be doing, remove one of the electron pair, put a bond. Now, octet of all these atoms is completed. You can check it out too. Octet of all these atoms is completed. Right? You can check 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, and 8. Right? Now, calling this as atom 1, calling this as atom 2, calling this as atom 3. Let's calculate formal charge on the first atom. First oxygen. Oxygen has got 6 valence electrons in the non-bonded state. Right now, tell me how many we have after breaking this bond. 1, 2, 3, 4, 5, and 6. So 6 minus 6 comes out to be 0. Formal charge on the second oxygen atom. Right? Oxygen has got 6 valence electrons in non-bonded state. Minus. Right now, how many it has after breaking all these bonds? 1, 2, 3, 4, 5. 6 minus 5 is equal to plus 1. So this oxygen has got plus 1 charge on it. Talk about this oxygen. Formal charge on the third oxygen atom will be equal to. In non-bonded state, it has got 6 valence electrons. Right now, it has 1, 2, 3, 4, 5, 6, and 1 of it. 7. 6 minus 7 is equal to minus 1. So this third oxygen atom has got minus 1 charge on it as well. So this is how you calculate formal charges, and this is how you draw the different structures of different molecules. Let's take one more at the end. Cn negative. Cn negative, right? My dear students, look at the Cn negative. You should be in a position to do all this stuff again. You should be in a position to do all this stuff again. Cn negative. First of all, valence electrons with carbon. Carbon has got 4 valence electrons. Nitrogen has got 5 valence electrons. There is a negative charge, so add it up. So 5 plus 1, 6. 6 plus 4 is 10. So total 10 valence electrons. So how many valence electron pairs? 10 divided by 2, 5. 5 valence electron pairs. 5 valence electron pairs, people. Yeah? 5 valence electron pairs. Okay. Now, people. Carbon, nitrogen. First of all, put a single bond. Done. Now start filling the octet of that atom which is more electronegative. Which one is that? Nitrogen. So 2, 4, 6, 8. Done. How many valence electron pairs we had? 5. Out of 5, how many we have used? 1, 2, 3, 4. We have used 4 pairs. So 1 pair is left. I'm giving that to carbon. Now, no doubt, the octet of nitrogen is complete. But is the octet of carbon complete? No. We have to complete that. So remove the electron pair here. Put a bond. Remove the electron pair here. Put a bond. Check whether the octet of carbon as well as nitrogen, both are complete or not. Both are complete or not. Nitrogen 1, 2, 3, 4, 5, 6, 7, 8. Complete. This carbon 1, 2, 3, 4, 5, 6, 7, 8. Octet of both atoms is complete. Now, let's calculate the formal charge on nitrogen and then let's calculate formal charge on carbon. Formal charge on nitrogen will be equal to, in non-bonded state, nitrogen has got 5 valence electrons, minus. Right now, break it. 1, 2, 3, 4, 5. 5 minus 5 is 0. Right? Perfect. Formal charge on carbon. In non-bonded state, carbon has got 4 valence electrons, minus. Right now, 1, 2, 3, 4, 5. 4 minus 5 is minus 1. So formal charge on this carbon here is. I believe I'm clear with this. Yeah? All clear, people? Quickly, let me know in the chats. JEE aspirant, I seriously do not know. When do you need to write the improvement exam? That depends on which board you are in. Whether you are state board or the CBSE board, you can go to their site and check it out. Okay. So people, quickly in the chats, all this stuff is clear? Okay. Now, before talking about the coordinate bond, what is the significance of this formal charge? Why did we study this formal charge? Why did I show you how to calculate the formal charges on different atoms? My dear students, formal charges, what kind of information it gives us? Formal charge, the main advantage of the formal charge is that it helps to select the most stable structure of the molecule. As per Lewis theory, this formal charge, it is going to decide, it's going to help us in deciding the most stable structure of the molecule. Now, which one is the most stable structure of the molecule as per formal charge? That molecule which has got lesser formal charge on its atoms. That molecule which has got lesser formal charge on its atoms, that will be considered as maximum stable. That structure which has got lesser formal charge on its atoms, that structure will be considered to be maximum stable. Point number 1. Point number 2. That structure wherein negative charge will be present on more electronegative element. That structure wherein negative charge will be present on more electronegative element, that will be considered to be more stable. Okay, that will be considered to be more stable. That structure wherein the unlike charges, positive and negative charges, that structure wherein unlike charges are closer. The separation distance between unlike charges is less. Separation distance between the unlike charges is less. That is considered to be more stable. That structure wherein like charges or the unlike charges, like charges or the unlike charges, are if distance between them is less, stability is less. Okay, these are few things which I would want you guys to remember. These are few things which I would want all of you to remember. Right, people? Right? So first thing, that structure as per Lewis theory, as per Lewis structures, that structure which contains less formal charges on the atoms, more stable. If negative charge is present on more electronegative element, more stable. Okay? If the distance between unlike charges is less, more stable. If distance between like charges is less, less stable. That's all. These are few things which you need to remember. And with the help of these, you can identify the more stable structure as per Lewis theory. Yeah? All clear, guys? All clear, all clear? All clear? Okay, have you heard about coordinate bond? Have you heard about coordinate bond? Let me give you the idea about coordinate bond as well. Yeah, they are more of the rules of resonance, actually. Yeah? In resonance, you have got same rules. You know it, right? All right, what is a coordinate bond? If you look at the definition of coordinate bond, as per the definition, the bond formed between the atoms, in which contribution of an electron pair, is made by one atom, while sharing is done by both. What does that mean? For example, see guys, imagine you have got NH3. I'm not giving you the orbital approach here. I'm just giving you the normal Lewis theory approach. Let's say you have got NH3. And for example, you have taken an H positive. You have got H positive as well. Okay. In case of nitrogen, how many valence electrons do we have? 5. Nitrogen has got 5 valence electrons. Out of 5, how many it has used right now? 1, 2, 3. It has used 3 valence electrons. Can I say 2 electrons will be left on nitrogen in the form of lone pair? Yes. 2 will be left on nitrogen in the form of lone pair. H positive. If you talk about hydrogen atom, one hydrogen atom contains 1 electron, right? If it is H positive, that means this electron has been taken out. This H positive, it does not have any electron. So this H positive is hydrogen deficient. It does not have any electron. But you know, hydrogen would want to complete its octet somehow. But how would it complete its octet? If both the electrons are given by this nitrogen, but mutually shared by both, since nitrogen here is contributing both the electrons, right? But no doubt both the electrons are given by nitrogen, but those 2 electrons will be mutually shared by nitrogen as well as hydrogen. You call this sort of a bond as the coordinate bond. Now check. If this electron pair is mutually shared by this hydrogen as well as this nitrogen, octet of both atoms, octet of nitrogen is also complete. Duplet of hydrogen is also complete. Okay? This is one way of representing this coordinate bond, where nitrogen is the donor atom, hydrogen is the acceptor atom. This is donor, this is acceptor. This is one way of representing this coordinate bond. Second way. This was your nitrogen with hydrogen, and hydrogen. This nitrogen had a lone pair as well. Now, H positive came closer to it. H positive did not have any electron, but it wants to complete the octet. So what nitrogen did? It donated its lone pair. Towards this hydrogen. It donated the lone pair towards the hydrogen. No doubt, contribution of both the electrons is made by nitrogen, but this electron pair which will be mutually shared by both nitrogen as well as hydrogen. Okay? Now, donor atom gets the positive charge. Acceptor atom was supposed to get the negative charge if the acceptor atom was neutral. But acceptor atom already had positive charge. Positive and negative makes it neutral here. So leave this positive charge here. So this is how your NH4 positive actually looks like. If you want to represent it with the arrow, this is how you represent it. Then you do not have to show that donor will be getting the positive charges, right? But if you are just representing it with the help of this line, not with the arrow, then you have to represent that donor gets positive, acceptor gets negative. Since acceptor already had positive, that positive negative got neutralized. Okay, I hope you got to know about this particular structure. NH4 positive. For example, you have got H2OH positive. See, let's say you have got water, H2O. Oxygen has got, you must be knowing oxygen has got 2 lone pairs. Now let's say you have got H positive coming towards this water. Since H positive does not have any electron, so it would want to complete its octet. So what this oxygen is going to do? What this oxygen is going to do? This oxygen is going to give away its lone pair. It is going to give away its lone pair towards this hydrogen. So a coordinate bond has got formed over here. Both the complete electron pair is donated by oxygen, but shared by both, but mutually shared by both. So this is a coordinate bond. This is one way of representing it. Another way of representing it. You had water. Oxygen had 2 lone pairs. Now H positive came closer towards it. Let's say you don't want to represent. Let's say you do not want to represent the coordinate bond with the help of the arrow. Let's say you want to represent it with the help of bond. So what you will say? You will say remove one of the electron pair from here, right? Give that electron pair to hydrogen. Since oxygen is the donor, it will carry the positive now. This donor gets the positive, acceptor gets the negative. But acceptor already had positive. That positive and negative gets nullified. And this positive charge you can remove from here. So either way you can show H3O positive. Either way you can show H3O positive here. Okay. Perfect. Now look at this BF3 and F3. BF3 and H3. Let's say this is B, this is F, this is F, and this is F. This is your BF3. Let's say this is your N, H, H, and H. Perfect. You know nitrogen has got 1 lone pair as well. Since nitrogen has got 5 valence electrons, out of 5 it has utilized 1, 2, 3. So 2 electrons are left as such on nitrogen. Now look at the octet of boron. Is the octet of boron complete here? Check it out. 2, 4, 6. It is not complete. It is incomplete octet. So it would want to complete its octet. So what this nitrogen is going to do? This nitrogen is going to donate its electron pair towards nitrogen in the form of a coordinate bond. This is one way of representing it. Another way of representing the same thing. This was your NH3. This was your NH3. And this was your BF3. If you do not want to represent with the help of arrow, represent with the help of single dash. Now, donor is going to get positive, acceptor is going to get negative. This is one way of representing this coordinate bond. So it's a coordinate bond here, it's a coordinate bond here as well. Perfect. BF4 negative. Have a look. BF4 negative. How BF4 negative gets formed? Imagine this is your BF3. Imagine if this is your BF3 and this F negative here. So what is going to happen? This boron is electron deficient. So this fluorine, F negative, it's going to donate one of its lone pair towards here, right? And that lone pair, which will be mutually shared by both boron and fluorine. So this is your BF4 negative, right? This is your BF4 negative. I believe you got to know what is the significance, what is the meaning of this coordinate bond. In the coordinate bond, in order to form the bond, both the electrons will be given by one atom, but both the electrons will be mutually shared by both the atoms. Do you get this? Do you get this, people? Do you get this? Yeah? Look at this one. This was your O3. This was its structure. O, single bond O, double bond O, lone pair, one hair, right? 1, 2, 3, 4, 5, 6. I told you this oxygen carries positive, this oxygen carries negative. Positive, negative. My dear students, don't you feel it's a dash, positive here, negative here? Don't you feel this has to be the coordinate bond here? Yeah, you should be in a position to understand now. Basically, it's a coordinate bond here which has got formed. Technically, if you see it. I told you, coordinate bond. Donor gets positive, acceptor gets negative, then you just have to represent it with a dash. This is one way of representing. Another way of representing. Donor to acceptor, arrow. No need to show the charges. Right? Here, one dash I have represented, positive, negative. So it is basically a coordinate bond here. Got it? I believe this is clear. I believe, people, this is clear to every one of you. Okay, I believe this is clear to every one of you. Perfect. So now we are going to enter into one more topic, that is Fazan's rules. Perfect then. Perfect. So let's get going with the new topic, that is Fazan's rules. Right? Fazan's rules. This is again something very important, guys. From this particular topic also questions have been frequently asked. Right? And it's easy at the same time. Okay? So let's get to know what Fazan's rules exactly are all about. Before letting you know about the Fazan's rules, there are certain basic things which I have already mentioned over here on the screen. Point number 1. My dear students, no bond can be 100% ionic or 100% covalent. No bond can be 100% ionic or 100% covalent. Every single covalent bond, contains some ionic character, and every ionic bond also contains certain covalent character. Every ionic bond will be having some covalent character into it, and every covalent bond will be having some ionic character into it. Covalent character in an ionic bond. Covalent character in an ionic bond cannot be calculated, but can be compared. My dear students, for example, let's say I have got a molecule HF. Let's say this is the molecule HF, correct? You know, there is a single bond between hydrogen and fluorine. We have already discussed this. There is a single bond between hydrogen and fluorine. It's a covalent bond. No doubt, it's a covalent bond between hydrogen and fluorine. But at the same time, if you think logically, among hydrogen and fluorine, which one is more electronegative? I would say fluorine is more electronegative. If fluorine is more electronegative, can I say this electron pair will be shifted towards fluorine? Due to which fluorine gets delta negative, hydrogen gets delta positive. No doubt the bond was covalent. But over here, if you see, due to electronegativity difference, can I say ionic character got generated in this bond? No doubt the bond was covalent, right? And in this covalent bond, what got generated? Ionic character got generated. So this covalent bond has got some ionic character into it. Right? So my dear students, what I'm trying to say over here is, there will be no bond which will be 100% covalent or 100% ionic. Every covalent bond will be having certain ionic character into it. And every ionic bond will also have some covalent character into it. Okay? Every ionic bond also have got some covalent character into it. Now, covalent character in an ionic bond, it cannot be calculated, but it can be compared. And how do we compare covalent character in an ionic bond? We compare covalent character in an ionic bond with the help of what? With the help of Fazan's rules. So the rules which we are going to discuss, the Fazan's rules. Fazan's rules are used to compare covalent character in an ionic bond. Okay? Covalent character in an ionic bond. Now, before talking about the Fazan's rules in detail, there are a few basic things which I'm going to share with you. There are some basic things which I'm going to share with you. Then we'll talk about Fazan's rule. My dear students, imagine that you have got an atom A. Imagine that you have got an atom A. Let's say this atom has got some 10 protons as well as 10 electrons. Imagine that this atom has got 10 protons as well as 10 electrons. So I would say right now, 10 protons are holding its 10 electrons. I would say right now, 10 protons are holding its 10 electrons. Now imagine that you are taking one electron out of this particular atom. When you take one electron out of this atom, it gets converted into A positive. Since you took an electron out from that, did you do anything with the protons? No, I did not do anything with the protons. Protons are still the same, but electrons now won't be 10. Electrons now will be only 9. Correct? So can I say initially 10 protons were holding 10 electrons. Now, the same 10 protons, they are only holding 9 electrons. Initially 10 protons were holding 10 electrons. Now, the same 10 protons, they are holding only 9 electrons. They're only holding 9 electrons. My dear students, can I say, since 10 protons are only holding 9 electrons, can I say force of attraction experienced by the electron here will be more? Because 10 protons are holding 9 electrons only now. Initially 10 protons were holding 10 electrons. Now 10 protons are holding only 9 electrons. So the force of attraction experienced by the electrons here will be more than that of the first case. Right? Right, people? What does that mean? What does that mean? Force of attraction experienced by the electrons over here will be more. What does that mean? That means effective nuclear charge here will be more. Here, the effective nuclear charge is comparatively less. Right? So, my dear students, what happened due to the increase in the effective charge? Due to the increase in the effective charge, I would say attractive power has increased. I would say attractive power has increased. Can I say something like this? Yeah. Now try to understand what exactly it means. See, my point is, when a parent atom, this was the parent atom, when the parent atom is converted, when the parent atom is converted into its cation, first thing, effective nuclear charge increases, due to which attractive power, what happens to it? It increases. Simple and basic. Yes. Now similarly, my dear students, imagine something like this. Let's say you have got atom B. Let's say it had some 10 protons in it and there were 10 electrons also. There were 10 protons and 10 electrons in this atom B. So 10 protons were holding 10 electrons. Now imagine I'm giving 1 electron to this B. When I'm giving this 1 electron to B, it gets converted into B negative. Since I'm giving electron to B, am I doing anything with the protons? No. But electrons initially were 10, now there will be 11. Now there will be 11, right? Now, my dear students, what can you conclude from here? Can I say initially 10 protons were holding 10 electrons. Now 10 protons are holding more electrons. 10 protons are holding 11 electrons. So force of attraction experienced by this electron over here will be comparatively less. Initially 10 protons were attracting 10 electrons. Now same 10 protons are attracting more electrons, 11 electrons. So the force of attraction experienced by the electrons now will be comparatively less. So I can say over here, the effective nuclear charge was more, and right here, the effective nuclear charge is less. So I can simply generalize a statement. When a parent atom is converted when a parent atom is converted into the anion. The first thing, effective nuclear charge decreases, due to which I can say attractive power, what happens to it? It decreases. I believe these two statements are absolutely clear to every one of you. If they are clear, let me know once in the chats quickly. If these two statements are clear to you. Okay? So whenever you'll be converting the parent atom into the cation, attractive power will be increasing. Whenever you'll be converting the parent atom into the anion, attractive power will be decreasing. This is the first point. Okay? Now, let's come to the Fazan's rules. My dear students, understand what Fazan's rules exactly are all about. As I told you, Fazan's rules are going to give us the idea. Fazan's rules will teach us how to compare covalent character in an ionic bond. Right? Perfect. Now, let's get to know about these Fazan's rules properly. My dear students, the first statement which I mentioned over here. Look at the statement carefully. When the cation approaches an anion, distortion of electron cloud takes place. Distortion of electron cloud of anion takes place. This phenomenon is called as polarization. Due to polarization, covalent character is induced in an ionic bond. What does it mean? Try to understand properly, guys, what it means. My dear students, imagine this is a cation over here. Imagine this is the cation. Cation carries which charge? It carries a positive charge, right? Imagine this is the anion over here. And anions are generally bigger in size than that of cations. This is the anion. Okay? The electron cloud of cation as well as electron cloud of anion. Right now, both the electron clouds, they are spherically symmetric. I'm assuming. They are spherically symmetric. Now, my dear students, when this cation will approach this anion, what is going to happen? See, imagine this is the nucleus of cation. Imagine this is the nucleus of anion. Okay? And what is this particular thing? This is electron density. This is the electron density of the anion. Okay? Which I'm representing over here. This is the electron density of the anion. And this is the electron density of what? This is the electron density of cation. Okay? Now, when this cation is going to approach towards anion, what is going to happen? When this cation is going to approach towards anion, I would say this cation will attract the electron density of this anion towards itself. When this cation is going to approach towards anion, I would say the cation is going to attract the electron density of the anion towards itself, due to which the electron cloud of anion, which was spherically symmetric, now since this cation is attracting the electron density towards itself, I would say this electron density of anion will shift in this direction. The electron density of the anion will shift in this direction. Electron density of anion will shift in this direction. Because this cation is attracting the electron density of anion towards itself. Okay? My dear students, initially the electron cloud of anion was spherically symmetric. Now, the electron density of anion has shifted towards this side. This phenomenon of shifting the electron cloud of anion towards the cation, this phenomenon is what we call as distortion of electron cloud. This is something which I call as distortion of electron cloud of anion. And this distortion of electron cloud of anion, when the cation approaches towards it, is something which we call as polarization. So what is polarization first of all? Polarization means distortion of electron cloud of anion when the cation approaches towards it. Right? This distortion of electron cloud is something which we call as polarization. Look at the statement again now. When the cation approaches the anion, distortion of electron cloud takes place, right? Due to the distortion of electron cloud takes place. And this distortion of electron cloud is what we call as polarization. My dear students, due to polarization, covalent character is induced in an ionic bond. How can we understand this? Due to distortion, covalent character is induced in an ionic bond. My dear students, just think logically. This anion, its electron cloud in the beginning was spherically symmetric. Now the electron cloud has shifted towards cation. Do you see? Electron cloud is coming in the middle of cation and anion. Do you see? As if the electron cloud is coming in between, right? If electron cloud is coming in between the cation and anion, just imagine it like this. Do you think it like this? That this electron cloud, which has got distorted, right? Which has got distorted, which is now in the middle. Can you see this electron cloud somewhat is now mutually shared between cation and anion? Can I say that? Now this part of electron cloud is mutually shared between cation and anion. Mutual sharing means what? Covalent bond. Mutual sharing means what? Covalent character. So can I say this ionic bond has now got some covalent character into it? Did you understand this? Did you understand this, people? So when the cation approached the anion, what happened? The cation attracted the electron cloud of anion towards itself, due to which some part of electron cloud of anion is coming in the middle, right? Or you can say that electron cloud which is coming in the middle, now it's mutually shared between cation and anion, and mutual sharing leads to covalent character. It leads towards what? Towards the covalent character. I would say when the cation approached towards anion, distortion of electron cloud of anion took place, due to which, and that distortion of electron cloud is what you call as polarization. Due to polarization, what happens? Covalent character is induced in an ionic bond. Due to which covalent character is induced in an ionic bond. Right? Perfect? Perfect, guys? And let me tell you, covalent character is simply directly proportional to polarization. More the polarization, that means more the electron cloud in the middle. So more will be the covalent character in short. As simple as that. Yeah? So let me quickly summarize this. When the electron cloud when the cation approaches towards the anion, this cation is going to attract the electron cloud of anion towards itself. That phenomenon is called as distortion of electron cloud. And distortion of electron cloud of anion is what you call as polarization. Due to polarization, covalent character is induced in an ionic bond. More the polarization, more the electron cloud in the middle, more the covalent character, right? So covalent character is directly proportional to polarization. More the polarization, more is going to be simply the covalent character in an ionic bond. Now, factors affecting polarization. Factors affecting polarization. The first factor on which polarization depends on, that's what you call as polarizing power. And polarizing power is defined for what? Polarizing power is defined for cation. Polarizing power is also called as ionic potential. You can also call it as ionic potential. Ionic potential. Now, how do we define the polarizing power of cation? Simple words. In simple words, the tendency of the cation to distort the electron cloud of anion towards itself. The tendency of the cation to attract the electron cloud of anion towards itself. That defines what? That defines polarizing power of cation. Simple. Simple. The tendency of the cation to distort the electron density of anion. Right? Okay? Perfect. Now think logically. If I say more is the polarizing power of cation, if I say more the polarizing power of cation, that means more is its tendency, more is the tendency of the cation to attract the electron cloud of anion towards itself. That means more would be the distortion. More would be the distortion of electron cloud of anion. If more is the distortion of electron cloud of anion, I can say more is the polarization. And if more is the polarization, I can simply say more is the covalent character in an ionic bond. As simple as that, right? So polarizing power of cation is directly proportional to covalent character, right? Is directly proportional to covalent character. So remember this particular statement, my dear students. Your covalent character in an ionic bond, it is directly proportional to what? Polarizing power of cation. It is directly proportional to polarizing power of cation. Perfect. Now this polarizing power of cation, it depends on two things. the polarizing power of cation, it depends on two things. Number one, polarizing power of cation, my dear students, polarizing power of cation, it is directly proportional to the charge on cation and inversely proportional to size of cation. Polarizing power of the cation, it's directly proportional to charge of cation, inversely proportional to size of cation. Now try to understand. Try to understand, people. See, if more is the charge on cation, think over it. If more is the charge on cation, that means cation has got more positive charge. If cation has got more positive charge, it is going to attract more electron density of anion towards itself. More will be the polarization. More will be the covalent character. So simple, in short, more the charge on the cation, more is going to be the polarizing power of the cation. More polarizing power of cation means more tendency of the cation to distort the electron cloud of anion. Hence more is the polarization, hence more is the covalent character, in short, right? Similarly, if you talk about the size, my dear students, think about it. Lesser the size of cation, more will be its charge density. Lesser the size of cation, more will be the charge density of the cation. If more is the charge density of the cation, it will attract more electron cloud of anion towards itself. That means more will be the distortion of electron cloud of anion. More the distortion of electron cloud of anion, more is going to be the polarization. More polarization means more covalent character. So in short, leave all this aside. Polarizing power of cation is directly proportional to what? Charge on cation, inversely proportional to size of cation. Now, if this is something which is clear to you, tell me, among these two ions, which one will be having more ionic potential? Which one will be having more polarizing power? You should be in a position to say it. You should be in a position to say it, people. Tell me quickly in the chats. Tell me quickly in the chats, everybody. Everyone. Everyone. Everyone in the chats. Done? See, I told you more the charge on cation, more the polarizing power. More the charge on cation, more the polarizing power. More the charge on cation, more the polarizing power. Done and dusted. Right? Done and dusted. Done and dusted. Second thing. Li positive, Na positive, K positive, Rb positive, Cs positive. Everywhere charge is same. So you are not going to decide on the basis of charge. You will be deciding on the basis of size. Lesser the size of cation, more is its polarizing power. Lesser the size of cation, more is its polarizing power. Because I told you, polarizing power directly proportional to charge, inversely proportional to size. Charge everywhere is same. Decide on the basis of size. Lesser the size of cation, more the polarizing power of cation. More the polarizing power of cation. Right? Now, my dear students, one more thing. As I told you already, polarizing power is also called as ionic potential. And at the same time, polarizing power also depends upon the effective nuclear charge in case of d block elements. Remember this particular point as well. Polarizing power of the cation, it depends on the effective nuclear charge of the cation in case of what? D block elements. You know, in case of D block elements, what happens generally? On moving from left to right, effective nuclear charge increases. Even on moving from top to bottom, in case of D block elements, effective nuclear charge also increases. Polarizing power depends on the effective nuclear charge in case of the D block elements, right? Perfect. On moving from left to right, in case of D block elements, effective nuclear charge increases. What does that mean? That means attractive power increases. If attractive power of cation increases, that means there will be more distortion of electron cloud of anion. If there is more distortion of electron cloud of anion, there is more polarization. If there is more polarization, more covalent character, in short. Yeah? Right? See, guys. For example, these are the cations which we have, right? How to arrange them on the basis of their polarizing power. My dear students, look carefully. This is 3d6. This is 3d7 configuration. This is 3d8 configuration. This is 3d9 configuration. Right? Fe dye positive, cobalt dye positive, nickel dye positive, copper dye positive. So basically we are moving from left to right. When we move from left to right, in case of d block elements, effective nuclear charge increases. Effective nuclear charge increases means attractive power of cation increases. So in short, polarizing power of cation increases. Polarizing power of cation increases. Right? This is something which also I told you. In case of d block elements, when you move from top to bottom, from 3D to 4D, from 4D to 5D, what happens to effective nuclear charge? Effective nuclear charge also increases. Effective nuclear charge also increases, right? In case when you are moving from 3D to 4D, 4D to 5D, effective nuclear charge increases. And if effective nuclear charge increases, polarizing power of the cation increases. See, zinc dye positive, cadmium dye positive, mercury dye positive. They belong to same group, right? This is a 3D element. This is 4D element. This is 5D element. On moving from 3D to 4D, 4D to 5D, effective nuclear charge increases. Therefore, polarizing power increases. Therefore, polarizing power increases. So this is the order of the polarizing power. Right? Now comes one more thing on which covalent character depends on. First thing on which covalent character depends on. Covalent character depends on the polarizing power of cation. Second thing, covalent character in an ionic bond depends on the polarizability of anion. It depends on the polarizability of anion. Now, what is polarizability? What is polarizability of anion? My dear students, polarizability, as I told you, it is defined first of all for anions. Now, how do we define polarizability? It is simply the tendency of the anion, the tendency of an anion to get polarized. The tendency of an anion to get polarized. More the tendency of an anion to get polarized, more the tendency of an anion to get polarized, more is the polarization, more is the covalent character. As simple as that. Polarizability, that is defined for anions, and polarizability means the tendency of an anion to distort its electron cloud. Let me write it in simple words. Tendency of an anion to distort its electron cloud. Tendency of an anion to distort its electron cloud is something which we call as polarizability. More the polarizability, more is the tendency of the anion to distort its electron cloud. That means more will be the polarization, more will be the covalent character. So remember the second point, covalent character in an ionic compound is directly proportional to polarizability. It's directly proportional to polarizability of what? Polarizability of anion. Now the point is, on what factors this polarizability of anion depends on? Let me tell you, polarizability of anion, first of all, depends on, it is directly proportional to charge on anion. It is directly proportional to charge on anion. And at the same time, it is directly proportional to size of the anion as well. Size of the anion as well. Let's try to understand this particular statement. See guys, polarizability of an anion is directly proportional to charge on anion first of all. And at the same time, it is directly proportional to size of anion. Tell me one thing. If the size of anion is more, let's say this is one anion, let's say over here, this is one bigger sized anion, right? This is one bigger sized anion. And over here, you have got a smaller sized anion, right? My dear students, tell me one thing. Among these anions, the size of the electron cloud of this anion is more. If the size of the electron cloud of this anion is more, can I say its nucleus won't be holding its electron density the way this nucleus will be holding its electron density? Because its size is comparatively less. So nucleus will be holding its electron density more here as compared to this. So where is the distortion of electron cloud easy? In the first anion or second anion? In the second anion, the distortion of electron cloud is easy. Electron cloud can get easily distorted here. Because this nucleus, since the size of the electron cloud is more, this nucleus won't be holding its electron cloud effectively towards itself. So we can distort this electron cloud easily as compared to the first one. So wherever distortion of electron cloud can happen easily in anion, there only polarization will be more. And wherever polarization is more, covalent character will be more there. In short. Am I clear with this? Am I clear with this? Am I clear with this, people? Okay. One more thing. More the negative charge on an anion, lesser will be its effective nuclear charge. If lesser is the effective nuclear charge of anion, that means its nucleus won't be holding its electron density more towards itself. So electron cloud can get easily distorted. If the electron cloud is getting easily distorted, what does that mean? More is the polarization. If more is the polarization, more is the covalent character. Am I clear with these two things, guys? Can you let me know quickly in the chats? Everybody. Yeah? So in short, you're going to remember simple this thing. Polarizability of anion is directly proportional to charge on anion. And at the same time, it is directly proportional to size of anion. And more the polarizability of anion means, more is the tendency of an anion to distort its electron cloud. More the distortion of electron cloud of anion, more polarization. More polarization means more covalent character. In short. Okay? Now, tell me the answer of this one. N tri-negative, O di-negative, F negative. Among these anions, which one has got more polarizability? Polarizability is directly proportional to charge on anion. Polarizability is directly proportional to charge on anion. Right? Simple. Simple, people. Right? Now, among these anions, where is the polarizability more? Where is the polarizability more? The charge on every anion is same. Now decide on the basis of size. More the size of anion, more is its polarizability. Right? More the size of anion, more is its polarizability. More the size of anion, more is its polarizability. If charge on anion is same. If charge on anion is same. Right? Clear? Clear, people? See, nitrogen, phosphorus, they belong to the same group. On moving from top to bottom, size increases. Right? So size of P tri-negative will be more than this. Size of S di-negative will be more than this. Similarly, I negative size will be maximum. Simple and basic. Perfect, guys? All clear? All clear? All clear? Tell me the answer of this question. Arrange on the basis of the order of their polarizability. Which anion can get polarized more? First, give preference to charge. More the charge on anion, more is the polarizability. More the charge on anion, more the polarizability. Remember, O di-negative, I negative. Their polarizability is almost the same. Almost the same. Okay, remember this particular thing. Now, I negative, Br negative, Cl negative, F negative. Since charge on all these four species is same, so decide on the basis of size now. More the size of anion, more the polarizability. So this is the order. O di-negative, OH negative. More the charge on anion, more the polarizability. Right? This is something which you will tell me in the comment section at the end. Which one can get polarized the maximum among all these 4 or 5 species? Yeah? Perfect? Now, people. Now, let me quickly summarize all the stuff. Let me quickly summarize all this stuff. And this is the summary which I'm again repeating particularly for you guys. Right? Take a note of this summary. Summary is covalent character in an ionic bond. Covalent character in an ionic bond. First of all, covalent character will be inversely proportional to what? Ionic character. More covalent character means lesser ionic character. Right? Now, covalent character depends on the polarization. It depends on the polarization. Polarization depends on 2 factors. One is polarizing power of cation and one is polarizability of anion. Polarizability of anion. Right? See, covalent character is inversely proportional to ionic character. Covalent character in an ionic bond depends on polarization, directly proportional. Polarization depends on polarizing power of cation At the same time, polarization depends on polarizability of anion. Okay? And polarizing power of cation depends on the charge on cation and size of cation too. Similarly, polarizability of what? Of anion. It also depends on charge on anion. Charge on anion also it is directly proportional to size of anion. This is the quick summary of all the things which we have discussed. Quick summary of all the things that we have discussed, right? Let's try to solve certain questions. See guys, over here if you see zinc dye positive, cadmium dye positive, Hg dye positive, Cl negative, Cl negative, Cl negative. So you are not going to decide on the basis of anion. Leave the anion aside because anion is same everywhere. Decide on the basis of cation. Arrange in the following on the basis of covalent character. See, this is 3D, 4D, 5D. From 3D to 4D, 4D to 5D. Effective nuclear charge increases, polarizing power of cation increases, and if polarizing power of the cation is more will be the polarization. If more is the polarization, more is the covalent character. So this is the order. Similarly here, zinc dye positive, cadmium dye positive, mercury dye positive, 3D, 4D, 5D, right? Here, Li positive, Na positive, K positive, Rb positive, Cs positive. F negative everywhere is same. So you are not going to decide on the basis of F negative. Decide on the basis of polarizing power of cation, right? Charge on every cation is same. Talk in terms of size of cation. More the size of cation, lesser will be its polarizing power. Lesser the polarizing power means lesser the covalent character. So what is going to be the order here? Covalent character order. This is the order of covalent character. Here you have got Be dye positive. This is Be here, by the way. This is Be. Okay. This is Be dye positive. This is Be dye positive here. This is Be dye positive. So you cannot decide on the basis of cation here. Decide on the basis of anion. F negative, Cl negative, Br negative, I negative. Charge on every anion is same. Charge on every anion is same. Talk in terms of size. More the size of anion, more the polarizability of anion, more the polarizability of anion, more is the covalent character. This is the order of covalent character. Clear, people? I hope this is clear. What do you think is the answer of this particular question? See, this is Al tri positive, F negative, Al tri positive, Cl negative, Al tri positive, Br negative, Al tri positive, I negative. So cation everywhere is same. You cannot decide on the basis of cation. Leave it. Talk in terms of anion. Talk in terms of anion. Charge on every anion is same. Look at the size. More the size of anion. I negative has got maximum size, followed by Br negative, followed by Cl negative, followed by F negative. More the size of anion, more is the polarizability. More the polarizability of anion, more is going to be the covalent character. Similarly, here I negative, Br negative, Cl negative. Similarly, I negative, Br negative, F negative. I negative, Br negative, Cl negative, F negative. This is the order. This is the order of the covalent characters. Is it clear, guys? Is it clear? Is it clear? Quickly. Is it clear? Is it clear? So, if I summarize things, when you see smaller cation and larger anion, smaller cation, larger anion means more covalent character. Means more covalent character. Right? Perfect. Similarly, more charge on cation, or more charge on anion means that we have got more covalent character. So in short, you can remember this stuff. Okay? All clear, people? Now, guys, there are few things which you need to remember over here. Polarizing power of that cation, which has got pseudo inert gas configuration, will be more than that of polarizing power of the cation, which has got inert gas configuration. Now, first of all, what is pseudo inert gas configuration? Understand. For example, I've got copper positive. Let's say I've got copper positive. Over here, I'm taking Na positive. Okay? Copper positive, Na positive. What is the outermost configuration of copper positive? It is going to be argon. With argon, you'll be writing 3d10. This is the configuration of copper positive, right? What is the configuration of Na positive? It's going to be neon. It was supposed to be 3s1, but that one electron is lost. So it is 3s0. This is the electronic configuration of Cu positive. This is the electronic configuration of Na positive. My dear students, whenever you see this sort of the electronic configuration, what is it? Electronic configuration of the noble gas followed by D10 configuration. Electronic configuration of noble gas, inert gas, followed by D10 configuration. This electronic configuration is what you call as, this sort of the electronic configuration is what you call as pseudo inert gas configuration. Pseudo inert gas. This Na positive, what kind of configuration it has? It has got exactly the inert gas configuration. Whatever is the configuration of neon, same is the configuration of Na positive. So Na positive has got inert gas configuration. Whenever you have such kind of the cation which can show the pseudo inert gas configuration, remember polarizing power of that cation is more. Polarizing power of the cation which shows the pseudo inert gas configuration is always more than the polarizing power of that cation which shows the inert gas configuration. Right? Where can I use this particular thing? Look at this question. CuCl, NaCl. CuCl, NaCl. This is Cu positive, Cl negative. Na positive, Cl negative. Anion is same. You cannot decide on the basis of anion. Now talk in terms of cation. Cu positive, Na positive. Few minutes back we saw this Cu positive. It has got pseudo inert gas. Inert gas followed by 3d10. Inert gas configuration followed by D10 configuration. Here you have got properly inert gas configuration. So this is pseudo inert gas configuration. This is inert gas configuration. And polarizing power of that cation which shows pseudo inert gas is more. If polarizing power of this cation is more, hence covalent character is more, because polarizing power is directly proportional to covalent character. Am I clear, people? Am I clear? Am I clear? Am I clear quickly? Now. There are some applications of the Fazan's rules which you need to know. Certain applications of the Fazan's rules which you must know, guys. What are these applications? Let's try to understand. What are these applications? See, guys. First of all, before making you understand this particular statement, let me write certain things over here. Solubility of ionic compound. Solubility of ionic compound will be more than that of solubility of covalent compounds in polar solvents. Ionic compounds will show more solubility than covalent compounds. In which solvents? In polar solvents, right? This is something which you should know. Okay? Perfect. Now understand one thing. I can say it like this as well. Solubility of ionic compound is more than that of covalent compound. I can say solubility is directly proportional to ionic character, right? More the ionic character, more the solubility. Hence, inversely proportional to covalent character. Now, we can look at this particular question. Understand. We are given with Ag2S and we are given with Ag2O. First of all, cation is, this is +1, this is -2. This is +1, this is -2. First of all, cation is same. Leave cation aside. Talk in terms of anion. S dinegative, O dinegative. Charge on both the anion is same. Talk in terms of size. S dinegative has got more size than O dinegative because this is O, this is S in the same group. Down the group, size increases. S dinegative has got more size. More the size of anion, more the polarizability of anion. More polarizability means more covalent character. So which one has got more covalent character? This one has got more covalent character. This is the order of covalent character. If this is the order of covalent character, you should be telling me the order of ionic character as well. this has to be the order of ionic character. Because covalent character is inversely proportional to ionic character. And more the ionic character, more the solubility. So which one is going to be more soluble? Ag2O is going to be more soluble than Ag2S. This was the question. This was the question. Ag2S is less soluble than Ag2O. Is less soluble than Ag2O. This is the solubility order. I hope I'm clear with this particular application part. Yeah? Right? Done and dusted. Moving on to one more application. See guys, over here I'm taking two compounds. Now you know the logic. I'm taking FeOH whole thrice and I'm taking FeOH whole twice. OH negative, OH negative. Fe tri positive, Fe di positive. Correct? Anion is same, leave anion. Talk in terms of cation. Talk in terms of cation. More the charge on cation, more is the polarizing power of cation. More polarizing power of cation means more covalent character. So this is the order of covalent character. If this is the order of covalent character, what will be the order of ionic character? You tell me. Opposite of it. This is the order of ionic character. If this is the order of ionic character, what will be the order of solubility? Solubility shows the same order as that of ionic character. Right? Because solubility is directly proportional to what? Ionic character here. This is the order of solubility. So, if you see properly, FeOH whole thrice is less soluble than FeOH whole twice. Got it? Is it clear, people? Is it clear? Similarly, one more application for melting point. You can decide melting points also on the basis of Fazan's rules. How exactly? You just need to remember 2 points. The first point. My dear students, generally what you will observe, melting points of ionic compounds will be more than that of melting points of covalent compounds. Ionic compounds have got more melting points than covalent compounds. Ionic compounds have got more melting points than covalent compounds. Or in other words, you can say melting point is directly proportional to ionic character and automatically it becomes inversely proportional to covalent character. Since ionic compounds have got more melting points generally than covalent compounds, right? So more the ionic character means more melting point. More ionic character means more melting point. Now, for example, you have got certain compounds like this, BeCl2, then you have got magnesium chloride, CaCl2, SrCl2, BaCl2. These are the chlorides of group second elements. These are the chlorides of group second elements, right? Now, everywhere anion is same. Everywhere anion is same. Talk in terms of cation. This is B di positive, this is magnesium di positive, this is calcium di positive, strontium di positive, barium di positive, right? Now tell me one thing. Charge on every cation is same. Talk in terms of size. On moving from top to bottom, size increases. Polarizing power of cation decreases. Covalent character decreases. So what is the order of covalent character first of all? I would say BeCl2 is maximum covalent, right? Followed by MgCl2. Followed by CaCl2, followed by SrCl2, followed by BaCl2. This is the order of covalent character. What is the order of ionic character? It will be reverse of this. This is the order of ionic character, right? What is the order of melting point? Melting point is directly proportional to ionic character. So more ionic character means more melting point. So melting point of BaCl2 will be maximum. Melting point of BaCl2 will be maximum, right? Just one more application over. This is one more application. I hope this is clear. Similarly, let's talk about thermal stability. Thermal stability. Again, remember one thing, thermal stability of ionic compounds will be more than that of thermal stability of covalent compounds. Thermal stability of ionic compounds will be more than that of thermal stability of ionic compounds. Or you can say thermal stability is directly proportional to ionic character, inversely proportional to covalent character. In short, thermal stability is directly proportional to ionic character, inversely proportional to covalent character. Now you should be in a position to answer this question as well. You have got Li2CO3, lithium carbonate, sodium carbonate, potassium carbonate, rubidium carbonate, cesium carbonate. Perfect. Now, among all these, which one is thermally maximum stable? As I told you people, thermal stability of ionic compounds is more than that of covalent compounds. Or you can say thermal stability is directly proportional to ionic character, inversely proportional to covalent character. Inversely proportional to covalent character. Now tell me one thing. Everywhere the anion is same. Carbonate ion, CO3 dinegative, CO3 dinegative, CO3 dinegative, CO3 dinegative. So I'm not going to decide on the basis of carbonate anion. No. Decide on the basis of cation now. Li positive, Na positive, K positive, Rb positive, Cs positive. Charge on every cation is same. So talk in terms of size. Lesser the size of cation, more is its polarizing power. More the polarizing power of cation, more is going to be the covalent character. So Li2CO3 will show maximum covalent character, followed by Na2CO3, followed by K2CO3, followed by Rb2CO3, followed by CS2CO3. This is the covalent character order. What will be the order of ionic character? Ionic character order will be reverse. This is the order of ionic character, right? And as I told you, your thermal stability is directly proportional to ionic character. More the ionic character, more the thermal stability. So this is the order of thermal stability as well. Okay? Tell me all of this is clear to you or not. So these were the Fazan's rules. I believe all of this stuff is clear. Let me quickly summarize whatever I have told you in Fazan's rules. I'm going to summarize it on one slide so that you are going to remember it from now onwards. Let me quickly summarize it. See guys, the first point I told you, covalent character is directly proportional to polarization. Polarization means distortion of electron cloud of anion. Second, polarization depends on polarizing power of cation, and polarization is directly proportional to the polarizability of anion. Correct? Third, polarizing power of cation is directly proportional to charge on cation, inversely proportional to size of cation. Polarizability of anion is also directly proportional to charge on anion and also directly proportional to size of anion. Right? Also directly proportional to size of anion. Covalent character is inversely proportional to ionic character. Generally, solubility of ionic compounds is more than that of solubility of covalent compounds in polar solvents. Or I can say solubility is directly proportional to ionic character, inversely proportional to covalent character. Seventh, melting point of ionic compounds will be more than that of melting point of covalent compounds. Or you can say melting point is directly proportional to ionic character, inversely proportional to covalent character. Similarly, talking about thermal stability of ionic compounds will be more than that of thermal stability of covalent compounds. Or I can say thermal stability is directly proportional to ionic character, inversely proportional to covalent character. This is the net summary of Fazan's rules. This is something which you can remember, and no question you'll be doing wrong here. Remember this particular chart. People all clear till here? Quickly in the chats. All clear, everybody. All clear. Everyone in the chats. Is every single thing clear? Quickly. Let me know. Let me know quickly in the chats. I hope this is clear, right? Perfect. So people, now we are going to enter into one more part of the chapter, that is one more topic, that is dipole moment. Okay, that is dipole moment. And once we are done with dipole moment, then we'll be taking a dinner break. Yeah. Sir, we are writing. Please give some time to write. Are you writing stuff? Oh my God, lot of things have to be covered. Should we move on now? give me some fire emojis in the chats first. Then we'll kill this dipole moment too. It is simple. It is simple, guys. I want that fire in the chats again. That particular compound which upon heating does not break down quickly, we say that compound is thermally stable. The ones who are asking me about thermal stability. Okay. Perfect, guys. So let's move on to something called as dipole moment. How do we define the dipole moment? First of all, what is a dipole? What is a dipole? See, guys. What is a dipole? Whenever you see the oppositely charged, whenever you see opposite charges separated by some distance. Whenever you see opposite charges separated by some distance. Let me tell you, the system of opposite charges separated by certain distance. What do we call it? We call it as dipole. System of opposite charges separated by certain distance. We call it as dipole, right? For the dipole, my dear students, what do we define? We define its moment. For the dipole, we define its moment, dipole moment, which is represented by mu, right? Which is represented by mu. Perfect. What is this dipole moment? This dipole moment is basically charge Q multiplied by distance between them. And this dipole moment, which is basically the product of charge and distance, it is a vector quantity. It's a vector quantity whose its unit is d by. Its unit is d by. Since it's a vector quantity, so it will be having a direction as well. The direction of dipole moment in chemistry, is taken from positive to negative. Or you can say less electronegative element to more electronegative element. Or you can say less electron density to more electron density. Less electron density to more electron density. Let's say you have got positive and negative separated by certain distance. The system of charges here I'm calling as dipole. For the dipole, we calculate its moment. The direction of dipole moment is from positive to negative. So the direction of dipole moment here will be from positive to negative. For example, let's say you have got HCl molecule. You know, chlorine is more electronegative than hydrogen. If chlorine is more electronegative than hydrogen, chlorine will be attracting this electron pair towards itself. So chlorine will show delta negative, hydrogen will show delta positive. Do you see oppositely charged species separated by certain distance? Yes. So you'll be calling it as a dipole. If it is a dipole, it will be having its moment. The direction of dipole moment is from positive to negative. It is from positive to negative. Okay, it's from positive to negative. Next point. Lone pair also contributes. Lone pair also contributes towards the dipole moment. Lone pair also contributes towards the dipole moment. And the direction of dipole moment, the direction of moment due to lone pair is towards the lone pair. Is towards the lone pair. For example, let's say I've got NH3. N, this is H, this is H, this is H. And nitrogen has got, for example, one lone pair. Here, this is the lone pair. My dear students, as I've told you, this lone pair over here, it also contributes towards the moment. And the moment due to lone pair is always towards the lone pair. This is the direction of moment due to lone pair. What is the direction of moment due to this bond? NH. Nitrogen is more electronegative. If nitrogen is more electronegative, nitrogen carries delta negative to delta positive. So moment due to this bond is in this direction, positive to negative. Here, positive to negative. Here, positive to negative. So these are all the moments which I've shown you over here. Okay? These are all the moments which I've shown you over. Perfect? Right? So remember dipole moment, lone pair also contributes towards the moment, right? Its direction is towards the lone pair. Now one more point, after that we'll see how exactly all of this is used. One more thing I'm going to tell you now. What is that one more thing? My dear students, that molecule whose net dipole moment is 0, you call that molecule as a non-polar molecule. That molecule whose net dipole moment is non-zero, you call that as the polar molecule. You call that as the polar molecule. Okay? You call that as the polar molecule. You call that as the polar molecule. For example, have a look. Understand what I'm going to say. Let's say we have got BeF2. This is how your BeF2 looks like. Now tell me, among beryllium and fluorine, which one is more electronegative? Fluorine. So this electron pair will be towards fluorine, right? So fluorine will get delta negative, beryllium gets delta positive. Similarly, due to this bond, fluorine delta negative, beryllium delta positive. How many dipole moments you got here? This is one dipole and this one more dipole. If you got two dipoles here, the direction of moment due to this dipole here is positive towards negative, due to this dipole, positive towards negative. Do you see you have got two equal moments? Equal and opposite moments? If you have got equal and opposite moments, they'll cancel out. I would say net dipole moment or BF2 is 0. If net dipole moment is 0, I would call this overall molecule as a non-polar. No doubt, the bonds are polar. Bonds are polar, but overall molecule is non-polar. Overall molecule is non-polar. Believe I'm clear with this. For example, you have got carbon dioxide. Let's say you have got carbon dioxide. Okay. Oxygen, carbon. More electronegative is oxygen, so delta negative. This is delta positive. Carbon, oxygen. Delta negative, delta positive. So how many dipoles did you get over here? This is one positive negative dipole. This is one more positive negative dipole. Two moments we go. Two dipoles we have. The direction of moment due to this dipole is from positive negative. Here also, it's from positive negative. Equal and opposite cancels out. Net dipole moment, 0. If net dipole moment is 0, the molecule overall is to be called as non-polar molecule. It's a non-polar molecule. Right? It's a non-polar molecule. Perfect? Yeah, it's a non-polar molecule. So basically that particular molecule whose net dipole moment will be 0, non-polar. That particular molecule whose net dipole moment will be non-zero, that will be polar. Tell me about this particular one. Tell me about HCl. Is HCl going to be polar or non-polar? In the chats quickly. Is HCl going to be polar or non-polar? Is HCl going to be polar or non-polar? This will be positive, this will be negative, right? So positive to negative. So its net dipole moment will be non-zero. This molecule will be polar in nature. This molecule will be polar in nature, right? Yeah, it will be polar. Now, my dear students, there are few molecules which I want all of you to remember. There are few molecules which I want all of you to remember. Those molecules I'll be discussing in some time, but I would want you guys to remember those molecules for now. Whenever you see a molecule, whenever you see a molecule whose central atom, number 1, does not have any lone pair. Central atom, number 1, does not have any lone pair. Molecule in which the central atom does not have any lone pair, number 1. Number 2, all the terminal atoms are same. All the surrounding atoms are same. All the terminal atoms, surrounding atoms should be same. Molecule should have regular geometry. Molecule should have regular geometry. Remember, all those molecules wherein the central atom does not have any lone pair, all the terminal atoms same, the molecule has regular geometry. Remember, this particular molecule will be always having the net dipole moment of 0. That means this molecule is going to be non-polar in nature. That molecule which will be following this particular criteria, remember it. Number 1. Number 2, whenever you see molecule of the type AB2L0, what is AB2L0? I'll let you know after some time. But first of all, you remember it. Whenever you see the molecule of the type AB2L0, molecule of the type AB3L0, a molecule of the type AB4L0, molecule of the type AB5L0, molecule of the type AB6L0, molecule of the type AB7L0, molecule of the type AB4L2, molecule of the type AB2L3, right? All these types of the molecules, let me tell you, their net dipole moment is going to be 0, and these molecules are going to be non-polar in nature. These molecules are going to be non-polar in nature. Remember this category, this is important. Remember this category of molecules which is always non-polar. Okay, which is always non-polar. Okay. Now guys, let's try to use all this stuff in the questions. Okay, let's try to use all this stuff in the questions. First of all, tell me the answer of this particular question. Or before doing the questions, there is one more thing which I would want you guys to write over here. One more thing. My dear students, as I told you, your dipole moment, it is the product of charge and distance. It's the product of charge and distance. Okay? More the charge on the atoms, more the dipole moment. Now, how can charge on atoms be more? Remember, if more is the electronegativity difference, more the electronegativity difference between the atoms, more are going to be the charges on the atom. More charges on the atoms means more dipole moment. So simply remember this particular statement. More the electronegativity difference between the atoms, more is going to be dipole moment. More is going to be the dipole moment. Remember this particular point as well, right? Remember this particular point as well. More electronegativity difference, more the dipole moment. Okay, perfect. At the same time, one more thing. Dipole moment is directly proportional to A as well. So, what does it mean? It means more the distance between the atoms, more the distance between the atoms, more has to be the dipole moment. More has to be the dipole moment. More the distance between the atoms, more the dipole moment. More the value of Q, more the dipole moment. Okay, this is one more point which I would want you guys to remember over here. Okay. Perfectly clear till here? Perfectly clear till here? Perfectly clear till here, people? Say yes or no once in the chats quickly. Now, as I told you, the moments, the bond moments, which we see from positive to negative, they're all vectors basically. They're all vectors basically. Okay, they're all vectors over here. And vectors follow the vector addition, vector subtraction, right? Vectors follow vector addition, vector subtraction. You know that. Perfect. You know that. See guys, for example, you have got a molecule which has got one of the moment in this direction and one moment in this direction. Okay, this is mu1, this is mu2 at an angle of theta. These are technically the vectors. So, what will be the resultant of these vectors? Resultant of these vectors will be under root of mu1 square plus mu2 square plus twice mu1 mu2 cos theta. Twice mu1 mu2 cos theta. Perfect. Twice mu1 mu2 cos theta. Or let's not remember all this stuff. This will be of no use to us. Let's remember in short like this. Lesser the angle between the two vectors, lesser the angle between the two vectors, lesser this angle between the two vectors, more is going to be the resultant. More resultant means more is going to be the net dipole moment. More is going to be the net dipole moment. Right? More is going to be the net dipole moment. For example, let me give you certain scenarios. Let's say you have got one bond moment in this direction, one bond moment in this direction. Let's say this is theta 1 here. Let's say one moment. This is theta 2 here. Similarly, for example, one moment in this direction, one moment in this direction. This is theta 3 here. Can you let me know where will be the net moment maximum? Where is the net moment maximum? In case 1, case 2, case 3, quickly. Case 1, case 2, case 3. Net moment will be maximum in 1, followed by 2, followed by 3. So simple. Smaller the angle between two vectors, more the result. More the result. Right? More the result. Correct? More the result. Correct, people? Right? Now I'm going to solve some questions so that you'll understand all of this. Let's start with this particular question. HF, HCl, HBr, HI. Right? We know more the electronegativity difference, more the dipole moment. So where do you see electronegativity difference more? In HF or HI? In case of H and F, electronegativity difference is more. It's more dipole moment. Done? This is the order of dipole moment. Yeah? Now, look at this one. PCl. Chlorine is more electronegative than carbon. So delta positive, delta negative. So bond moment in this direction. Similarly, positive, negative. Bond moment in this direction. One moment, one more moment. Both the vectors are in the same direction. So this is, for example, the resultant. Resultant is going in this direction. This is the resultant of the two vectors, for example. Now similarly, positive to negative cancels out. Net dipole moment is 0. So among these two, where is the dipole moment more? Here you have got more dipole moment. NH3, NF3. NH3, NF3. Okay. See, for example, I'm making NH3. This is your NH3. This is your NF3. First of all, the direction of moment due to the lone pair is towards the lone pair. Here also it's towards the lone pair. Nitrogen, hydrogen, which one is more electronegative? Nitrogen. So delta negative, delta positive. Due to this bond, in this way. Due to this bond, in this way. Due to this bond, in this way. Right? Similarly, nitrogen, fluorine, which one is more electronegative? From less electronegative to more electronegative. From less to more. From less to more. Look at all these moments. Look at all these moments. They are converging in one direction. Well, over here, if you see, some are going down, some are going up. Can I say over here in this particular case, there will be some cancellations? Because one is going up, one is going down. There will be some cancellations here. Over here, there are no cancellations. Here, there are cancellations. So net dipole moment in the first case will be more than that of net dipole moment in the second case. Right? So here, in case of NH3, I would say net dipole moment of NH3 will be more than that of NF3. Because in case of NH3, there are certain, in case of NF3, some cancellations of the vectors is happening. In the first case, there is no cancellation of vectors happening. I hope you are getting all this. So NH3 has got more dipole moment than that of NF3. Okay. This is one example which you have to focus more on. Okay. See guys, this is CH3F. The bond is between CF here. Okay. Here the bond is between CCl. Here the bond is between CH3Br. CBr. C and Br. And then at the end, bond is between Ci. Okay. My dear students, calling this as number 1, calling this as number 2, calling this as number 3, calling this as number 4. Okay. You know, dipole moment depends on two factors, charge and distance. More the charge, more the dipole moment. More the charge, more the dipole moment. Perfect. So what will be the dipole moment order? Because of charge factor. The charge factor is saying that more the electronegativity difference, more the dipole moment. So this has to be the order of dipole moment as per charge. As per charge. Or let's just compare 1 and 2. This is the order of the dipole moment as per charge. What is the order of dipole moment as per distance factor here? CCl bond length is more. If CCl bond length is more than that of CF, that means dipole moment of second here should be more than that of first as per distance factor. As per charge factor, this has to be the order. As per distance factor, this has to be the order. Remember, in case of this particular species, in case of this particular case, in particular, remember it. Distance factor dominates over the charge factor. Dominates over the charge factor. So people, if the distance factor dominates over the charge factor, so your net dipole moment order will be as per distance, right? So the correct order is going to be 2 greater than 1, then 3, then 4. This is the order of the dipole moment in this particular case. H2O, H2S, more the electronegativity difference. Here the bond is between O and H. Here the bond is between H and S. More electronegativity difference, more the dipole moment. More electronegativity difference, more the dipole moment. More electronegativity difference, more the dipole moment. In short. Right? Right, people? Remember this particular case as well. Now, look at these examples. Look at these examples. My dear students, do you know about CH3 group? This is something which you will study in GOC. I believe this is something basics which all of you must be knowing already. CH3 is electron donating. CH3 is electron donating. Nitro is withdrawing, electron withdrawing. See, this is donating. If this is donating, this gets delta positive, for example, this gets delta negative, just to make you understand. So, positive to negative. One vector is in this way. Similarly, electron donating. So, positive to negative. One more vector in this way. So in the first case, you have got one vector pointing downwards, one vector pointing upwards. Equal and opposite vectors, right? So net dipole moment here is going to be 0. Net dipole moment here will be 0. In this case, positive to negative, or you can say less electron density to more electron density, right? So one vector is going downwards, another vector is in this particular direction, and this is the angle between them. Let's call this as theta1. Similarly, positive to negative, positive to negative. So one vector pointing downwards and one vector pointing in this direction. Let's call this as theta2. Let's call this as theta2. Lesser the angle between the two vectors, more the resultant. Simple. Lesser the angle between the two vectors, more the resultant, right? So resultant will be maximum in the third case, followed by second. First one, it is 0 only. So 3 to 1 is the order of the dipole moment, right? 3 to 1 is the order of the dipole moment. Look at the next one. Look at this particular species. This is donating, this is withdrawing. If this is donating, it will donate. If it is donating, delta positive, delta negative, right? Delta positive, delta negative. So this way, it is electron withdrawing. When it withdraws the electrons, this gets delta negative, this gets delta positive, positive to negative. So one moment downward direction, one moment in this direction. Okay. Similarly, this is donating, positive, negative, positive, negative. This is withdrawing, positive to negative. So one in this direction, one in this direction. Okay. Let's call this as theta1. Let's call this as theta2. Look at this one. Positive to negative, positive to negative. What is the angle between these two vectors? One angle is 0, right? Angle is 0 here. Theta3 is 0. So tell me just the answer of this question. You should be in a position to answer this at least. Lesser the angle, more the resultant. So third, followed by 2, followed by 1. I hope I'm clear with this. I hope I am clear with this. Now, tell me the answer of this question. Which has maximum dipole moment? Which has maximum dipole moment among these 4 species? See guys, less electronegative to more electronegative. This is one moment. Less to more, less to more. Perfect. Since all these are same, CF, CF, CF. So let's call this moment as X. Let's call this moment as X. Let's call this moment as X. Right? Now, this particular moment and this particular moment, they are at an angle of what? This one, and this one. They are at an angle of 120. If they are at an angle of 120, if they are at an angle of 120, your vector says that the resultant will be in this direction. The resultant will be in this direction, which will be X only, right? So the resultant of this one and this one will be in this direction, which will be X. So X plus, already there was one X here. So X plus X makes it 2X. So 2X is the magnitude of net dipole moment here. 2X is the magnitude of net dipole moment here. Look at the next one. Less to more. Less electronegative to more. Less electronegative to more. Perfect. Now these two, if this is X, this moment is X, this moment is X. Now these two are at an angle of what? These two are at an angle of 120. So their resultant will be in this direction, which will be also X. So X and this X gets cancelled out. So its net dipole moment is 0. Net dipole moment of this molecule is 0. Right? Look at the next one. Less electronegative to more electronegative. Right? Less to more. Less to more. If this is X, this is X, this is X. And this X, they'll get cancelled out. So resultant is X in this direction. Less to more. Less to more. Equal and opposite, net is 0. So tell me, which one has got maximum dipole moment among all? First one has got maximum dipole moment. 1, 3, and these two have same dipole moment. 2 and 4 are same. So order is going to be, if this is 1, if this was, let's say 2, if this was, for example, 3, and this was the 4th molecule, I would say first one has got maximum dipole moment, followed by 3, followed by 2, and 4 have got same dipole moment. I believe I'm clear with this. Now, before solving the questions, few more questions. My dear students, tell me, what will be the net dipole moment of this molecule? Net dipole moment of this molecule. TCl, less electronegative to more electronegative. Less to more. Equal and opposite. Net dipole moment has to be 0. Net dipole moment is 0. Okay. Now, what about this one? OH, OH. OH from the top, OH from the bottom. Don't think OH from the top, OH from the bottom, it cancels out. Don't think its net dipole moment is 0. Let me tell you, its net dipole moment is non-zero. Because the orientation of OH group here is somewhat in such a way that the two moments, they do not cancel out. The two moments, they do not cancel out because of the orientation of this hydrogen and hydrogen here. Okay, be careful with this one. Okay, so net dipole moment of this is not going to be 0. You can remember it like this. See, from less electronegative to more electronegative. Less to more. Are they cancelling out? I don't think so. Just to make you understand. In short, the H group orientation at top and bottom is in such a way that their moments do not get cancelled out. Okay, so net dipole moment of this particular molecule is non-zero. Now guys, tell me the answer of this particular question. NEET 2020. Tell me, which of the following set of molecules will have zero dipole moment? Zero dipole moment. BF3. 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 Its net dipole moment will be? Today, teachers also assembled here. Who is the teacher here watching us? Tell me the answer of this question quick, people. Quick, 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 quick. Quick, people, everybody in the chats. What is the order? Which of the following set of molecules will have? See guys, if you look at this particular HF does not have zero dipole moment. So this set of molecule is not the answer. BF3, its net dipole moment is 0. It will be of the type AB3L0, right? This will be AB2L0. 1,3-dichlorobenzene we studied a few minutes back only, right? So first cannot be the answer. NF3, its net dipole moment is 0. Sorry, its net dipole moment is non-zero. So it cannot be the answer. BF3, 0. BEF2, 0. Carbon dioxide, 0. 1,4-dichlorobenzene, 0. Yes, this is the answer. Right? This is the answer. Yeah, done? Done, people? Are we done with this? Now we are going to shift towards the theories, right? Now, people, we are going to start with valence bond theory. Then comes hybridization, VSEPR, MOT, bond parameters, hydrogen bonding. This is the sequence of the things which we have to do now, right? Perfect, guys. So let's start with the valence bond theory. My dear students, what this valence bond theory exactly is all about. What kind of information this theory gives us. This is something very important, okay? Try to understand it very carefully. First of all, let me tell you, valence bond theory, it explains the formation of covalent bond. So this theory exactly is going to tell us how a covalent bond actually is formed. Till now, we have discussed about the Lewis theory. Lewis theory said a covalent bond is formed by the mutual sharing of electrons, right? Now, this valence bond theory is going to give us the exact idea about how a covalent bond is formed. So, first of all, it deals with the explanation of the formation of the covalent bond. How a covalent bond is formed, right? That is to be explained by valence bond theory. And my dear students, there are few postulates of this particular theory which you need to know first of all. My dear students, as per this particular theory is concerned, a covalent bond is formed by the overlap of atomic orbitals of the bonding atoms. A covalent bond is formed by the overlap of atomic orbitals of the bonding atoms. What does that mean? I'll let you know in some time. Number 2, in order to show the overlap, the bonding atoms must come close such that their orbitals can overlap. So over here, as you can see, a term is frequently coming. What is the term? Overlap. So let's first of all get to know what this overlap is all about. Then I'll make you understand about these 2 points. But dear students, what is overlapping? What is overlapping? I told you, as per VBT, covalent bond is formed by the overlap of atomic orbitals of the bonding atoms. Now, what is meant by overlapping? Overlapping is defined as the penetration of atomic orbitals. The penetration of atomic orbitals of bonding atoms into each other. What does that mean? Let's have a look. Let's say I have got, this is one of the atomic orbitals of some atom. Let's say this is one of the atomic orbitals of some atom. Let's say this is one more atomic orbitals of one more atom. I've taken 2 atomic orbitals of 2 atoms over here, right? My dear students, what is meant by the penetration? What is meant by overlapping of atomic orbitals? Let's say this is one of the atomic orbital of one atom. This is one more atomic orbital of one more atom, right? This is the nucleus and this is its electron density. This is its electron density, right? This is its electron density. Similarly, this is the nucleus and this is the electron density of this atomic orbital. Now what VBT says that a covalent bond is formed by the overlapping of atomic orbitals into each other. Now overlapping means what? Overlapping means penetration of atomic orbitals into each other. My dear students, in order to show the overlap, first of all, these atomic orbitals, they should come close. When they come close, there will be a scenario when these atomic orbitals will overlap. When these atomic orbitals will overlap. Overlapping means what? Penetration of atomic orbitals into each other. Do you see? Over here, I took 2 atomic orbitals of 2 bonding atoms. Now imagine these bonding atoms are coming close. If bonding atoms are coming close, that means their atomic orbitals are coming close. Now, when the atomic orbitals will be coming close, there will be a scenario when these atomic orbitals will merge into each other. And this merging of electron clouds, these merging of atomic orbitals, these merging of electron clouds into each other is something which we call as overlapping. So what is overlap? What is overlap? Overlap means penetration, merging of electron clouds into each other, merging of atomic orbitals into each other. That is something which we call as overlapping, right? And as per your valence bond theory is concerned, due to overlapping, which bond gets formed? Due to overlapping, covalent bond gets formed. Covalent bond is formed, right? Now, my dear students, let's get back to the business. Let's understand these 2 points. VBT. As per VBT, a covalent bond is formed. A covalent bond is formed by the overlapping of atomic orbitals of bonding atoms into each other, right? And my dear students, in order to show the overlap, the bonding atoms must come close. And when the bonding atoms come close, their atomic orbitals will be coming close. And there will be a scenario when these atomic orbitals will merge into each other. That merging of electron clouds into each other is something which you call as overlapping. Due to overlapping, covalent bond is formed. Right? Due to overlapping, covalent bond is formed. Perfect. Now, my dear students, since we got to know, due to the overlapping of atomic orbitals into each other, a covalent bond is formed. Yeah? A covalent bond is formed. Now, remember few things. Remember few things for now. I'll be explaining them one by one. Remember one thing, greater the extent of overlap, greater the extent of overlap, greater the merging of electron cloud into each other, stronger will be the covalent bond formed. Stronger will be the covalent bond formed. So the first point which you need to know, strength of a covalent bond is directly proportional to what? It is directly proportional to extent of overlap. More the overlap between the atomic orbitals of the bonding atoms, right? More is going to be the strength of the bond. Okay, more is going to be the strength of the bond. This is something which I'll explain further more in detail in some time. Okay, before that, one more thing. My dear students, when overlapping takes place, when atomic orbitals of bonding atoms merge into each other, what happens after that? Say, for example, this is atomic orbital of one atom. This is atomic orbital of one more atom. Let's say these two atoms are basically the bonding atoms which have to form a bond in between. So what they need to do, in order to show the overlapping, these atomic orbitals must come close. The bonding atoms must come close. When bonding atoms will be coming closer, their atomic orbitals will be coming closer. As a result, these atomic orbitals will merge into each other. This merging of electron clouds into each other is something which you call as overlapping. Due to overlapping, a covalent bond gets formed. Now, my dear students, this common electron cloud over here, this common electron density over here, let me tell you, this common electron density, it is going to arrange itself in such a way, this common electron density, it is going to arrange itself in such a way that it should come under the influence of both these nuclei. The common electron density, the merged electron density, the merged electron density, it will arrange itself in such a way that it comes under the influence of both the nuclei. So finally, you'll show it like this. Finally, you'll show it like this. This is one of the nuclei. This is one more nucleus, right? And this is the common electron density. So you can say the common electron density has arranged itself in such a way that now it is under the influence of both the nuclei, right? It is under the influence of both the nuclei. Okay, so let's quickly recap it. VBT explains the formation of covalent bond. As per VBT, atomic orbitals of bonding atoms, they should overlap, right? What is overlapping? Overlapping means merging of electron clouds into each other. In order to show overlap, I would say bonding atoms must come close, due to which their atomic orbitals will come close. Therefore, a stage will come when these atomic orbitals will merge into each other. And merging of electron clouds into each other is what you call as overlap. Due to overlapping, covalent bond gets formed. Greater the extent of overlap, stronger is going to be the covalent bond. Now, once this merging is done, once this overlapping is done, the common electron density will arrange itself in such a way that it should come under the influence of both the nuclei, right? It should come under the influence of both the nuclei, just to avoid the repulsions between these two nuclei, right? Just to avoid the repulsions between these two nuclei. Now, let's get into the details of this. Let's get in the details of this. My dear students, a covalent bond is formed by the overlapping of atomic orbitals into each other. Now, how many types of overlap do we have? What are the different types of overlaps? Okay, what are the different types of overlaps? The first type of overlap is what you call as axial overlap. And the second type of overlap, which we have to discuss in detail, right? You call that as a parallel overlap. In case of axial overlap, what happens basically? I would say, in case of axial overlap, overlapping takes place, overlapping of atomic orbitals, it takes place along the axes. It takes place along the axes. Along the axes. Along the axes overlapping takes place. And whenever overlapping between the atomic orbitals takes place along the axes, that overlapping is something which you call as axial overlapping. Axial overlapping leads to the formation of covalent bond. Which type of covalent bond? You call that covalent bond as the sigma bond. Either you call it as the axial overlapping, or you can call it directly as the head-on overlapping. You can call it as the head-on overlapping. Due to head-on overlap, which covalent bond gets formed? It is a sigma bond that gets formed due to the axial overlapping, right? Overlapping along the axes. Along the axes. Both the orbitals will come along the axes. They'll penetrate into each other, right? And that penetration is what you call as overlapping. Which type of overlapping? It is going to be the axial overlapping. Axial overlapping always leads to the formation of sigma bond. Okay? Now, what happens in parallel overlapping? My dear students, in parallel overlapping, what I can say, I would say, in case of parallel overlapping, I would say in parallel overlapping, overlapping takes place overlapping takes place by keeping the axes parallel. What does that mean? You'll get the idea in some time, right? For example, imagine this one of the p orbital. Imagine this one of the p orbital. This is head-on overlap, overlapping along the axis. Now, if this is one p orbital, if they are going to overlap like this, by keeping their axes parallel, you call this as the parallel overlapping, or you can call this as sideways overlapping. Sideways overlap. And let me tell you, this parallel overlapping, this sideways overlapping, it leads to the formation of covalent bond. Which covalent bond? You call that as pi bond. So either pi bond gets formed or delta bond gets formed due to parallel overlapping. Either pi bond gets formed or delta bond gets formed due to parallel overlap. Now let's get into the details of axial overlapping and parallel overlapping, right? Let's get into the details. My dear students, let's first start with the axial overlapping. When the atomic orbitals overlap along their axes, it leads to the formation of sigma bond. That's something I told you. Now let's try to understand this axial overlapping in detail. Okay. In order to understand the axial overlapping, I'm going to take the first case over here. What we call that as? We call that as SS overlap. We call that as the SS overlap. SS overlap. Okay. First of all, my dear students, imagine that this is your internuclear axis, which generally is taken as Z axis. I'm calling this as Z axis over here. Let's call this as Z axis, right? Let's call this as Z axis. This is your Z axis over here. Now, for example, S orbital of one atom plus S orbital of one more bonding atom. Okay? This is S orbital of an atom. This is S orbital of one more bonding atom. Now, what they are going to do? They have to show axial overlapping. Axial overlapping means head-on overlapping. So they'll come closer. When they are going to come closer, what's going to happen? When they are going to come closer, let me tell you, this is the nucleus of it. This is the nucleus of it. When they are going to come closer, they will their atomic orbitals will merge into each other like this. Their atomic orbitals will merge into each other, right? And this merging of atomic orbitals into each other is what you call as overlap. Due to overlap. Which type of overlap? First of all, this is head-on overlap. This is head-on overlap, right? This is what I call as axial overlap. Overlap along the axis. Due to axial overlap, which bond gets formed? I would say it is the sigma bond that would have got formed over here. Now, my dear students, you know, this electron density, this common electron density, it's going to arrange itself in such a way that it comes under the influence of both the nuclei. It comes under the influence of both the nuclei. So, final shape, you are going to represent it like this. Let's say this was one nuclei, this is one more nucleus, right? And this is the common electron density, which is under the influence of both the nuclei. So which bond has got formed over here? Since it was the axial overlap leads to the formation of sigma bond. Perfect. Right, people? So this is your SS overlap, SS head-on overlap, which leads to the formation of sigma bond. Okay? Is it clear till here, people? Is it clear? Let me tell you one more thing. SS overlap, see, basically, there are two types of overlaps. Let me tell you. There are two types of overlaps. Let me tell you. Right? Two types of overlaps. One is called as your positive overlap. One is called your negative overlap. Positive overlap. Negative overlap. And let me tell you, positive overlap leads to the bond formation. Positive overlap leads to the bond formation. Negative overlap does not lead to the bond formation. Negative overlap does not lead to the bond formation. How exactly can we say whether positive overlap has happened or negative overlap has happened? That's something which I'll tell you in some time. Wait for that. But one thing which you are going to remember over here, whenever you have SS overlapping always, in case of S and S, it always shows positive overlap. SS head-on overlap is always positive. It is not negative in nature. Technically, there are two types of overlaps: positive overlaps, negative overlaps. Positive overlaps lead to the formation of bonds. Negative overlaps, they do not lead to the formation of bonds. Remember, SS overlapping is always positive. SS overlapping is always positive, right? What is negative overlapping? I'll let you know in some time, right? Okay, so this was your first step of overlap, which is what you call as SS overlap. Now, my dear students, let's talk about the second axial overlap. That is your SP overlap. SP overlap. Which type of overlap I'm showing you right now? I'm showing you axial overlap. This is the second type of axial overlap, right? So, what is going to happen over here? What's going to happen over here? Let's try to understand. Let's try to understand, guys. Let's try to understand. See, in case of SP overlap, what's going to happen? I would say one of the s orbital of one bonding atom and p orbital of one more bonding atom. If this is the z-axis, which I'm considering as the internuclear axis, right? This is the s orbital of one atom. And similarly, this is, for example, your pz. This is pz orbital of one more bonding atom. Perfect. Now, over here, they are going to show the overlapping. Over here, they are going to show the overlapping, right? Is this overlap head-on overlap? Is this overlap the head-on overlap? Absolutely, this is the overlap which is happening along the axis. So it is the head-on overlap, axial overlap. Axial overlap leads to the formation of bond, sigma bond. Perfect. Now, I told you a few minutes back, there are basically two types of overlaps. There are two types of overlaps. One is positive, one is negative. Let me show it to you here only. One is positive, one is negative. So, if imagine this is the z-axis, right? Imagine this is the z-axis. This is your s orbital, and this is again your p orbital. Now, how do I show positive overlap and negative overlap? See, guys, positive and negative. Let me give this particular orbital as the sign positive. Let me give this, if this is positive, let me give this sign positive and let me give this sign negative. Well, these are not charges or something. These are the signs with the help of which I'm showing you which one is positive and which one is negative overlap. I'm giving this orbital the sign positive. This orbital I give the sign positive. I mean, this lobe I give the sign negative. Perfect. Now, do you see same sign on same side? Yes, same sign on same side. This overlap I'll be calling as positive overlap. Same sign, same side. Or you call it as the constructive interference, or leave constructive interference aside. See, this overlap you call either as positive overlap or you call it as the in-phase overlap. You call it as the in-phase overlap, right? Now, over here I have to show the negative overlap. For the negative overlap, I have to show opposite sign, same side. Let's say this is positive, so this has to be negative. This has to be positive. Opposite sign, same side. Opposite sign, same side. This is something which I call as negative overlap, or you call this as out of phase overlap. And negative overlap, out of phase overlap, it does not lead to the formation of bond. It is just the positive overlap leads to the formation of bond. So what is going to happen here? These two atomic orbitals, they are going to merge into each other. How exactly will be the scenario? This is S and this is P. They have merged into each other. They are merged into each other. And this is the common electron density. This is the common electron density. So, is this overlap along the axis? Yes, this is the penetration of atomic orbitals along the axis, and we call this as axial overlap. Axial overlap leads to the formation of sigma bond. So, I would say a sigma bond has got formed over here. So, this was your sp axial overlapping. This was your sp axial overlapping, right? The third one. The third one. Third one is your pp axial overlapping. I'm right now teaching you axial overlapping only, right? So, now I'm going to teach you PP overlap. PP axial overlap to be more precise. PP axial overlap, right? So, how do I show you PP axial overlap? Again here, I'm going to draw two lines. Just to make it clear for you. PP axial overlap, right? So, calling this as z-axis, which is my, for example, internuclear axis. Z-axis, I'm calling this as the internuclear axis. Now, imagine this is the p orbital of one atom. Imagine this is the p orbital of one atom. Now, they are going to show the axial overlapping, head-on overlapping. Now, as I told you, This overlapping can happen in two ways. Either it's going to be positive overlap or it's going to be negative overlap. How do I represent them? Just with the help of signs. If I'm giving positive sign to this lobe, negative to this lobe, I'll be giving positive to this lobe, negative to this lobe. Positive, positive, same sign on same side. So this is your positive overlap. This is your positive overlap, right? Or you call this as in phase overlap. In phase overlap. Similarly, if I'm giving this as positive, giving this as negative, now this is negative, this is positive. Opposite sign on same side. So I'm calling this as negative overlap. Negative overlap. Or you call this as out of phase overlap. Out of phase overlap. And out of phase overlap, negative overlap does not lead to the formation of bond, right? So only positive overlap leads to the formation of bond. So this is the positive overlap here, and this is axial in nature, right? And how it looks like finally. So this is one of the p orbital, let's say. This is, for example, one more p orbital, and over here you can see their lobes have merged into each other. So this is the example of the axial overlap, right? This is the example of the axial overlap. And axial overlap leads to the formation of which bond? Sigma bond. I would say sigma bond has got formed over here. As I told you, the common electron density is going to arrange itself in such a way that it should come under the influence of both the nuclei. This is the nucleus of this. This is the nucleus of this, right? Common electron density should be arranged in such a way that it should be under the influence of both the nuclei. This is nucleus, this is nucleus. Perfect. How it finally looks like. See. This is how it's finally going to look like. Understand, guys. This is nucleus, for example. One nucleus, this is one more nucleus. Perfect. This was carrying negative. Let me give this as a negative. This was carrying negative. Let me give this the negative. And let me give this a positive. In the middle, I'm giving this a positive. As you can see, the common electron density has arranged itself in such a way that it comes under the influence of both these nuclei over here. And which bond is formed here? I would say sigma bond has got formed. So this was your PP overlap, PP axial overlap, right? This was your PP axial overlap. Well, these charges, again, I'm telling you, these are not real charges, right? These are just the signs which I'm giving just to let you know whether positive overlap is happening or negative overlap is happening. I believe I'm clear with this. Yeah? People, is it clear till here? So this was PP axial overlap. Perfect. PP axial overlap. Now, guys, there is one more overlap. One was axial. Another one is sideway overlap or parallel overlap. What happens in parallel overlap? In parallel overlap, atomic orbitals combine. Atomic orbitals merge into each other by keeping their axes parallel. By keeping their axes parallel. The first type of parallel overlap over here, which I'm showing you, that is your PP parallel overlap. That is your PP parallel overlap. Understand what this PP parallel overlap is all about. Now, my dear students, imagine. Let's say this is p orbital. Let's say this is p orbital of one atom. Okay. Let's say this is p orbital of one more atom. If this is the internuclear axis, which you call as z-axis, right? Let's say this is your internuclear axis, z-axis. So calling this as y-axis, for example, calling this also as the y-axis. So this is your py atomic orbital. This is your py atomic orbital. Perfect. Now, my dear students, imagine these atomic orbitals are coming in this way, right? Their lobes will overlap. They'll penetrate into each other. Perfect. Now, first of all, as we know, there can be two possibilities, positive or negative. Let me give this as a positive sign. This also as the positive sign. Negative, negative. Same sign, same side. Same sign, same side. Positive overlap. Positive overlap. Positive overlap. Or you can call this as in-phase overlap, which leads to the formation of which bond over here. Since these atomic orbitals are overlapping by keeping their axes parallel. By keeping their axes parallel. So it will be like this. This is one of the p orbital. And similarly, this is one more p orbital. Perfect. This is the common electron density. This is the common electron density. This was the nucleus of one atom. This is the nucleus of one atom, right? This is the common electron density over here. So which type of overlap this is? This is the parallel overlap, and parallel overlap leads to the formation of over here the pi bond. And this pi bond which got formed over here I'll be calling this pi bond as the p pi bond. This is p pi p pi bond. Now, as I told you already, the common electron density is going to arrange itself in such a way. This is the common electron density. It is going to arrange itself in such a way that it should come under the influence of both these nuclei. It should come under the influence of both these nuclei. See guys, what I'll be doing over here. Understand how it finally looks like. Imagine this is one plane over here. Imagine this is a plane. This is a plane. I'm basically talking about this particular plane. This is the plane over here. Now, if this is the plane, on the top of the plane like this, and on the bottom of the plane like this, you'll find the electron density. So, on the top, on the top of the plane, and similarly, on the bottom of the plane, you are going to find the electron density. Perfect. On the top of the plane and the bottom of the plane, you are going to find the electron density. Let me give them signs as well. This was positive, positive, negative, negative. So positive, positive, I'll be giving this as the positive sign. This I'm giving as a negative sign, right? This was one of the nucleus of one atomic orbital, nucleus of one more atom, right? So these nucleuses will be here. These are the nuclei basically. Perfect. So my dear students, if I ask you one thing, on this particular plane, do you find any electron density? No, electron density is present above the plane and below the plane. Electron density is present above the plane and below the plane. On this plane, you won't find any electron density. So this particular plane which you got over here, on which there is no electron density, you'll be calling it as nodal plane. So how many nodal planes are there over here in this particular p pi bond? There is one nodal plane. This is something which I'll be calling as nodal plane here. Right? Right, people? Am I clear with this? Am I clear with this? So which type of overlap this was? This was in-phase overlap, positive overlap. Now, between P and P, there can be negative overlap as well, you know. There can be negative overlap as well. And how do I show negative overlap? I just have to interchange the signs. Let's say this was one py, one more py. Let's say this is positive, this is negative. Now this is negative, this is positive. Opposite sign on same side. Opposite sign on same side. What do I call this as? Negative overlap. Out of phase overlap, which does not lead to the bond formation. Perfect. So this was your PP parallel overlap, which leads to the formation of pi bond over here. Yeah. Now, the second type of parallel overlap is your, this was PP, right? Now it's going to be PD parallel overlap. PD parallel overlap. Just give me a second. See, this was your SS axial overlap, okay? Just to keep things a little more transparent for you, this was SS axial overlap. And then this was SP axial overlap, which leads to the formation of sigma. Then this was PP axial overlap. Okay, PP axial overlap. Over here, this was PP parallel overlap. Now I'm going to show you PD parallel overlap. So imagine this one of the p orbitals, giving this is positive and this negative, for example. This is p orbital of one atom. And imagine this is the d orbital of one more atom. Okay? Perfect. This is your z-axis, for example. Calling this as py, calling this as dxy. Okay, positive, negative. Let me give this positive, so this will get negative. If this is negative, just a second, guys. If this is negative, I'm giving this as negative, negative and positive, positive and negative. Perfect. Now they are going to overlap by keeping their axes parallel, right? So, which type of overlap? First of all, this is it in phase or out of phase? Same sign, same side. It is in phase, positive overlap. It is positive parallel overlap, right? And how do I show it at the end? This is p orbital, and these are the lobes of d orbitals which have penetrated into the p orbital. And this is the common electron density over here. Perfect. And what kind of overlap this was? Parallel overlap, which leads to the formation of pi bond. Which leads to the formation of pi bond. I hope I'm clear with this. This was PD parallel overlap. This was in phase overlap, positive overlap, in phase overlap. By chance, if you want to show the PD negative overlap, which does not lead to the formation of bond, let me just show it to you. PD negative overlap. How do you are going to represent it? For example, if this carries positive, this carries negative, then this should contain negative, this should be having positive. If this is positive, this is negative. If this is negative, this is positive. So, what kind of overlap this is going to be? This is going to be out of phase overlap or negative overlap, which does not lead to the formation of any bond. Okay, this was PD parallel overlapping. PD parallel overlapping. Negative overlap or out of phase overlap. Out of phase overlap. Now guys, the third category here is going to be your DD parallel overlap. DD parallel overlap. Okay, DD parallel overlap, or I'll be calling this as two-lobe interaction. I'll be calling this as two-lobe interaction. Two-lobe interaction. See guys, what it's all about. Let's say this is your one of the d orbital. I'm calling this as dxy, for example. Okay, here also, let's say I've got dxy. This is your dxy, for example, of one atom. This is dxy of one more atom. If I want to show the positive overlap, how do I show it? Let's call this as positive, right? So this is going to be negative. Let's call this as negative. This is going to be positive. So positive, positive, negative, 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 positive, positive, negative. Same sign, same side, right? So when these basically d orbitals will come by keeping their axes parallel, what is going to happen? These these lobes are going to merge into each other. Is it positive or negative? This is positive overlap, or what do they call this as? In phase overlap. Is this axial or parallel? It is parallel overlap basically. It is parallel overlap basically. It is parallel overlap basically. And this is the common electron density over here, which you can see. This is the common electron density over here, which you can see. And my dear students, if you look carefully, this is parallel overlapping, which leads to the formation of what? It leads to the formation of pi bond. Which pi bond do I call this as? This is the pi bond formed between two d orbitals. This is a d pi bond. D pi bond. Over here, I forgot to tell you, this was your p pi d pi bond. P and D. This pi bond was formed with a P and D. So I'll be calling this as P pi D pi bond over here. P pi D pi bond over here. Similarly, over here you can show the negative overlap as well. You just have to interchange the signs, right? You just have to show opposite signs on same side. You'll show the negative overlap. I believe that's clear. So this was your DD parallel overlap, or you can see this is two-lobe interaction, right? This is two-lobe interaction. Two lobes are interacting. Now, my dear students, there could have been one more possibility. There could have been one more possibility in DD parallel overlap. In DD parallel overlap, there could have been one more possibility, which is what you call as four-lobe interaction. Which is what you call as four-lobe interaction. And this four-lobe interaction, let me tell you, it leads to the formation of which bond? It leads to the formation of delta bond. It leads to the formation of which bond? Delta bond. See how. Let's say this was your one of the d orbitals. Let's call this as dxy. This is your dxy, for example, as well. In the earlier case, these orbitals interacted like this. These orbitals interacted like this. Now, these orbitals could have interacted in another way as well. Let's say this particular orbital is going to come on this side, so that there will be interaction between all the four lobes. That means this particular lobe will interact with this one. This particular lobe will interact with this one. And this one in particular lobe is going to interact with this one. And this particular lobe is going to interact with this one. Do you see how? Do you see how, people? So earlier, it was interaction between two lobes, here and here. Now imagine this atomic orbital you are taking over here. right? Just above it. This atomic orbital you're taking and keeping above the first one. When you are keeping it above the first one, there will be interaction between all the four lobes. And whenever this sort of overlapping happens, in which all the four lobes interact, the bond which gets formed is something which is known as delta bond. Am I clear with this? Am I clear with this? Let me know once in the chats, right? So delta bond is formed by the four lobe interaction. I hope I'm clear with this. Tell me the answer of these sort of questions, people. Tell me the answer of these sort of questions. See, the first question, S orbital, along any axis. If they come along x-axis, if they come along y-axis, if they come along z-axis, they always form which bond? They're always going to form the sigma bond. Right? Where did I write it? S orbitals along any axes will lead to the formation of what? Will lead to the formation of sigma bond. Perfect? They'll always lead to the formation of sigma bond. Number one. Why is that? For example, this is S and S. If this is z-axis, let's call this as z-axis. So over here, it's going to be sigma. Over here, it's going to be sigma. Now, for example, this is S and this is S. Let's call this as y-axis, right? So if they come like this, it's again going to be head-on only, so sigma. So if they come along z-axis, again it's going to be head-on overlap only, so sigma bond. Now S plus px. Quickly tell me, what is going to be S plus px? S plus px if internuclear axis is x-axis. So if this is your internuclear axis, which we are calling as x-axis here, right? So S plus px. This is S and this is your px. So it will lead to the formation of what? Sigma bond only. So here also a sigma bond gets formed. Sigma bond gets formed. S plus py, keeping the internuclear axis y-axis. So if internuclear axis is called as y-axis, if this is your internuclear axis, this is S and your py. This is your py. So again, it's going to be head-on overlap only. Head-on overlapping means sigma. So again, which bond gets formed here? In the third case, it's again going to be sigma bond. Now, S plus px along z-axis. If this is the z-axis, right? This is S and px. Px will be perpendicular to z. So this is your p. Do you see any overlap will happen here? There will be no overlap. There will be no overlap here in this case. No bond gets formed. Px plus px, keeping x-axis as the internuclear axis, px, it's going to give the sigma bond formation. Py along y-axis. So y-axis is the internuclear axis, py, it's again going to form what? Sigma bond. pz, keeping z-axis as the internuclear axis. Z-axis and internuclear axis, pz will form again the sigma bond only. Right? So let me show it to you quickly. Px along x-axis. So if x-axis is the internuclear axis, so this is your px, this is your px, sigma. Now you are keeping y-axis as the internuclear axis, py, again head-on sigma. Now if you are keeping z-axis as the internuclear axis, pz, again what? Sigma only. Again sigma only. Now py, keeping z-axis as the internuclear axis. If this is, for example, your z-axis, right? Now y-axis will be perpendicular. So let's call this as py, let's call this as py. It's going to be parallel overlapping, leads to the formation of what? Pi bond. Leads to the formation of pi bond. pz, keeping x-axis as the internuclear axis. Again which bond? Pi bond. Right? dxy and px, quickly in the charts. dxy and px in the charts. This one, and this one. You are going to think over them and let me know in the comments at the end. Which bond gets formed over here. And you should be in a position to think over them. dxy and px, keeping y as the internuclear axis. You should be in a position dxy plus px, keeping y as the internuclear axis. This is y, right? This is your dxy, dxy. This is your px. This is your px, right? Which bond here? Which bond here? It's going to be pi, right? dxy, py, by keeping x-axis as the internuclear. This is x-axis, which is the internuclear axis. Here you have got dxy, and this is your py. Perfect. Again what? Again pi. Again pi. So here was also pi, here was also pi. Now if you think over this, any axis, dxy plus z, dz plus pz, any axis. Now at least this is something which you will tell me in the comments. Okay, this one you will tell me in the comments. I hope I'm clear with this. I hope I am clear with this. I hope I'm clear with this. Am I? Quickly. Quickly in the chats, people. Quickly in the chats, yeah? So how many of you think there'll be no overlap here in the last? How many people are thinking that there'll be no overlap in the last? Think over it and let me know in the comment section at the end. Okay, let's not go there. All right, people. So I hope things are clear till here. Now, my dear students, as I told you already, strength of a bond, strength of the covalent bond is directly proportional to extent of overlap, right? That's something which I told you already. Strength of the bond is directly proportional to extent of overlap. More the extent of overlap, stronger the bond. Stronger the bond, right? That's one of the things which I told you long back. That's one of the things which I told you long back. My dear students, it has been observed that sigma bonds are stronger than pi bonds. Why? What is the logic? Sigma bonds, it has been observed that sigma bonds are stronger. Sigma bonds are stronger than what? Than pi bonds. What is the logic? What is the reason? There are two reasons which I'm going to tell you over here. There are two logics over here. First logic, we know already strength of bond is directly proportional to extent of overlap. Extent of overlap. Extent of overlap. The first reason is, my dear students, the first reason why it happens, why sigma bonds are stronger than pi bonds, extent of overlap in axial. Extent of overlap in axial is greater than that of extent of overlap in parallel. In parallel. More the extent of overlap, stronger the bond. Due to axial overlapping, sigma bond gets formed. Due to parallel overlapping, pi bond gets formed. So, extent of overlap here is more. That is the reason why sigma bonds are stronger than pi bonds. This is the first factor. This is the first way by means of which you can say why sigma bonds are stronger than pi bonds. The second thing, guys. Second thing. I can explain it with the help of energy factor as well. I can explain the same stuff with the help of energy factor as well. And how come you can explain this with the energy factor? Let's understand. See, energy factor is also going to decide the same. See how. For example, imagine this is the s orbital of one atom, s orbital of one more atom. Let's say this is the axial overlapping which I'm showing. Right? This is the axial overlapping. This is the nucleus of one, this is the nucleus of one. And at the end, the common electron density is going to arrange itself in such a way that it comes under the influence of both the nuclei. This is nucleus 1, this is nucleus 2, and here is the common electron density. So which overlapping this is? This is, for example, your axial overlapping. Now, let me show you the parallel overlapping. Let me show you the parallel overlapping, right? What happens in parallel overlapping? Understand. For example, this is one of the P and this one of the V. Let's say they have to show the parallel overlapping. So how do I show it at the end? At the end, if you look carefully, this used to be a nodal plane, right? There used to be electron density above it. There used to be electron density above it, and there used to be electron density below it. Something which we discussed already. Electron density above it and electron density below it, right? Now, this was nucleus of one, and this was nucleus of another one. Perfect. Now, guys, this overlap was your parallel overlap. This is your parallel overlap. Do you see in axial overlap between two nuclei, there is electron density? In parallel overlap between two nuclei, is there electron density? It's a nodal plane on which no electron density will be there. There is no electron density here. There is no electron density here. But there is electron density here between these two nuclei. So, when it comes to the axial overlap, this electron density will be between the nuclei. In case of parallel overlap, there is no electron density between the nuclei, right? So, I would say these two nuclei, they are in direct contact. So, there will be repulsions. If there are repulsions, energy of the system will increase. More the energy of the system, lesser the stability, right? Over here, this electron density, it creates a shield between the repulsions of these nuclei. It creates a shield between the two nuclei, right? So this electron density, this common electron density, it creates a shield between two nuclei, right? So that repulsions are minimized and stability is maximum. Repulsion is minimized and stability is maximum. More the stability means stronger the bond. Over here, which bond got formed? Sigma. Over here, which bond got formed? Pi bond. That is the reason sigma bonds are stronger, they are more stable as compared to pi bonds, which are comparatively less stable. In other words, I can say sigma bonds are stronger than that of your pi bonds. Am I clear? Am I clear, people? Yeah? So, by two ways, you can explain why sigma bonds are stronger than pi. Sigma is stronger than pi. Number one, extent of overlap. One reason. One more reason is going to be your energy factor, right? Over here, in case of sigma bond, there will be electron density in between the nuclei. There will be no electron density in between the nuclei, due to which repulsions will be more, energy will be more, stability will be less. Less stability means weaker the bond. Less stability means the bond is weaker. Here, this electron density, it creates a shield between two nuclei. So lesser repulsions, more stability means stronger the bond. So that's why sigma bond is stronger than that of your pi bond. Because when it comes to sigma bond, there will be less repulsions between the nuclei. In case of pi bonds, here you can say this is direct contact. Oh, right here. So I would say your sigma bonds are stronger. Perfect. So one of the two explanations you can remember out of the two. Perfect. Now guys, few more things which you need to know. Few more things which you need to remember. What are those things? Try to understand. Try to understand, people. Strength of sigma and pi bonds. Strength of sigma and pi bonds. There are few things which you need to remember directly, which will solve a lot of our things. Okay, which will solve a lot of our things. For the same energy shell, what is the extent of axial overlap? For the same energy shell, what is the extent of axial overlap? My dear students, imagine the shell number is same. Let's say the shell number is 2. So this will be 2s2s. This will be 2s2p overlap. This will be 2p2p overlap. I'm assuming all these overlaps, the axial overlaps. All these overlaps, the axial overlaps. Okay. For the same energy shell, remember pp axial overlap, its extent will be more than that of sp than that of ss. Similarly, let's say there is an overlap between 3s, 3s, there is an overlap between 3s, 3p, and there is overlap between 3p, 3p. And everywhere overlap is axial. If overlap is axial, extent of axial overlap in 3p, 3p will be more than that of 3s, 3p, which will be more than that of 3s, 3s. So for the same energy shell, pp axial overlap, its extent will be more. Its extent will be more. And more the extent of overlap, more the stronger the bond formed. So the bond which gets formed by 2p axial overlap will be stronger than the sigma bond which gets formed between sp axial overlap, than that of sigma bond which gets formed between 2s axial overlap. Remember this particular thing. Number one. Number two. if the orbitals are of different shells, then lower energy orbitals, they produce more effective overlap. If the orbitals are of different shells, see 1s and 2s, different shells, 1s and 1s, same shell. Okay, 1s and 1s, same shell. If orbitals are of different shells, as you can see over here, axial overlap is happening between 1s and 2s. Here, one more overlap is happening. One more axial overlapping is happening between 1s and 1s. Now, where is the extent of overlap more? Which one shows more effective overlap? The lower energy orbitals are going to show more effective overlap. So, overlap between 1s and 1s is going to be more effective than that of 1s and 2s. So, the sigma bond which gets formed here will be stronger than the sigma bond which gets formed here. Do you understand this? Similarly, let's say over here 2p, 3p axial overlap is happening. 2p, 2p axial overlapping is happening. If the orbitals are of different shells, the lower energy orbitals are going to produce the effective overlap. The lower energy orbitals are going to produce the effective overlap. So my dear students, imagine this is the axial overlap. This is also the axial overlap. So both the ones are going to lead to the formation of sigma bond. So sigma here, sigma here. Where will the sigma bond stronger? Sigma bond is going to be stronger here than that of this particular sigma. Because the lower energy orbitals, they are going to show more effective overlap. Okay? Remember this particular point as well. I'll be utilizing this particular point at a lot of places. This was strength of the sigma bonds, basically. Now, similarly, strength of pi bonds, you have to remember two things. Strength of pi bonds. My dear students, one statement. Strength of pi bond is inversely proportional to internuclear distance. Strength of pi bond is inversely proportional to internuclear distance. More the internuclear distance, lesser the strength of the pi bond. First of all, how a pi bond gets formed? Pi bond gets formed by the parallel overlaps. By the parallel overlapping. More the internuclear distance, lesser will be the strength of the pi bond. And this is the order which I would want every one of you to remember. This is the order which I would want every one of you to remember. And this is the order based on internuclear distance only. Here, it is going to be 2p, 2p pi overlap. 2p, 2p parallel overlap. Right? 2p, 2p parallel overlap. Here it's 2p, 3d parallel overlap. So internuclear distance is comparatively more. Right? Perfect? Yeah? So this is the order which you will be remembering when it comes to what? Strength of the pi bonds. 2p, 2p, followed by 2p, 3d, followed by 2p, 3p, followed by 3p, 3p. Perfect? So that pi bond which gets formed between 2p and 2p will be stronger pi bond than that of the other pi bond which is formed between 2p and 3d, than that of this one, than that of this one. Okay? Now, similarly, few more basic stuff. My dear students, between two atoms, whenever you see three bonds, remember, out of these three bonds, one is going to be your sigma bond, and another two bonds are going to be your pi bonds. Whenever you see a triple bond between two atoms, out of these three bonds, one is going to be sigma, two are going to be pi. Whenever, by chance, if you see four bonds between two atoms, out of which one is going to be sigma, two are going to be pi, and one is going to be delta. Imagine if this is sigma, this is pi, and this has to be delta. This is something which you need to know as well. Yeah? Right, people? All clear with this? All clear with this? And this delta is basically, you would have heard about rhenium tetrachloride. Rhenium tetrachloride is one molecule wherein delta bond gets formed. Right? Okay. My dear students, carbon-carbon double bond is frequently, it is abundant. It is frequently seen. But silicon-silicon double bond is not frequently seen. What is the logic? What is the logic? Carbon-carbon double bond is frequently observed. Silicon-silicon double bond is not frequently observed. Why is that? I mean, this pi bond is frequently seen. This pi bond is not frequently seen. Why? Because this is the pi bond which is formed between 2p, 2p parallel overlap. 2p, 2p parallel overlap. Right? This is 3p, 3p parallel overlap. And you know, the bond which gets, that pi bond which gets formed between 2p, that is stable, that is stronger. Perfect. If this is the stable one, if it is the stronger one, that is the reason for this particular pi bond to be stronger. I would say this particular pi bond is frequently observed, frequently seen, and this particular pi bond is rarely observed. Reason is, over here, the pi bond gets formed between, it is a 2p pi bond. Here, this one is going to be 3p pi bond. And you know, strength of 2p pi is more than that of strength of 3p pi. That is the reason why this particular pi bond is frequently seen and this is not frequently seen. As simple as that. Yeah? Right? Now, guys, let's try to use this VBT in some molecule so that you'll properly analyze and understand how this VBT explains the formation of different molecules. I'm marking the heading here as formation of different molecules. Formation of different molecules as per what? As per valence bond theory. Formation of different molecules as per valence bond theory. For example, the first molecule which I'm taking into consideration, let's say I have to show the formation of F2 molecule. How the F2 molecule is formed as per VBT. Try to understand, guys. How this F2 molecule is formed as per VBT. For example, I've got two fluorine atoms. What is the outermost configuration of fluorine? 2s2, 2p5, right? 2s2, 2p5. So this was your 2s2, 1, 2, 3, 4, and 5. This is your 2p5 configuration. Similarly, if this is one more fluorine atom, its outermost configuration also is 2s2, 2p5. Perfect. So this is S containing 2 electrons, and this is P containing 5 electrons. 1, 2, 3, 4, and 5. Perfect. Let me call this axis as PZ axis. This is PX axis. This is PY axis. Similarly, calling this as PZ, calling this as PY, calling this as PX. Perfect. Now, people, what exactly I'm doing over here? Let's say I'm keeping Z as the internuclear axis. Let's say I'm keeping Z as the internuclear axis. This is the Z axis, right? Talk about this fluorine atom. It's outermost. PZ carrying 1. So this is Z axis. That means this is your PZ. It's carrying 1. Perfect. PX, PY. PX will be perpendicular, right? PX will be perpendicular. Let's say this is your PX. Carrying how many? 2 electrons. Similarly, there will be PY as well. PY will be, for example, perpendicular to both X and Y. It is also carrying 2 electrons, right? Similarly, talk about this particular fluorine. PZ carrying 1 electron. So this is PZ. This is PZ, which is carrying 1 electron. Okay. Similarly, PY carrying 2. Let's say this is your PY carrying 2 electrons and PX carrying 2 electrons as well. PX carrying 2 electrons as well. So do you see penetration of atomic orbitals into each other here? Yes. What kind of overlap this is? This is axial overlap, which leads to the formation of sigma bond. So this is the sigma bond that has got formed between these two atoms. Okay. So how do I represent them at the end? This is fluorine, bond, fluorine. Perfect. So this is the formation of F2 molecule as per what? As per your valence bond theory is concerned. Correct, guys? Now, let me take one more example so that it becomes like clear to you. For example, I have to show the formation of O2 molecule. Let's say I have to show the formation of O2 molecule as per valence bond theory. How exactly I'm going to show this? Understand. I've got one oxygen atom whose configuration, for example, is 2s2, 2p4. There is one more oxygen atom whose configuration I'm keeping as 2s2, 2p4. Okay. 2p4 configuration I'm going to show like this. 1, 2, 3, 4. Similarly here. 1, 2, 3, and 4. This, for example, your PZ, This, for example, your py. This, for example, your px. This is, for example, your pz. This is, for example, your py. And this, for example, your px. Okay. Let's say this is your internuclear axis, which I'm calling as, which by default I'm taking as z axis, right? So talk about this oxygen. Its pz is, for example, this one carrying 1 electron. Perfect. Its py is, for example, this is py carrying 1 electron. Px is carrying 2 electrons. Let's say this is your px, which is carrying 2 electrons. Talk about another oxygen atom. Its pz is carrying 1 electron. Its pz is carrying 1 electron. Let's say this is its pz carrying 1 electron. Similarly, its py is carrying 1 electron. Its py is carrying 1 electron. Let's say this is its py carrying 1 electron. And similarly, its px is carrying 2 electrons. This is px carrying 2 electrons already. Okay. What has happened over here? Between these two orbitals, I would say axial overlap has happened, right? This is the direct penetration of atomic orbitals into each other. So this is the sigma bond. Now, if you talk about py and py, both are containing unpaired electrons and both are parallel as well. So they are going to show which overlap here? They are going to show parallel overlap here. They are going to show parallel overlap here. So between two oxygen atoms, this was oxygen atom, this was one more oxygen atom. First, which bond got formed? First, sigma bond got formed. After that, pi bond got formed. So finally, you can represent it here. Oxygen, first single bond got formed, then your pi bond got formed. So this is O double bond O, out of which one is your sigma bond and one is your pi. I hope this is also clear to you. Yeah? All clear, people? This was the formation of O2 molecule. Similarly, if you want to have a look on the formation of N2 molecule, how N2 molecule is formed. Formation of N2 molecule. Okay. This is one of the nitrogen atoms whose outermost configuration is 2p3. This is one more nitrogen whose outermost configuration again is 2p3. 2p3 configuration, how it looks like? 1, 2, and 3. Similarly, here also it is 2p3. So I would say this is 1, this is 2, this is 3. So, calling this as the internuclear axis as z-axis, for example. If this is your z-axis, I'm calling this as pz, this is your py, this is your px. Similarly, let's say this is your pz, this is your py, this is your px. Now, let's show this particular nitrogen atom, it's pz. This is its pz. This is pz containing 1 electron. Similarly, it has got px as well as py. Let's say this is py carrying 1. And similarly, this is px carrying 1. Correct? Talk about one more nitrogen atom. It has got also one pz carrying unpaired electron. This is that pz. So it has formed the, it has done the axial overlap here, sigma. Now, it has got py as well. It has got py as well, carrying 1 electron. Similarly, it has got pz as well, carrying 1 electron. So already sigma bond has got formed over here. Now, if you think carefully, this is py, py. They are going to show parallel overlap, right? Similarly, this is pz, pz. They are parallel also. If pz, pz is also parallel, right? They're also going to show parallel overlap. So how do I represent this? If this is one nitrogen atom, this is here one more nitrogen atom. First, a sigma bond got formed. Then 2p pi, 2p pi. 2p pi, 2p pi bonds. Perfect. So this is your N2 molecule, out of which one is sigma, one is pi, and one more is also pi. This is the formation of N2 molecule as per VBT is concerned. Let me know once in the chats if it is super clear. Let me know once in the chats if it is super clear. So this was your valence bond theory. I hope if anything is asked from VBT, you should be in a position to answer the question. All clear, people till here? Quickly in the chats, everyone. everyone. Perfect. So let's move on to hybridization now. Huh? Just give me a second. I hope all of you are alive and ticking. Yeah? Alive and ticking. Fire in the chats, Will. Fire in the chats. Yeah. Class duration, I do not know. Class duration, I do not know. For him, node is a region around the nucleus at which electron density is 0. That's what you call as node. So around the nucleus, you will see multiple regions. There will be some regions wherein electron density probability is maximum, right? There will be some regions wherein electron density will be 0. One is called as orbital, one is called as node. Simple. Let's get done with hybridization. After that, we'll take a break again. Yeah? Let's get done with the hybridization. Let's get done with the hybridization. So first of all, what was the need of hybridization? So let's talk about, first of all, need for hybridization. Why this concept of hybridization was given. What was the need for hybridization? Why this concept of hybridization was given? Okay. What is the need for hybridization? Try to understand, guys. First of all, we know already strength of a bond is directly proportional to extent of overlap. Strength of a bond is directly proportional to extent of overlap. Extent of overlap. I can relate it with bond length as well. So I would say it will be inversely proportional to bond length. Stronger the bond, lesser the bond length, right? Stronger the bond, lesser the bond length. Stronger the bond between the atoms, lesser is going to be their bond length. Now guys, try to understand. For example, let's see the formation of the molecule CH4. Let's see how CH4 molecule is formed as per VBT. Let's see how CH4 molecule is formed as per VBT. See guys. For example, if I take the carbon atom, if I talk about carbon, what is the outermost configuration of carbon? 2s2, 2p2. This is the outermost configuration of carbon, right? 2s carrying 2 electrons, 2p also carrying 2 electrons. This is what you call as the ground state of carbon. This is what you call as ground state of carbon. Now, since carbon here is forming 4 bonds, and over here there are only 2 unpaired electrons. So as per this ground state configuration, since there are only 2 unpaired electrons, as per VBT, this carbon should form only 2 bonds. Right? As per VBT, this carbon should form 2 bonds only because it has got only 2 unpaired electrons. But carbon in reality is forming 4 bonds. So what should happen? There should be the presence of 4 unpaired orbitals. How there will be the presence of 4 unpaired orbitals? One of the electron will get excited and will go here. So when you write carbon in excited state, 1 here and 3 here. This is the excited state of carbon. This is the excited state of carbon. This is the 2s carrying 1 electron of carbon. This is, for example, 2px. This, for example, 2py. This, for example, 2pz. Correct? Right, people? Now, this is 2s of carbon carrying 1 electron. This is, for example, 2px of carbon carrying 1 electron. This is, for example, 2py of carbon carrying 1 electron. And this, for example, 2pz of carbon carrying 1 electron. Correct? Now, what is going to happen? What's going to happen? Carbon has to form bonds with hydrogen. Hydrogen, what is the outermost configuration of hydrogen? It is 1s1. Right? So it is s orbital carrying 1 electron. So I would say one of the s orbital of hydrogen, one hydrogen atom, its s orbital will come from here. We'll do the overlap. Right? So it's going to be ss overlap. Here it's going to be sp overlap. Here it's going to be sp overlap. Here it's going to be sp overlap. So I would say one of the hydrogen will come from this side. We'll do the overlap. One more hydrogen will do the head-on overlap with this. One more hydrogen will do the head-on overlap with this. One more hydrogen will do the head-on overlap with this. Right? So this overlap is going to be here. This is 1s of hydrogen, 1s of hydrogen, 1s of hydrogen, 1s of one more hydrogen, since there are 4 hydrogen atoms. So this overlap was your 2s2s overlap. This overlap is your 2s2p overlap. This overlap is your, again, 2s2p overlap. The first overlap was your 1s2s overlap. The second overlap is again your 1s2p overlap. Third overlap is also your 1s2p overlap. And fourth overlap is also your 1s2p overlap. Right? My dear students, SS overlap, SP overlap. See, the overlap is different. Here the overlap is between SS. Here the overlap is between SP. So extent of overlap is different. So extent of overlap in these cases will be different. If extent of overlap will be different, I would say the sigma bond which got formed here and the sigma bond which got formed here, should they have same strength or different strength? Since the extent of overlap is different, so the sigma bonds formed should have different strengths. If sigma bond formed, if sigma bond formed over here have different strengths, so bond lengths, CH bond lengths should be different too. CH bond length should be different too. But it was observed that in CH4, it was seen experimentally, all the bond lengths are same. As per VBT, all the bond lengths should not be same because here it's SS overlap, here it's SP overlap. Extent of overlap is different. So strength of CH bond in these two cases should be different. If strength of bonds are different, therefore bond length should be different. But in reality, it was observed that in case of CH4, all the bond lengths are same, right? Which was not explained by VBT, which was explained by one more concept, that is the concept of hybridization. Did you understand why the concept of hybridization was introduced? Quickly in the chats. Did you understand why the concept of hybridization was introduced? Because VBT could not explain why all the 4 CH bonds in case of CH4 are same. Yeah? Right, people? VBT could not explain that. As per VBT, this was the sigma bond formed by SS. This was the sigma bond formed by SP. Since extent of overlap here and extent of overlap here should be different. So bond strength, sigma bond which gets formed here and sigma bond which gets formed here, their strength should be different. Therefore, CH bond length here, CH bond length here should be different. But in reality, it was observed that all the bond lengths in CH4 are same, which was technically explained by what? Which was technically explained by your hybridization. Now, let's talk about this hybridization. What this hybridization exactly is all about. My dear students, this is one of the super important topics. Hybridization question is frequently asked from this topic, right? Understand. The first point related to hybridization, let me tell you, it's a complete hypothetical concept. It is a complete hypothetical concept. That means this hybridization, it does not have any experimental background. It is complete hypothetical. It is complete hypothetical. So no experimental background. No experimental background. Now, let me write few points about hybridization. Then I'll make you understand what exactly it's all about. See guys. See. In case of hybridization, what happens? In case of hybridization, what happens? Let me tell you. In case of hybridization, atomic orbitals of a bonding atom, that particular atom which is going to form bonds, that particular atom which is going to show the bond formation, its atomic orbitals are going to intermix. Atomic orbitals of the bonding atoms. Atomic orbitals of, I'll write it like this, wait. Atomic orbitals of a particular bonding atom. Atomic orbital of a particular bonding atom. Particular bonding atom. Those atomic orbitals are going to show intermixing. They are going to intermix. Right? And my dear students, intermixing of atomic orbitals of a particular atom. Right? So let me quickly tell you this thing again. First of all, it is a theoretical concept. Who is spamming in the chats? Who is this such a nonsense? Go sleep. You sleep, bro. Why are you, giving some free suggestions to all these kids? You sleep, you go somewhere else, right? You have a lot of work to finish. Your night has started. Yeah? Just give me a second, guys. Who is this Dikshi? Dikshi, you will never be able to comment here on this channel from now onwards. This Stella someone. Sorry for you. Again. You'll never be able to comment on this channel. Do we have any other one? Do we have any other one? Blocked. Is there any other hero or heroine? Yeah? Quickly. Just give me the names. I'll do it right now and we'll start again. Just give me the names, I'm asking you. Yes, Diksha, you can go there. If NASA has told, you can go to NASA and talk to them, okay? And let me know what they say. You're blocked. Anyone else? Quick. Quick. Okay, let's continue now. So, if I talk about hybridization, it is a complete hypothetical concept, number one. Number two, it does not have any experimental background. Number three, in case of hybridization, what happens exactly? In case of hybridization, atomic orbitals of the bonding atom, the atomic orbitals are going to intermix. Atomic orbitals of a bonding atom, they are going to intermix, right? Or let me write it over here like this. Atomic orbitals of a bonding atoms which have got slightly different energies. Or let me not use the term slightly different energies. Let's keep it as such. Atomic orbitals of a particular bonding atoms, right? They are going to intermix. And when atomic orbitals of a bonding atom are going to intermix, they are going to lead to the formation of new orbitals. Lead to the formation of new orbitals. New orbitals which are identical in all the respects. Which are identical in all the respects. That means identical in shape, identical in energy, etc., etc. So atomic orbitals of the bonding atom are going to intermix and they are going to lead to the formation of new orbitals which are identical, right? Which have got same shape, same energy. And those new orbitals formed are what we call as hybrid orbitals. Those new orbitals formed are what we call as hybrid orbitals. How these hybrid orbitals look like? We have to make one lobe bigger in size, one lobe smaller in size. This is how hybrid orbitals look like. Once these hybrid orbitals are generated, right? After that, what happens? I would say these hybrid orbitals, once these hybrid orbitals are generated, these hybrid orbitals arrange themselves in such a way, these hybrid orbitals arrange themselves in such a way that there should be minimum repulsions between them. There should be minimum repulsions between them. And once these hybrid orbitals are formed, let me tell you, hybrid orbitals formed overlap with the hybrid orbitals or pure atomic orbitals, with the pure atomic orbitals of other atoms. And let me tell you, hybrid orbitals formed, they are going to overlap with the hybrid orbitals or atomic orbitals of other atoms. And overlap of hybrid orbitals always leads to the formation. Always leads to the formation of sigma bond. There is one exception, that is benzene. Except in benzene. In case of benzene, hybrid orbitals overlap and lead to the formation of pi bonds. One more thing. Vacant orbitals, half-filled orbitals, as well as fully filled orbitals can participate in intermixing. Can participate in hybridization. And remember, number of atomic orbitals intermixed is always equal to the number of hybrid orbitals formed. number of atomic orbitals intermixed is equal to number of hybrid orbitals formed. Guys, first write all this stuff. Then I'll be explaining all this stuff one by one. Okay? Next important point. Hybridization does not take place in the isolated atoms. Does not take place in the isolated atom. Hybridization only takes place at the time of bond formation. Hybridization takes place at the time of bond formation. Now, people, it's time to understand what this hybridization exactly is all about. See, there are a few things which you need to remember first, and I'll show you its application, how all these concepts, all these points related to hybridization are utilized. First thing which you need to remember, hybridization is a completely hypothetical concept. It does not have any experimental background, number one. Number two, when you talk about hybridization, hybridization simply means intermixing of atomic orbitals of one atom, right? Atomic orbitals of an atom, they are going to intermix, they are going to lead to the formation of new orbitals, which are identical in all the respects, and those new orbitals are what we call as hybrid orbitals. Once these hybrid orbitals are formed, they arrange themselves in such a way that there are minimum repulsions between them. And once these hybrid orbitals are formed, these hybrid orbitals, once formed, they overlap either with hybrid orbitals of other atoms or atomic orbitals of other atoms. And let me tell you, overlapping of hybrid orbitals, it always leads to the formation of sigma bond except benzene. Right? In hybridization, in intermixing, vacant orbitals, fully filled orbitals, half-filled orbitals, all the types of orbitals can participate in the intermixing. All the types of orbitals can participate in the hybridization, right? Similarly, number of atomic orbitals intermixing is always equal to number of hybrid orbitals formed. If two atomic orbitals of an atom are intermixing, they lead to the formation of two hybrid orbitals. If three atomic orbitals are intermixing, they lead to the formation of three hybrid orbitals. So number of atomic orbitals intermixed is equal to number of hybrid orbitals formed. Similarly, hybridization only takes place at the time of bond formation. Whenever between two atoms bond has to get formed, at that point of time, you'll talk about hybridization. If you have got the isolated atom, which is not going to form any bond. Let's say you have got an isolated atom, which is not going to form any bond. So you are not going to discuss hybridization in that isolated atom. Hybridization is discussed only in case of those atoms which are going to form the bonds. Hybridization does not take place in the isolated atoms. Now, let's get to know about this hybridization a bit more in detail. But before getting to know about hybridization a bit more in detail, there are a few more things which you need to know first. What is that? How do we calculate hybridization? My dear students, there is a method called as steric number method. There is a number called as steric number method, with the help of which we calculate hybridization of the atom. With the help of which we calculate hybridization of the atom. So I'm first of all going to show you how to calculate hybridization with the help of steric number method, and after that I'll explain this hybridization one on one, right? All the points, whatever I wrote on the screen already. Okay. First of all, in case of steric number method, what do we need to do first of all? We need to calculate steric number. What is steric number? Steric number simply means sigma bonds plus lone pairs. Sigma bonds plus lone pairs is going to give us the steric number, right? It is going to give us the steric number. Point number one. If steric number comes out to be 2, at that point of time, we say hybridization involved is sp. If steric number is equal to 3, at that point of time, we say hybridization involved is sp2. If steric number is 4, at that point of time, we say hybridization involved is sp3. If steric number is 5, at that point of time, we say hybridization is sp3d. If steric number is 6, at that point of time, we say hybridization involved is sp3d2. If steric number is 7, at that point of time, we say hybridization is sp3d3. sp3d3. Now, In case of sp hybridization, what happens? I would say in the atom, one of the s and one of the p orbitals, right? They are going to intermix. Over here, one of the s and two of the p orbitals are going to intermix. Over here, one of the s and all the three p orbitals are going to intermix. Perfect. Let's call this as px, py, this is pz. In case of sp3d, I would say one of the s orbital, px, py, pz, and over here dz square, right? They are going to intermix. In this particular case, it's s, px, py, pz, dx square minus y square, and dz square. These are the six orbitals which are going to intermix. Similarly, this is s, this will be px, py, pz, dx square minus y square, dz square, and dxy. These are the orbitals which are going to intermix. I told you the number of atomic orbitals intermixed is equal to the number of hybrid orbitals formed. So here, how many hybrid orbitals will be getting formed? 2 hybrid orbitals. Here, 3 hybrid orbitals will get formed. Here, 4 hybrid orbitals, 5 hybrid orbitals, 6 hybrid orbitals, 7 hybrid orbitals will get formed, right? And I told you, the hybrid orbitals which get formed, they orient themselves in such a way that there should be minimum repulsions between them, right? But dear students, remember, whenever there is sp hybridization, the geometry which is predicted through hybridization, that is linear, and bond angle is 180 degree. Whenever hybridization is sp2, we say the geometry which is predicted through hybridization, what is that? That is trigonal planar. That is trigonal planar. And at that point of time, the bond angle is 120 degree. In case of sp3d hybridization, the geometry predicted through hybridization is tetrahedral, right? And at that point of time, the bond angle is 109 degree, 28 minutes. Okay. In case of sp3d hybridization, right? The geometry predicted through hybridization is trigonal bipyramidal. Trigonal bipyramidal. And in case of trigonal bipyramidal geometry, how many different types of bond angles do you observe? You observe different types of bond angles. You observe 120 degree bond angle, which I'll show you few minutes afterwards. 120 degree. You observe 90 degree bond angle as well. You observe 90 degree bond angle as well. So these are the 2 bond angles which you observe in trigonal bipyramidal geometry. Similarly, in sp3d2, the geometry predicted through hybridization is what you call as octahedral. And in case of octahedral geometry, you only observe one type of bond angle, that is 90 degree. That is 90 degree. In case of sp3d3 hybridization, the geometry predicted through hybridization is pentagonal bipyramidal. Pentagonal bipyramidal. And here you will see one of the bond angle as 72 degree, one of the bond angle as 90 degree. Perfect. This is just some basics which is required to learn the hybridization in detail. This is some basics which is required to learn the hybridization in detail, right? So remember, when steric number is 2, steric number is first of all sigma plus lone pair. When steric number is 2, sp. Steric number 3, sp2. Steric number 4, sp3. Similarly, sp3d, sp3d3, similarly sp3d2, sp3d3. These are the atomic orbitals which intermix, and number of atomic orbitals intermixed is equal to number of hybrid orbitals formed. These are the geometries which are predicted through hybridization, and these are the respective bond angles which are observed in these geometries. Now, let's get into the details of hybridization. Let's see exactly how what all things we have to consider here when we talk about hybridization. Understand, guys. The first molecule which I'm taking over here, that is BeCl2. Understand properly. First of all, beryllium here is your central atom. And how many valence electrons are with beryllium? How many valence electrons are there with your central atom? 2. How many surrounding atoms do you see? 2 surrounding atoms. Number of surrounding atoms is equal to number of sigma bonds. Number of surrounding atoms is equal to number of sigma bonds. I would say beryllium had 2 valence electrons, and it has utilized both the electrons to form 2 sigma bonds. So there will be no lone pair on beryllium. No lone pair on beryllium. I calculated sigma as well as lone pairs. What about steric number? Steric number is sigma plus lone pair. 2 plus 0 is 2. If steric number is 2, hybridization involved is sp. If hybridization involved is sp, So I would say geometry predicted through hybridization is linear. Geometry which is predicted through hybridization, that is linear. Now, get into the details of it. Get into the details of it. See how it's formed. Understand. I'm going to write the central atom as beryllium over here. Hydrogen, helium, lithium, beryllium. Its outermost configuration is 2s2 and 2p0. This is the outermost configuration of beryllium, right? So my dear students, I would say this 2s carries 2 electrons here and this 2p carries 0 electrons here. This is the ground state configuration of beryllium. This is the ground state configuration of beryllium. What you need to do first is just do the excitation. Send 1 electron here. When you send 1 electron here, this will contain 1 electron and this will also contain 1 electron. So this is my excited state here. This is my excited state. Now in case of BeCl2, beryllium undergoes sp hybridization. So this s orbital and this p orbital of beryllium, they are going to intermix. They are going to intermix. As I told you already, the number of atomic orbitals intermixed is equal to number of hybrid orbitals formed. Since 2 atomic orbitals are intermixing, so it will lead to the formation of 2 hybrid orbitals. This is one of the hybrid orbital. This is one more hybrid orbital, right? This hybrid orbital I'll be calling as sp hybrid orbital. This is also what I call as sp hybrid orbital. How these hybrid orbitals got formed? By the mixing of these 2 orbitals, s and p. sp orbitals mixed and formed 2 hybrid orbitals, sp hybrid orbitals. Okay. Now, my dear students, these sp hybrid orbitals, they are going to arrange themselves in such a way that there should be minimum repulsions between them. So first of all, 1, 1, there are 2 electrons, give this 1 electron, give this 1 electron. Okay. Now these hybrid orbitals, as I told you, they are going to orient themselves in such a way that there should be minimum repulsions between them. So these are the 2 sp hybrid orbitals. These are the 2 sp hybrid orbitals which have arranged themselves in such a way that there is minimum repulsions between them. One carrying 1 electron, one more carrying 1 electron. Yeah. Now, what is going to happen after this? After this, I would say this beryllium has to form a bond with 2 chlorine atoms. If you talk about chlorine, its outermost configuration is 2p5, right? 1, 2, 3, 4, 5. Let's call this as pz. This is px. This is py, for example, right? It contains 1 unpaired orbital. That unpaired orbital of 1 chlorine atom, this pure pz orbital of 1 chlorine atom will come from this side. We'll do the overlap. And there is one more chlorine as well, whose pz will come from this side. We'll do the overlap. So, which overlap this is? This is head-on overlap happening, right? Head-on overlap happening means which bond will get formed? Sigma bond. So, this is a sigma bond formed. This is a sigma bond formed. I would say this sigma bond is formed between sp hybrid orbital of beryllium and pure p orbital of chlorine. Similarly, this sigma bond is formed by sp hybrid orbital of beryllium and pure p orbital of chlorine. Perfect. So, at the end, I'm going to represent it like this. This is B at the center. This is 1 chlorine and this 1 more chlorine. If I ask you what is the bond angle over here, you will say bond angle here is 180 degree. And what is the geometry which is predicted through hybridization? It is linear, right? Now, guys, there is one more thing which I want to tell you. These 2 atomic orbitals, they intermixed and formed hybrid orbitals, right? And formed hybrid orbitals. Right? See, guys, this is one of the hybrid orbital. This is one more hybrid orbital. This sp hybrid orbital, it is formed how exactly? How these 2 sp hybrid orbitals are formed? When these 2 atomic orbitals have intermixed, right? So this hybrid orbital will be containing some s character, some p character into it. This hybrid orbital also contains some s character and p character into it. Let me tell you percentage of s character. Percentage of s character in sp hybrid orbital. How do you calculate it? See, how many s orbitals were used to form this? 1 s orbital was used. How many total orbitals intermixed? 2 multiplied by 100. So I would say this sp hybrid orbital will 50% be like s orbital, 50% be like p orbital. So it will be having 50% characters of s orbital, it will be having 50% characters of p orbital. Similarly, if you want to calculate percentage of p character in this sp orbital, how many p orbitals were used? 1. In total, how many orbitals were used? 2 multiplied by 100. So 50%. So this hybrid orbital over here, they'll be 50% more like s orbital, 50% more like p orbital. Yeah. Is it clear, people, today? So this was your BeCl2, wherein the hybridization involved is sp. Okay. Let me take few more cases. Let's say you got BF3. Talk about the second case, BF3. First of all, boron is a central atom. How many valence electrons boron has? Hydrogen, helium, lithium, beryllium, boron. So 2 in the first shell, 3 in the second shell. Right? So 3 valence electrons. How many surrounding atoms? 3. Number of surrounding atoms is equal to number of sigma bonds. Number of surrounding atoms is equal to number of sigma bonds. How many lone pairs boron has? Boron had 3 valence electrons. And I would say it has utilized all the 3 valence electrons to form 3 sigma bonds. So there will be 0 lone pairs. If there is 0 lone pair, steric number sigma plus lone pair, 3 plus 0 is 3. Hybridization involved is sp2. When hybridization is sp2, the geometry predicted through hybridization is trigonal planar. Let's have a look one by one on the different steps which we have over here. See guys, if you talk about boron, what is the outermost configuration of boron? Hydrogen, helium, lithium, beryllium, boron, right? 1s2, 2s2, 2p1. So it is 2s2, 2p1. This is the ground state configuration of boron. This is the ground state configuration of boron. Perfect. If I would want to make its excited state, send one of the electron from here to here. When you send one of the electron from here to here, it will be, this is carrying 1, and I would say this carrying 1, this carrying 1. Perfect. Now, boron here is undergoing sp2 hybridization. So I must say, one of the s and 2p orbitals, they are going to intermix. Since 3 atomic orbitals are intermixing, so they lead to the formation of 3 hybrid orbitals. 1, 2, and 3. Perfect. Each hybrid orbital I'll be calling as sp2. I'll be calling as sp2 hybrid orbital. First of all, if I ask you what is the percentage of s character in case of sp2 hybrid orbital, it will be equal to how many s orbitals were involved during intermixing? 1. Divided by how many total orbitals are involved? 3. Multiplied by 100. So 33%. 33% of s character is there in this sp2 hybrid orbital. Similarly, what is the percentage of p character in case of sp2 hybrid orbital? It will be 100 minus 33, which approximately comes out to be 66.6%. Now, my dear students, what happens? Once hybrid orbitals are generated, since there are 3 electrons, give 1 to each. Once these hybrid orbitals are generated, now we have to arrange these hybrid orbitals in such a way, that there should be minimum repulsions between them. This is how they orient themselves, right? And each hybrid orbital is containing 1 electron. Now, my dear students, boron is forming bonds with fluorine atom, right? What is the outermost configuration of fluorine? 2p5, right? 2p5. So one of the p orbital of fluorine will be unpaired. Imagine the unpaired p orbital of one fluorine came from this side and did the overlap. Similarly, the unpaired p orbital of one more fluorine came from this side, did the overlap. And similarly, the unpaired p orbital of one more fluorine came on this side and did the overlap. What should I call these types of overlaps as? What do I call these overlaps? This is the overlap which happened between sp2 hybrid orbital of boron with pure p orbital of fluorine. This is also your sp2 p overlap. This is also your sp2 p overlap, right? And all these overlaps are head-on overlaps, direct overlaps, right? Axial overlaps, they lead to the formation of sigma bond. So sigma bond is formed here, sigma is formed here, sigma is formed here. At the end, how do I show it? This is boron, one fluorine here, one fluorine on this side, and one fluorine on this side. If I ask you, how does it look like? This shape looks like trigonal planar. What do you think is the bond angle over here? This bond angle will be 120 degree. Am I clear with this? Am I clear with this, people? Am I clear with this? Now, this was your BF3. Now, talking about CH4. If I talk about carbon, how many valence electrons carbon has? 4. How many surrounding atoms? 4. Number of surrounding atoms is equal to number of sigma bonds. How many lone pairs? I would say carbon had 4 valence electrons and it has utilized all the 4 valence electrons to form 4 sigma bonds. So 0 lone pairs. Correct number. 4 plus 0, 4. Hybridization involved. sp3. Geometry predicted through hybridization. Tetrahedral. Geometry predicted through hybridization has to be tetrahedral. Now, look at the other things. If you talk about the outermost configuration of carbon, it's 2s2, 2p2. Perfect. This is 2s carrying 2 electrons. This is 2p carrying 2 electrons, 1 and 2. I'll be calling this as ground state configuration of carbon. Perfect. Now, if I want to make the excited state configuration of this carbon, so I'll have to send 1 electron. So it becomes like this. 1 here, 1 here, 1 here. I'm calling this as the excited state of carbon. Perfect. Now, carbon over here is undergoing sp3 hybridization. So, s orbital and these 3 p orbitals are going to intermix and they will lead to the formation of, since 4 atomic orbitals are intermixing, they lead to the formation of 4 hybrid orbitals. Each hybrid orbital I'll be calling as sp3 hybrid orbital. Each hybrid orbital I'll be calling as sp3 hybrid orbital, right? Now, first of all, if you ask me what is the percentage of s character in one of the hybrid orbitals, you will say 1 s orbital is involved. Divided by, in total 4 atomic orbitals are involved, multiplied by 100. So, one of the sp3 hybrid orbitals contains 25% of s character into it. And the remaining will be p character. So, p character will be 75%. So, this sp3 hybrid orbital will be more looking like p orbital as that of s. Because its percentage p character is 75%. So, this sp2 hybrid orbital will be more looking like p orbital than that of s. Yeah? Yes, steel shot, I live there. I'm right now live from there only. Okay? So, as I told you people, how many hybrid orbitals we got over here? We got 4 hybrid orbitals. Now these hybrid orbitals, since there were 4 electrons, so give 1 electron to each hybrid orbital. Now these 4 hybrid orbitals, they are going to arrange themselves in such a way that there should be minimum repulsions between them. Let's say this is one of the hybrid orbital. This is one more hybrid orbital. This is one more hybrid orbital. And this is one more hybrid orbital. And each hybrid orbital will be containing 1 electron each. Yeah? Now, it is CH4. So I would say s orbital of hydrogen will come from this side, 1 more from this side, 1 more from this side, 1 more from this side. Perfect. And do the overlap. Which overlap? This is head-on overlap. So this is the overlap between sp3 hybrid orbital of carbon and pure s orbital of hydrogen. Similarly, all these overlaps are same, right? And everywhere head-on overlap has happened. So I would say 4 sigma bonds has got formed over here. This is CH, this is H. Similarly, this is one more H, this is one more H. Do you see sp3s, sp3s, sp3s as well as sp3s? So type of overlap everywhere is same. If type of overlap everywhere is same, that means extent of overlap everywhere will be same. Strength of all the 4 bonds will be the same. All the 4 bond lengths, all the 4 CH bond lengths in CH4 will be same, which VBT could not explain. Hybridization explained, right? Hybridization explained this. Now, this structure, what do we call this as? We call this as tetrahedral structure. And in case of tetrahedral structure, what is the bond angle? Bond angle here will be 109 degree, 28 minutes. Okay? I hope this is clear. All clear, people? All clear? Yeah? So this was your CH4 molecule showing sp3 hybridization. Now, talking about sp3d hybridization. See, the central atom is phosphorus here. How many valence electrons phosphorus has? Phosphorus belongs to nitrogen family. It has got 5 valence electrons. Okay. Now, how many sigma bonds? 5 sigma bonds. How many lone pairs with phosphorus? 0 lone pair. Steric number, sigma plus this, 5. Right? Hybridization involved, sp3d. Geometry predicted through hybridization, it's trigonal bipyramidal. Trigonal bipyramidal. Now let's see all this in detail. Let's see all this in detail. See, if you talk about phosphorus, its outermost configuration will be 3s2, 3p3, as well as 3d0. So this is technically the ground state electronic configuration of phosphorus. This is the ground state configuration of phosphorus. Now, in the excited state, one of the electrons would have gone here. So the excited state will be like this. This is the excited state configuration. This was the ground state configuration. This is the excited state configuration. Now, which hybridization is involved here? You can see sp3d hybridization is involved. So one of the s, 3p orbitals and 1d, they are going to intermix. They lead to the formation of 5 hybrid orbitals. They will lead to the formation of 5 hybrid orbitals, right? Okay. They lead to the formation of 5 hybrid orbitals. Each hybrid orbital I'll be calling here as sp3d hybrid orbital. What is the percentage of s character in one of the sp3d hybrid orbital? How many s orbitals are involved? 1 divided by, in total how many orbitals? 3, 4, 5 multiplied by 100. This is going to give you the percentage of s character in sp3 hybrid orbital. Similarly, you can calculate percentage of p character as well. How many p orbitals were involved? 3 divided by, in total 5 orbitals multiplied by 100. Similarly, you can talk about d. Percentage of d character, 1 divided by 5 into 100. Perfect. That's going to give you percentage of all these. Right, people? So, what's going to happen here? What is going to happen here? Since we got 5 hybrid orbitals, since there are 5 electrons, give 1 electron to each here. Now, these 5 hybrid orbitals containing electrons, they are going to orient themselves in such a way that there should be minimum repulsions between them. So, imagine this is one of the hybrid orbital. Imagine this is one more hybrid orbital. And imagine this one more hybrid orbital, right? So these are the 3 hybrid orbitals which I have made over here and each containing 1 electron. So imagine these 3 hybrid orbitals, they are present on one plane. They are present on one plane. There is one more hybrid orbital here present above the plane and one more hybrid orbital here present below the plane. Okay? And they are also containing 1 electron. Now people, this is PCl5. Imagine one phosphorus will come from this side, we'll do the overlap. One phosphorus from this side, one from this side, one chlorine from this side, one chlorine from this side, one chlorine from this side. From all the sides, chlorine atoms came, did the overlap, right? So how do I show it at the end? How did I show it at the end? How did I show it? How do I show it at the end? See guys, this is phosphorus, perfect. This is one of the sigma bond which is forming with chlorine, one more sigma which is forming with chlorine, one more sigma which it is forming with chlorine. All these 3 bonds, they are present on the same plane. All the 3 bonds, they are present on the same plane. Okay, I mean all these 4 atoms, they are present on one plane. Now above the plane you will find one bond. Above the plane there is one chlorine. Similarly, below the plane also there is one chlorine. Above the plane as well as below the plane, there is one chlorine. Now guys, this particular geometry is something which we call as trigonal bipyramidal geometry. This is what you call as trigonal bipyramidal geometry. Now understand, these bonds which I represent over here with the white color, this bond, and this bond. These white colored lines I'll be calling as equatorial bonds here. Equatorial bonds. And yellow colored lines over here, this one and this one, I'll be calling them as axial bonds. I'll be calling them as axial bonds. Okay. But dear students, remember one thing. This particular bond angle between two equatorial bonds, between two equatorial bonds, The bond angle is 120. Okay, the bond angle is 120. Between axial and equatorial, the bond angle is 90. The bond angle is 90. Between axial and axial, the bond angle is 180. Axial and axial, bond angle is 180. Okay. Now, if I ask you one more thing here, let me not ask you, let me just tell you this. Remember, axial bond length here will be greater than that of equatorial bond length. In case of sp3d hybridization, in case of PCl5, you will find axial bond length greater than that of equatorial. Why is that? Because these three equatorial chlorine atoms, they have got lone pairs. This has got lone pairs. This has got lone pairs. They are going to show repulsion to the lone pairs of this particular chlorine. These three chlorine atoms will show repulsions towards the lone pairs of this particular chlorine. See, this chlorine carries lone pair. This carries lone pair. Repulsions. Lone pair, repulsions. Lone pair, repulsions. Similarly, lone pair, repulsions. Due to which these axial bonds, they elongate and axial bond length eventually comes out to be greater than that of equatorial bond length. If I ask you, how many 90-degree angles are here in this particular compound? How many 90-degree angles do you see? How many 90 degrees do you see here? See guys, one on 90, second 90, third. See, basically these three bonds, these white colored lines, they are present on the same plane, right? There is axial one above it, which is forming 390 degrees from the top. Similarly, 390 degrees from the bottom. So in total, how many 90 degrees do you see? 690 degrees. 690 degrees, right? How many 120 degrees do you see here? 1, 2, 3. 390 degrees. Okay? 390 degrees you see here. Am I clear? Am I clear with this? So this was your sp3d hybridization. And in case of sp3d hybridization, which all orbitals are involved? This is s, this is px, py, pz, and dz square. And dz square. I hope I'm clear with this. Okay? Perfect. This was your PCl5, which was sp3d. Now, similarly, there is sp3d2 as well. Understand? If you talk about this sulfur atom, how many valence electrons it has? Sulfur belongs to oxygen family, so 6 valence electrons. Yeah, 6 valence electrons. How many sigma bonds? 6 sigma bonds. Surrounding atoms is equal to sigma bonds, right? Lone pairs on sulfur. Sulfur had 6 valence electrons. All the 6 valence electrons it has utilized to form 6 sigma bonds, so no lone pair. Direct number 6 plus 0, 6. Hybridization sp3d2. sp3d2. Geometry predicted through hybridization octahedral. Octahedral, right? Now, if you talk about sulfur, its outermost configuration will be 3s2, 3p4, 3d0, right? Let's say this is 3s2. 3p4. 3d0. This is the ground state electronic configuration of sulfur. Now, if you talk about the excited one, send one electron here, send this electron also here, right? So, excited state electronic configuration of sulfur will be like this. This is the excited state electronic configuration of sulfur. Now, which hybridization it undergoes? sp3d2. So, s, 3p and 2d orbitals. So, it undergoes sp3d2 hybridization, right? So, number of atomic orbitals intermixed is equal to number of hybrid orbitals formed. So, 3 to 5 plus 1, 6. So, over here, I would say 6 hybrid orbitals would have got generated. Now, how these 6 hybrid orbitals would have oriented themselves? How these 6 hybrid orbitals would have oriented themselves? Let me show it to you. Let's say this was one hybrid orbital. This is one more hybrid orbital. One more here. And one more here. So these 4 orbitals on one plane. These 4 hybrid orbitals on one plane. Similarly, one above the plane perpendicular upwards. One down the plane perpendicular downwards. Okay. So all these hybrid orbitals, they are containing one electron. 4 in the plane, 4 in the plane, 1 above the plane, 1 below the plane. Now, SF6, I would say one fluorine atom would have come from this side, one from this side, one from this, one from this, one from this, one from this. And what do we call this particular geometry? If I show it at the end, this is sulfur. This was one of the fluorine atom. This was one more fluorine. One more fluorine. One more fluorine. All these 5 atoms, including sulfur, they are present on the same plane. They are present on the same plane. Perpendicular to it, there is one fluorine upwards. Perpendicular downwards, there is one fluorine like this. Okay? And when you join them, right, what kind of geometry do you get over here? This is octahedral. This is what you call as octahedral. Okay? What is the bond angle? What is the bond angle? First of all, between this equatorial bond angle is 90 degree. This is 90. Axial equatorial is also 90 degree. Because all these axial bonds, they are present on plane. All these axial bonds are present on plane. Sorry, I'm telling the reverse. All the equatorial ones are present on the plane. All the equatorial ones are present on the plane. Axial perpendicular, upwards, perpendicular downwards. So this axial is forming 90 with this equatorial. This axial is forming 90 with this equatorial. This axial is forming 90 with this equatorial. Similarly with this equatorial, right? Correct? So axial equatorial 90. Similarly, so this was equatorial, right? This equatorial. It was 90, axial equatorial. And similarly, axial was, how much axial? That's 180. 180. So if I ask you one thing, how many 90 degrees do you see here? How many 90 degrees do you see here? So 1, 2, 3, and 4. 4 in this plane. 4 in the equatorial plane. Between equatorial ones. 4. Similarly, this is forming 1, 2, 3, 4. 4 from upwards, 4 from downwards. So there are in total 12 90 degrees. 12 90 degrees, right? How many axial equatorial 90 degrees are there? Axial equatorial, 4 from top, 4 from bottom. 8. Right? 8. In total, there are 1290, out of which 4 are making from the top, 4 are making from the bottom, and 4 are present on the same plane. I hope you're getting what I'm trying to say. So this was your SF6, right? Guys, same goes for IF7. In case of IF7, let me show you directly. It is sp3d3, right? sp3d3. The geometry is pentagonal bipyramidal. Pentagonal bipyramidal. How do you show it at the end? See, this is for example iodine. 1 fluorine here, 1 fluorine here, 1 here, 1 fluorine here, right? And 1 fluorine here. Okay, this is pentagon, and 1 fluorine from the top, 1 from the bottom. This is pentagonal bipyramidal. This pentagonal bipyramidal. This pentagonal bipyramidal. So first of all, this bond angle present on the equatorial plane. This is 72 degree here, and this with this is 90. This with this is 90, right? So how many 72 degrees do you see here? 172. Second, third, fourth, fifth. So 572 degrees here between equatorial, right? How many axial equatorial? Axial equatorial is 90. How many 90s do you see? 1, 2, 3, 4, 5. 5 from top, 5 from bottom. So 10 90 degrees, which are between axial equatorial. And how many 180 degrees do you see? 180 degrees are 1 in number. Or let me just write it like this. 180 degrees are basically formed between axial and axial bonds. This can be asked. And this particular geometry, what do you call this as? Pentagonal bipyramidal geometry. I hope all this stuff is clear. I hope all this stuff is clear. Now guys, since you are familiar with hybridization, now there are a few more things which I am going to tell you now. Hybridization through structure directly. Hybridization through structure. How do we get the hybridization through structure? Understand. For example, I've got the molecule like this. Okay. Let's say I've got the molecule like this. Let's say you've got the molecule like this, right? For example, you've got the molecule like this. Now, if you talk about this particular carbon, how many valence electrons carbon has? 4, right? How many sigma it's forming? 1, 2, 3, 4. 4 sigma. It's forming 4 sigma. It had 4 valence electrons. Out of 4 valence electrons, I would say it has utilized all those 4 electrons. So no lone pair. So steric number is 4. Steric number 4 means hybridization of this carbon is sp3. Similarly, hybridization of this carbon is also sp3. Okay. Talk about this carbon. How many sigma it's forming? 1, 2, 3. 3 sigma. How many lone pairs? It had in total of 4 valence electrons. And it has utilized 1, 2, 3, 4. It has utilized all the 4. So there is no lone pair. So 3 plus 0 is 3. Steric number 3. Steric number 3 means sp2. Steric number 3 means sp2. Similarly, this carbon also undergoes sp2 hybridization. Similarly, you can calculate for this carbon, it will be sp. This carbon will be also sp. Right? If you talk about this particular nitrogen, nitrogen had 5 valence electrons. How many sigma it's forming? 3 sigma. How many lone pairs it has? 1 lone pair. 3 plus 1 is 4. Steric number is 4. If steric number is 4, hybridization involved is sp3. So hybridization of this nitrogen is sp3. Similarly, 2 sigma bonds, 2 lone pairs, steric number 2 plus 2, 4, hybridization sp3. Correct? All clear? All clear, people? For example, a lot of questions are asked based on hybridization. A lot of questions are asked based on hybridization. Now, how do we calculate hybridations of different species? For example, let me write over here. Let me write over here. For example, I'm asking you to calculate hybridization of carbon in carbon dioxide. Let's say I'm asking you to calculate hybridization of xenon in XCF2. Let's say I'm asking you to calculate all the parameters of xenon in XCF4. Let's say you've got NH4 positive. Let's say you've got NO2 negative. Let's say you've got I3 negative. I3 negative. For example, you have got XCOF4. XCO2F2. Talk about hybridizations and geometry predicted through hybridization. See guys, first thing, carbon, how many valence electrons? 4. How many surrounding atoms? 2. So sigma bonds 2. How many lone pairs? Since oxygen is divalent, so carbon is forming 4 bonds. It had 4 valence electrons. It's forming 4 bonds. So it has utilized all the 4 valence electrons. So lone pair 0. Lone pair 0 means steric number 2. Steric number 2 means hybridization sp. Hybridization sp. Geometry predicted through hybridization is linear. Geometry predicted through hybridization is linear. Right? Similarly, XCF2. How many valence electrons with xenon? 8. How many sigma bonds? Terminal atoms, 2 sigma 2. Lone pairs. Out of 8 valence electrons, 2 have been utilized to form 2 sigma bonds. So there will be 6 valence electrons as such in the form of 3 lone pairs. So steric number, 3 plus 2, 5. Hybridization is sp3d. Geometry predicted through hybridization is trigonal bipyramidal. That is the geometry predicted through hybridization. Similarly, XeF4. XeF4. Xenon. How many valence electrons? 8. How many sigma bonds? 4. How many lone pairs? Out of 8 valence electrons, 4 are utilized to form 4 sigma bonds. So 4 electrons will be left as such in the form of 2 lone pairs. Steric number 4 plus 2, 6. Hybridization sp3d2. sp3d2. Geometry predicted through hybridization is octet. This is the geometry predicted through hybridization. Okay. NH4 positive. NH4 positive. Guys, these are the geometries predicted through hybridization. Okay. These are the geometries predicted through hybridization. See, nitrogen. How many valence electrons? It is supposed to have 5, but there is positive charge, so subtract it. So 4. How many sigma bonds? 4. Lone pairs. 4 valence electrons, 4 sigma bonds. So 0 lone pair. Steric number 4 plus 0 is 4. Hybridization is sp3. Geometry predicted through hybridization is tetrahedral. Okay. NO2 negative. How many valence electrons? It should have 5, but there is a negative charge. So plus 1 makes it 6. How many sigma bonds? Surrounding atoms 2, so sigma bonds 2. So lone pairs. Lone pairs. Nitrogen has 6 valence electrons, but it's attached with oxygen. Oxygen is diet. Oxygen forms double bond, right? So 2 oxygen atoms means technically 4 bonds. So out of 6, 4 bonds. So 2 electrons will be left as such on nitrogen in the form of a lone pair, in the form of 1 lone pair. So 2 plus 1, 3, steric number 3. If steric number 3, sp2 hybridization. Geometry predicted through hybridization is trigonal planar. Okay. For example, you have got I3 negative. I3 negative you can make like this, I2 negative. You can make it like this, I2 negative. Talk about this particular iodine, which you keep as the central atom. So 7 negative charge, so 7 plus 1 makes it 8. Sigma bonds means surrounding atoms, 2. Out of 8 valence electrons, 2 bonds are being formed. So 6 electrons will be left as such in the form of 3 lone pairs. So 3 plus 2, 5. Steric number is 5. If steric number is 5, hybridization is sp3d. Geometry predicted through hybridization is trigonal bipyramidal. XeOF4. XeOF4. How many valence electrons? 8. How many terminal atoms? 5. Out of 8 valence electrons, how many have been utilized? 4 with 4 single bonds with fluorine and 1 double bond with oxygen. So 4 plus 2 makes it 6. Out of 8 valence electrons, 6 are used. So 2 will be left. 2 will be left in the form of a lone pair. 5 plus 1 steric number makes it 6. Steric number 6 means sp3 d2. Right? This you can consider as the homework and solve this. Perfect. And guys, there is one thing which you need to remember about hybridization. That's important, okay? This is given in your NCERT as well. You need to remember this. Oxygen is divalent, right? Asha. Hybridization of certain species. PCl5 when present in solid state. PCl5 when present in solid state exists as PCl4 positive, PCl6 negative. This phosphorus will show separate hybridization. This phosphorus will show separate hybridization. Okay. Similarly, PBr5 in solid state. What will be the hybridization of this phosphorus? Basically, PBr5 solid exists as PBr positive dot Br negative. XeF6 solid, it exists as XeF5 positive dot F negative. Right? N2O5 solid exists as NO2 positive, NO3 negative. I2Cl6 liquid exists as ICl2 positive, ICl4 negative. Similarly, I2 exists as I3 positive, I3 negative. So, whatever atoms I've underlined, you should be in a position to calculate their hybridizations. So, this cationic part, hybridization of phosphorus in the cationic part. Hybridization of phosphorus in the cationic part. How you will calculate? In the cationic part, if you see, how many valence electrons phosphorus have? 5 minus 1, because there is positive, 5 minus 1, 4. Sigma bonds here will be just 4. Lone pairs on phosphorus will be 0. Steric number will be 4 plus 0, 4. Hybridization will be sp3. So hybridization of phosphorus in cationic part is sp3. Now hybridization of phosphorus in anionic part. How many valence electrons this phosphorus will be having? 5 plus 1, 6. Sigma bonds, 6. Because it's forming 6 sigma bonds. Lone pairs, 0. Steric number 6 plus 0, 6. Hybridization sp3, d2, right? So this phosphorus which is present in the anionic part, it shows sp3, d2. This phosphorus in the cationic part, it shows sp3, right? Similarly, my dear students, you have to remember all these compounds and the way they exist, and accordingly you can calculate hybridization of each species. Did you understand this? Did you understand this, people? Say yes or no in the chats quick. Did you understand this particular point which I said? I believe you can easily calculate hybridization of every species, whatever I have underlined. For example, you have got I3 positive, I3 negative. Let's calculate the hybridization of iodine and I3 positive. Then let's calculate the hybridization of iodine and I3 negative. For example, I've got I3 positive. I3 positive can be written as I2 positive. Simple. Similarly, I3 negative can be written as I2 negative. Rest all the procedure is same. Valence electrons with iodine. 7, there's the positive charge, so minus 1 comes out to be 6. Valence electrons with this iodine, 7 plus 1 comes out to be 8. Sigma bonds here, terminal atoms 2. Sigma bonds here, terminal atoms 2. Lone pairs here. Out of 6 valence electrons, 2 have been neutralized. So 4 will be left as such on this iodine in the form of 2 lone pairs. So 2 lone pairs here. Similarly, 8 minus 2, 6. 6 divided by 2 is 3. 3 lone pairs. Steric number is 4 here. Steric number is 2 plus 2, 4. Here the steric number is 5. Steric number 4 means sp3 hybridization. Steric number 5 means sp3d hybridization. So iodine of the cationic part here shows sp3. Iodine of the anionic part shows sp3d. That is the point. Yeah? Got it? Similarly, you can calculate the rest of the species as well. This PBr4 positive, phosphorus, 4 valence electrons, 4 sigma bonds, 0 lone pair, so sp3. This xenon, 8 minus 1, 8 minus 1 comes out to be 7. So 5 sigma, 1 lone pair, 5 plus 1, 6, sp3d2. This nitrogen, 5 minus 1, 4, 2 oxygen, double bonds. So 2 sigma, 0 lone pair because everything gone. 2, so it's sp. This nitrogen, 5 minus 5 plus 1 comes out to be 6. 3 oxygen atoms, divalent, so 3 2s are 6. So 3 sigma, 0 lone pair, sp2. This iodine, you can easily calculate. 7 minus 1 is 6. So 2 sigma, 2 lone pairs, right? 2 sigma, 2 lone pairs. So sp3, ICl4 negative. 7 plus 1, 8. 4 sigma, 2 lone pairs. 4 plus 2, 6. sp3d2. And rest of the things we have already calculated. Let me first of all check this. ICl2 positive. 7 minus 1 is 6. Out of 6, 2 are sigma and 2 will be lone pairs. 2 plus 2, 4, sp3, right? So these are the hybridations of the underlined atoms. Perfect, guys. So with this, our hybridization topic is over. Perfect. Should we start, people? The VSEPR. Are you ready for the VSEPR, valence shell electron pair repulsion theory? I hope this particular part is clear. Yeah? I hope this particular part is clear. Okay, let me give you first of all a question, then I'll move on to the VSEPR. Let me see whether you got it properly or not. Dear students, for example, I'm writing NH3 plus H positive. What does it give? We have discussed it in coordinate bond, if you remember. It is going to form a coordinate bond with this H positive, right? Tell me the hybridization of these underlined atoms. Tell me the hybridization of these underlined atoms. Number 1. The second one I'm going to write again. This was the first question, for example. Let me give you the second one. BF3 plus NH3. It is again, since nitrogen has got the lone pair, it's going to form a coordinate bond. You know it. Tell me the hybridization of the underlined atoms here. Okay, in the first one, since nitrogen has got 3 sigma bonds and 1 lone pair, so 3 plus 1 makes it 4. Steric number is 4, it means sp3. Here nitrogen is forming 1, 2, 3, 4. Right? It's forming 4 sigma here. 4 sigma means again sp3 only. Right? 4 sigma means again sp3 only. So there is no change in hybridization over here for the nitrogen. If you look at the second case, boron here is forming 3 sigma bonds and it does not have any lone pair. So steric number 3, sp2. Here boron is forming 1, 2, 3, 4, 4 sigma. Perfect. So its steric number will be 4 and its hybridization will be sp3. So basically when BF3 gets converted into this species, its hybridization of boron changes from sp2 to sp3. This was once asked in your JEE examination. There were 3-4 reactions given like this and you were supposed to check in which of the following reaction hybridization of the underlined atom changes. So hybridization of the underlined atom changes here. Okay, I hope this is clear to everyone. I hope this is clear to everyone. Right? I hope this is clear to everyone. Now I'm moving on to the valence shell electron pair repulsion theory. My dear students, this valence shell electron pair repulsion theory, let me tell you, it gives us the idea about the actual shape of a molecule. It is going to give us the idea about the actual shape of the molecule. Point number one. Point number one. Point number two. For example, I'm taking NH3 molecule over here. Let's say I'm taking NH3 molecule. Since you know nitrogen has got 5 valence electrons. Out of 5, it is using 3 of its valence electrons to form 3 sigma bonds. There'll be 2 electrons left as such on nitrogen. Okay, there'll be 2 electrons left as such on nitrogen, which have not participated in the bonding, right? My dear students, these 2 electrons over here, what do I call them as? I call them as the non-bonding electrons. Non-bonding electrons. And these 3 electrons over here, I'll be calling them as bonding electrons. I call them as the bonding electrons. Let me tell you non-bonding electrons plus bonding electrons. Non-bonding electrons plus bonding electrons. Okay? I'll be calling them as valence shell electrons. I'll be calling them as valence shell electrons. First of all, these 2 electrons, they belong to the valence shell of nitrogen. These 2 electrons, they belong to the valence shell of nitrogen, but do not participate in the bonding. I call them as the non-bonding electrons. These 3 electrons, they belong again to the valence shell of nitrogen, but participate in the bonding. I'll be calling them as bonding electrons. Now, bonding plus non-bonding, I'll be calling them combinedly as valence shell electrons, right? As per VSEPR, my dear students, as per VSEPR, molecule acquires that shape. Molecule acquires the shape in which repulsions between the valence shell electrons, in which the repulsions between the valence shell electrons are minimized. And when repulsions are minimized, when repulsions are minimum, you would say stability is maximum. You would say stability is maximized. If repulsions are minimized, you would say stability is maximized. As per VSEPR is concerned, molecules, they try to acquire that shape wherein the repulsions between the valence shell electrons are minimized, hence stability is maximized. Okay, number one. Number two, as I told you, in the molecule, you have got two types of valence electron pairs. You have got two types of valence electron pairs. One you call as bond pairs, one is what you call as lone pairs. Let me give you the order of the repulsion. Let me give you the order of the repulsion of these valence shell electron pairs. My dear students, remember, lone pair repulsions are considered to be maximum, followed by bond pair lone pairs, followed by bond pairs. Lone pair repulsions are considered to be maximum, followed by bond pair lone pairs, followed by bond pairs. Okay? Simple. Remember, molecule tries to acquire that shape wherein the repulsions between valence shell electron pairs, they should be minimized basically, so that stability is maximized, right? Order of the repulsions, lone pair repulsions are considered to be maximum, followed by lone pair, followed by bond pair, right? Now, remember one important point, or let me write that on the next slide. Remember the next point that is important. My dear students, remember, whenever you'll be having a molecule, if in a molecule central atom does not have any lone pair, if in a molecule central atom does not have any lone pair, at that point of time, the geometry predicted through hybridization is same as that of the actual shape of the molecule. If in a molecule central atom does not have any sort of lone pair, at that point of time, whatever is the geometry predicted through hybridization, that is going to give you the actual shape of the molecule. For example, I've got CH4. Carbon here is the central atom. Carbon in total has got how many valence electrons? It has got in total of 4 valence electrons. How many sigma bonds it has here? 4 sigma bonds. So carbon has utilized all its 4 electrons to form 4 sigma bonds. So there will be no lone pair on carbon. Steric number is 4 plus 0, 4. Hybridization is sp3. Geometry predicted through hybridization, that is tetrahedral. Whatever is the geometry predicted through hybridization over here, that is going to be the actual shape of the molecule. So actual shape of CH4 is same what we have predicted through hybridization. Okay. For example, one more thing I'm going to let you know over here. Whenever you have got a molecule in which central atom has the lone pair, remember at that point of time, the geometry which is predicted through hybridization is not same as that of actual shape. At that point of time, actual shape would be different. Now this VSEPR, as I told you already, VSEPR is going to give us the idea about the actual shape of the molecule, right? Let's exactly get into the details of it so that you'll understand all of this in a better way. My dear students, first of all, our first category of molecules, I'm going to talk about those molecules which have got the steric number of 3. Let's first of all discuss those molecules which have got the steric number of 3. Yeah? Steric number 3 means hybridization is sp2. Hybridization sp2 means geometry which is predicted through hybridization, that is trigonal planar. So first of all, we are going to discuss about these molecules which have got the steric number of 3. Okay, which have got the steric number of 3. My dear students, what all possibilities are there to have steric number 3? The first possibility, let's say you have got a molecule wherein central atom is forming 3 sigma bonds and central atom has got 0 lone pairs. This is the first possibility for the steric number to be 3. 3 plus 0 makes it 3. The second possibility for the steric number to be 3 is if the central atom is forming 2 sigma bonds and there is 1 lone pair on the central atom. 2 plus 1 again makes it 3. Okay. These are the two possibilities. First of all, let me tell you, whenever you see this kind of the molecule, wherein the central atom has got 3 sigma bonds, it's forming 3 sigma bonds, 0 lone pair. Let me tell you, the type of the molecule is going to be represented by AB3L0. A represents the central atom. Central atom is forming 3 sigma bonds, and central atom does not have any lone pair. This particular molecule you are going to represent with AB2L1. AB2L1. A is the central atom, 2 sigma bonds, forming 2 sigma bonds, and 1 lone pair on the central atom. Okay? Now, people, 3 sigma bonds, 0 lone pair. We know, in such case, whenever central atom does not have any lone pair, at that point of time, whatever geometry is predicted through hybridization, that's going to give you the actual shape. Geometry and shape and actual shape here are going to be the same. They are going to be trigonal planar. Trigonal planar. Right? How do you represent it? This is A, this is B, this is one more B, and this one more B. This is your trigonal planar shape. This is your trigonal planar shape. Yeah? Am I clear with this? You can take its example as BF3. Okay, B is the central atom forming 3 sigma bonds, no lone pair on boron. And what is the bond angle here? I would say bond angle here will be 120 degree. Bond angle here is 120 degree. Let's exactly see the second set of molecules. First of all, I'm assuming we have got the central atom which is forming 2 sigma bonds, and central atom has got 1 lone pair. So the type of the molecule is AB2L1. First of all, AB2L1. What is the geometry which is predicted through hybridization? As per hybridization, steric number is 3. Hybridization is sp2. So geometry which is predicted through hybridization, that is trigonal planar. Perfect. But what about the actual shape? What about the actual shape of the molecule? How do you represent it? First of all, in order to make the actual shape of the molecule, what is the geometry predicted through hybridization? That is trigonal planar. It was supposed to be like this. This is what you call as trigonal planar geometry. Now, in this particular geometry, we have got 3 sigma bonds. But in reality, do we have 3 sigma bonds or 2? We have got 2 sigma bonds, 1 lone pair. So, remove one of the sigma bond, and instead of that, just put a lone pair. Perfect. Now, just hide this lone pair once. When you hide this lone pair, see how this molecule looks like. This molecule looks like bent. So, its actual shape is bent shaped. It is bent shaped over here. Yeah, it is bent shaped over here. Its actual shape is bent. Geometry predicted through hybridization is trigonal planar, but its actual shape is bent. Yeah, am I clear? Guys? Quickly, everyone in the chats. So this was the first set of molecules which have got wherein the steric number is 3, right? Let's move on to those set of molecules wherein steric number is 4. Steric number 4 means hybridization sp3. Geometry predicted through hybridization is tetrahedral. It is tetrahedral. Okay, it is tetrahedral. Now, how many cases do we have over here? When all we can have the steric number 4? The first possibility is if the central atom has got 4 sigma bonds and 0 lone pair. This is the first possibility. Second possibility, 3 sigma bonds, 1 lone pair. Third possibility, 2 sigma bonds, 2 lone pairs. Right? These are the 3 possibilities wherein we can have the steric number 4. Guys, 4 plus 0. The type of the molecule here is going to be AB4L0. This is the type of the molecule. Hybridization you already know. 4 plus 0. Steric number is 4. So hybridization is sp3. Central atom does not have any lone pair. That means geometry predicted through hybridization is same as that of its actual shape. And what is the geometry predicted through hybridization? That's tetrahedral. And its actual shape also will be the tetrahedral. Perfect. How do you show it in reality? This is, for example, A, this is B, this is B, this is one more B, and this one more B. Right? This is your tetrahedral geometry over here. Bond angle in this particular case is how much? 109 degree, 28 minutes. Perfect. Now, sigma 3 lone pair 1. So the type of the molecule I'll be represent like this, AB3L1. AB3L1. This is going to be the type of the molecule, AB3L1. Correct? Now, people, first of all, what is the hybridization? 3 plus 1, 4. Steric number 4, sp3. Already we know. What is the geometry predicted through hybridization? Geometry predicted through hybridization is tetrahedral. But will the actual shape be tetrahedral as well? Will the actual shape will be tetrahedral as well? If you talk about the actual shape and geometry predicted through hybridization is only same when the central atom do not have any lone pair. But here the central atom has got the lone pair. Now, in order to make the actual shape, what do I need to do? Make the geometry first of all. How the geometry looks like? Tetrahedral, right? Geometry looks like tetrahedral. So from this geometry, what you need to do is just remove one of the bond pair and instead of that, put a lone pair. Now, when you hide this lone pair, how it looks like? When you hide this lone pair, it looks like pyramid. It looks like a pyramid. So this particular shape is what we call as pyramidal shape. This is what we call as a pyramidal shape. As in case of what? As in case of NH3. NH3 is the example. NH3 is the example. Okay, NH3 is the example. Well, all the examples I'll let you know at the end. I'll be giving a lot of questions wherein you can predict shape and geometry as well. Okay, sigma 2, lone pair 2. What will be the type of the molecule? Type of the molecule is AB2L2. Okay, steric number is 2 plus 2, 4. Hybridization is sp3. Geometry predicted through hybridization is simply tetrahedral, you know it. Tetrahedral. So what about the shape? In order to make the shape, first make the geometry, right? From the geometry, remove 2 bond pairs. Instead of that, put 2 lone pairs. So let's say this is A. Let's say this is B. This is B. Let's keep one lone pair here. Let's keep one lone pair here. This shape is what you call as V-shaped, or you can call it as a bend-shaped again. V-shape. This is what you see in water. This is what you see in water. Perfect? Perfect, people? So this was the category of the molecules which show the steric number of 4. Similarly, let's have that category of the molecule which shows the steric number of 5. Steric number 5 means hybridization is sp3d. Geometry predicted through hybridization is trigonal bipyramidal. Trigonal bipyramidal. Okay. Now, what all possibilities are there to have the steric number 5? The first possibility is 5 sigma bonds, 0 lone pairs, right? Second possibility is 4 sigma bonds, 1 lone pair. Third possibility is 3 sigma bonds, 2 lone pairs. Okay. Fourth possibility is this is 3, this is 2. 2 sigma bonds and 3 lone pairs. These are the 4 possibilities wherein we can have the steric number of 4, steric number of 5. So my dear students, first of all, here the steric number is 5. So first of all, hybridization is going, first of all, the type of the molecule. Type of the molecule is going to be AB5L0, AB5L0, right? Geometry predicted through hybridization is going to be trigonal bipyramidal. Perfect. Trigonal bipyramidal. Perfect. What about the shape? I would say shape will also be trigonal bipyramidal only. Its actual shape. Why is that? Because the central atom does not carry any lone pair. How it looks like exactly? This, for example, A. This is B. This is B. And this is B. All these 4 atoms, they are present on the same plane. They are present on the same plane. There is one B perpendicular upwards, one B perpendicular downwards. Perfect. You call this particular geometry as trigonal bipyramidal geometry. You call this particular geometry as trigonal bipyramidal geometry. Right? Now, 4 sigma bonds, 1 lone pair. The type of the molecule will be AB4L1. Hybridization is again same. Steric number 4 plus 1, 5. Right? So hybridization is going to be same, sp3d. Here also the hybridization was same, sp3d. Everywhere hybridization is same, sp3d. Now, what is the geometry which is predicted through hybridization? It is trigonal bipyramidal. But what about the actual shape? Actual shape of the molecule. See, geometry which is predicted through hybridization, that was trigonal bipyramidal. Perfect. That was trigonal bipyramidal. Now, from the geometry, just remove one bond pair and put one lone pair. Remove one bond pair and put one lone pair. So let me remove this bond pair. It'll be like this. B, B, one more B, and here you have got a lone pair. And this shape is what we call as seesaw shape. This is what we call as seesaw shape, as we see in the molecule SF4. Okay? This was trigonal bipyramidal, as we see in the molecule PCl5. Right? PCl5. Look at the next category. The type of the molecule is going to be AB3L2. AB3L2. Steric number is again 3 plus 2, 5. So sp3d. sp3d. Geometry which is predicted through hybridization, that is trigonal bipyramidal. Right? But its actual shape would be different. Its actual shape would not be trigonal bipyramidal. What would be its actual shape? So, from the geometry, you can see 5 bond pairs, 0 lone pairs. But we have to keep 3 bond pairs and 2 lone pairs. 3 bond pairs and 2 lone pairs. So, remove 2 bond pairs here. When you remove 2 bond pairs, it's going to be like this. This is B, this is B, this is B. Here you are keeping one lone pair. Here also you are keeping one lone pair. So when you hide these lone pairs, it will be a T-shaped molecule. So it has got its actual shape is T-shaped one. Okay, T-shaped one. And its example is going to be, for example, BRF3. BRF3 is its typical example. 3 sigma bonds, 2 lone pairs. Correct? T-shaped one. Similarly, 2 sigma bonds, 3 lone pairs. The type of the molecule is going to be AB2L3. AB2L3. Steric number is going to be 3 plus 2, 5. So sp3d. Geometry is again the same. Trigonal bipyramidal. But what about its shape now? What about its shape now? See, in the actual geometry, there are 5 sigma and 0 lone pair. Right? So instead of 5 sigma, we have to keep 2 sigma and 3 lone pairs. So I'll be removing 3 sigmas. And which all sigmas I'll be removing here? See, this is A, B I'm keeping as such, P I'm keeping as such. I'm removing all the equatorial bonds with these, replacing them with lone pairs. When you hide these lone pairs, it looks like a straight, linear molecule. The actual shape of the molecule is linear, right? Actual shape of the molecule is linear, as we see in case of I3 negative. As we see in case of I3 negative. Right? As we see in case of I3 negative. So this was the set of the molecules which are showing steric number 5. Now, steric number 6. Molecules which have got steric number 6. Their hybridization has to be sp3d2. Geometry predicted through hybridization has to be octahedral. It has to be octahedral. Right? Now, what all categories will come under this? Let's see. First type of the category, 6 sigma, 0 lone pairs. Second category, 5 sigma, 1 lone pair. Third category, 4 sigma, 2 lone pairs. Right? These are the 3 set of the categories which come under steric number 6. Achha, by the way, one more thing. You must be thinking, why did I remove these 3 bond pairs and place 3 lone pairs here? I told you guys, molecule tries to acquire that shape wherein the repulsions between the valence shell electron pairs are minimized and stability is maximum. This is the shape wherein the repulsions between the valence shell electron pairs are minimized and stability is maximized. Similarly, this is the shape wherein the repulsions between the valence shell electron pairs are minimized, stability is maximized. Right? So I'm directly writing those shapes over here, wherein the repulsions are minimized and stability is maximized. Okay, we were talking about the steric number 6 now. Steric number 6 means over here it's going to be AB6L0. Hybridization is, it's already sp3d2. Geometry predicted through hybridization is octahedral, which is going to be its actual shape as well, because the central atom does not have any lone pair. And when the central atom does not have any lone pair, shape and geometry will be the same. So how it looks like finally? This A, this for example B, this is one more B here, this is one more B, and this one more B. All these 5 atoms are present on the same plane, right? So this is 1B perpendicular upwards, this 1B perpendicular downwards. How does it look like? It looks like an octahedron. It looks like an octahedron. Perfect. And this is what you see in SF6 molecule. This is what you see in SF6 molecule. Yeah. AB5L1. AB5L1. Hybridization again same. 5 plus 1, 6. sp3d2. Right? Geometry predicted through hybridization. You know it already. It's octahedral. But shape, actual shape here will be different now. Actual shape here will be different. It's AB5L1. So from the geometry, we have to remove one bond pair, right? And place a lone pair instead of that. So let me replace this bond pair over here. So this is A, B, this is B, this is B, and this is B. I'm writing it as such. This B I'm keeping as such. And instead of the B at the bottom, I'm keeping a lone pair here. Now hide the lone pair and see how it looks like. Hide the lone pair and see how it looks like. It looks like a square pyramid at the top, right? These five atoms, they are present on one plane. B is at the top. So it looks like a square pyramid. It looks like a square pyramid. It looks like a square pyramid. Perfect. Am I clear with this? Am I clear with this, people? These diagrams will directly come in your examination. Yes, 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 yes. I'll tell you the types of the questions which can be asked here. Just wait. Let me complete this first. Is it clear till here? Its example you can consider as BRF5. 5 sigma and 1 lone pair, right? Okay. This particular molecule is of the type AB4L2. Hybridization again same, sp3d2. Geometry predicted through hybridization, that is octahedral. What about its shape? See how it looks like. AB4L2, right? This is A, B, this is B, this is B, and this is B. So all these 5 atoms, they are present on one plane. Perfect. Lone pair at the axial position, one more lone pair at the axial position. Now, hide these lone pairs. How it looks like? It looks like a square planar molecule. It looks like a square planar molecule. It is square planar. Its example is XCF4. Perfect. 4 sigma bonds and 2 lone pairs on xenon. This is its example. So this was the category of steric number 6. Now, one last, that is steric number 7. Steric number 7 means sp3d3. Geometry predicted through hybridization is pentagonal bipyramidal. Pentagonal bipyramidal. Pentagonal bipyramidal. Now here you have got 2 categories. The first one, if there are 7 sigma bonds, 0 lone pairs. The second one, if there are 6 sigma bonds, 1 lone pair. The type of this molecule is going to be AB7L0. The type of this molecule is going to be AB6L1, right? Here, the hybridization is going to be same, sp3d3. Here also, the hybridization is going to be same, sp3d3, right? Geometry predicted through hybridization is going to be same, trigonal bipyramidal. Geometry predicted through hybridization is going to be again trigonal bipyramidal. Now here the actual shape is also going to be trigonal bipyramidal because the central atom does not carry any lone pair. How it looks like? This, for example, A. This is B here. This is B here. This is B. And this is B. This is, for example, one more B. So on the plane, they are forming a pentagon. There is one B at the top. There is one B at the bottom. So how does it look like at the end? It looks like a pentagon bipyramid. It looks like a pentagon which has got pyramid at the top as well as pyramid at the bottom. So it is a pentagonal bipyramidal shape. And this is shown by IF7. IF7, pentagonal bipyramidal shape. Now this one, what is the actual shape here? What is the actual shape here? So what you'll be doing, you'll be removing one of the bond pairs here. Instead of that, you'll be placing a lone pair. So it's going to be like this. Here you are going to keep a lone pair. Here you are going to keep a lone pair. Just a second. This is 1B at the top, 1B at the bottom. This particular shape is what you call as distorted octahedron. This is what you call as distorted octahedron. This is the shape of the molecule of the type AB6L1. So my dear students, why did I tell you all these shapes? What is the reason behind that? Because the questions are directly asked. What kind of questions are asked? For example, I'm giving you certain molecules. You just tell me everything about them. Whatever things you can, predict, just tell me all the things. I'm starting with the molecule XCF2. Give me all the things about XCF2. Give me all the things about XCF4. Give me all the things about XCO2F2. Give me all the things about ICl2 negative. Okay? Give me the complete information. See, first example I'm going to show you, and you will understand how do we derive all the information. Understand. How many valence electrons are there with xenon? 8. How many surrounding atoms? 2. So there will be 2 sigma bonds. Xenon had 8 valence electrons. It's forming 2 sigma bonds with chlorine. So it is utilizing 2 electrons. So there will be 6 valence electrons as such on xenon in the form of 3 lone pairs. Steric number will be 3 plus 2, 5. Type of the molecule is going to be AB2L3. Right? Geometry predicted through hybridization. Steric number 5. First of all, let me write hybridization is steric number is 5. Hybridization is sp3d. Geometry predicted through hybridization is going to be trigonal bipyramidal. Actual shape of the molecule will be what? Actual shape. What will be the actual shape? 2 sigma 3 lone pairs. 2 sigma 3 lone pairs. It's going to be linear. Right? AB2L3, its actual shape is linear. Correct? Yeah? Now, XCOF4. Have a look on XCOF4. This is xenon, the central atom. How many valence electrons? 8. How many surrounding atoms? 4 plus 1, 5. How many lone pairs? See guys, xenon is forming 4 single bonds with 4 fluorine atoms. So it is utilizing 4 valence electrons. And there is one oxygen as well. Oxygen is divalent. So xenon will be forming double bond with oxygen. So 2 valence electrons, again it's utilizing there. 4 utilizing with 4 fluorine atoms. 2 utilizing with 1 oxygen atom. So 4 plus 2, 6. So out of 8 valence electrons, xenon is utilizing 6 valence electrons. So there will be 2 valence electrons left as such on xenon in the form of a lone pair. So 1 lone pair. Type of the molecule, AB5L1. Steric number, 5 plus 1, 6. If steric number is 6, hybridization, sp3d2. sp3d2. Geometry predicted through hybridization has to be octahedral. Actual shape, it is AB5L1. It is going to be square pyramidal. It's going to be square pyramid. AB5L1 we have discussed, right? AB5L1. AB5L1, square pyramid. Correct? So all this stuff you can easily do. All this stuff you can easily do. One example I'm showing, one more you will do on your own. This is something which you will do on your own. I'm moving on to ICl2 negative. How many valence electrons iodine has? 7 plus 1 makes it 8. How many surrounding atoms? 2. So sigma bonds 2. Out of 8, it is utilizing 2. So 6 will be left as such on iodine in the form of 3 lone pairs. Steric number is 3 plus 2, 5. Hybridization will be sp3d. Geometry predicted through hybridization has to be trigonal bipyramidal. Type of the molecule is going to be AB2L3. AB2L3. Actual shape of the molecule will be what? AB2L3. It's again going to be linear only. Right? It's again going to be linear only. Perfect? This is something which you can try on your own. All this stuff you can easily do. Okay, all this stuff you can easily do. I believe this is super clear to everyone again. Right, people? All clear with this? All clear with this? Well, there are few more applications of this VSEPR which I'll tell you afterwards. When I'll teach you bond angle separately, bond length separately, bond parameters, right? I'm keeping that as such for now. We'll see that at the end. Okay? Now we are going to move on to the molecular orbital theory, people. Molecular orbital theory. So before starting the molecular orbital theory, which is very, very, very important, so tell me in the chats whether all the things which we have discussed till now are super clear to you or not. Tell me in the chats whether all the things, whatever things we have discussed till now, are super clear or not. How many topics are left? 3 topics are left. 3 topics are left. Ideal and non-ideal. What ideal, non-ideal? What ideal, non-ideal you are talking about? Yeah? What ideal, non-ideal you are talking about? Let me know. We have discussed ideal, non-ideal in the chapter solutions, right? We have discussed that in detail. So are you guys all alive? Let me know in the chats first. Are you all alive? Like properly alive? Have some water first. Have some water because this topic is very important. Have some water. You'll be like in your senses properly. Have some water first. Have some water first. Brain is not functioning properly. Go wash your face once and come back. Brain will start working. Someone's water ran out, huh? Yes. Let's start the molecular orbital theory then. Yeah? Just give me a second. Okay. All right. Perfect. So let's get to know now about the molecular orbital theory. My dear students, first and the important point, this MOT, molecular orbital theory, this MOT, let me tell you, it is basically the extension of valence bond theory. It is the extension of valence bond theory. It is the extension of valence bond theory. What valence bond theory used to say? As per valence bond theory, atomic orbitals of the bonding atoms, they used to overlap, right? They used to overlap and they used to lead to the formation of what? covalent bond. Similarly, as per molecular orbital theory is concerned, atomic orbitals of the bonding atoms, they are going to combine to form the molecular orbitals. As per MOT is concerned, it is the extension of VBT. VBT used to tell us atomic orbitals of the bonding atoms, they overlap and lead to the formation of molecular orbitals, lead to the formation of covalent bonds, right? Or I can say molecular orbitals. MOT also tells the similar thing. MOT also tells the similar thing. Atomic orbitals of the bonding atoms, they are going to combine and they are going to lead to the formation of molecular orbital. One more point I'm going to add over here. Number of atomic orbitals combined, will be equal to the number of molecular orbitals formed. Number of atomic orbitals combined is equal to number of molecular orbitals formed. My dear students, for example, I have got atomic orbital of one atom, and similarly, I have got atomic orbital of one more atom. Let's say I have taken two bonding atoms, right? Two bonding atoms I have taken. The atoms which have to combine and form a bond, basically. The atoms which have to combine and form a molecule, basically. So, the atomic orbitals of the bonding atoms, as per MOT is concerned, they are going to combine and they will lead to the formation of what? They lead to the formation of molecular orbitals. Number of atomic orbitals combined is equal to number of molecular orbitals formed. So, two atomic orbitals are combining here. So, two molecular orbitals will be formed, out of which one will be called as bonding molecular orbital, one will be called as anti-bonding molecular orbital, right? One will be calling as bonding molecular orbital, one will be called as anti-bonding molecular orbital. Let me tell you people, bonding molecular orbital, its energy is less and stability is more. Why is that? You'll get the idea in some time. Bonding molecular orbital, its energy is less, stability is more. Anti-bonding molecular orbital, its energy is more and stability is less. Its energy is more and stability is less. Okay? Its energy is more and stability is less. As per MOT is concerned, the atomic orbitals of the bonding atoms, they are going to combine and they are going to lead to the formation of molecular orbitals. Number of atomic orbitals combined is equal to number of molecular orbitals formed, out of which some are going to be bonding, some are going to be anti-bonding. Bonding molecular orbitals are the ones which have got lesser energy, more stability. Anti-bonding molecular orbitals are the ones which have got more energy, lesser stability. For example, have a look. Here. See guys, let's say I've taken 1s atomic orbital here. This is 1s atomic orbital of some atom. Similarly, I've taken 1s of one more atom. I've taken two atoms basically, which are the bonding atoms, which are going to form a bond, which are going to form a molecule, right? So, atomic orbital of one bonding atom, atomic orbital of one more bonding atom. 1s and 1s I'm taking. As per your MOT, they are going to combine. They are going to lead to the form of molecular orbitals, right? One will be called as bonding, one will be called as anti-bonding. One is going to be bonding molecular orbital, one is going to be anti-bonding molecular orbital. Now, my dear students, understand one thing. As per your VBT, SS used to do the head-on overlap. Which bond used to get formed? Sigma bond used to get formed. So, this molecular orbital over here, the bonding molecular orbital, I'll be calling it as sigma 1s. The anti-bonding molecular orbital which is formed here, this is what I'll be calling as sigma star 1s. Okay? One I'll be calling as sigma 1s, one I'll be calling as sigma star 1s. Perfect? Right? For example, let me take one more example. Let's say this is one of the atomic orbital of one atom, one more atomic orbital of one atom. Perfect? Let's call this as 2p. Perfect? For example, 2py, 2py. Okay? Now, if these two atomic orbitals will be combining, they'll be forming two molecular orbitals. One will be called as bonding molecular orbital, one will be called as anti-bonding molecular orbital. Perfect? Bonding, anti-bonding. How do I represent bonding here? Since These are parallel basically. And in VBT, we have discussed parallel overlapping leads to the formation of pi, right? So this is what I'll be calling as pi 2py. And this is what I'll be calling as pi star 2py. Nothing else. That's all. One is going to be pi 2py, one is going to be pi star 2py. Perfect. For example, you have got this kind of a scenario. For example, you have got this kind of the scenario. This is one of the p orbital. This, for example, one more p orbital. Perfect. One p orbital, one p orbital. Since two p orbitals are combining, they'll lead to the formation of two molecular orbitals. One is going to be bonding, one is going to be anti-bonding, right? How do I represent bonding here? Since it is axial one, axial leads to the formation of sigma. So let's call this as 2p. Let's call this as 2p. So this is going to be your sigma, for example, 2pz. Sigma 2pz. This is going to give to the formation of sigma star 2pz. Perfect. Simple and basic. So number of atomic orbitals combined is equal to number of molecular orbitals formed, out of which one will be bonding, one will be anti-bonding, right? Now, my dear students, once the atomic orbitals of the bonding atoms are going to combine, once they lead to the formation of molecular orbitals, right? Once we get the molecular orbitals, as molecular orbitals are formed, comma, we need to fill the molecular orbitals. We need to fill the molecular orbitals with the electrons. As molecular orbitals are formed, we need to fill these molecular orbitals with the electrons in accordance to Abbas principle, Pauli's exclusion principle, as well as Hund's rule. And once we fill electrons in these molecular orbitals, then, my dear students, what all things we can do? Let's have a look. We can calculate bond order of a molecule, basically. Bond order means simply the number of bonds existing between two atoms. Bond order in a diatomic species means number of bonds between two atoms, right? Bond order is calculated as half of number of electrons in bonding molecular orbital minus number of electrons in anti-bonding molecular orbital. This is how you calculate bond order. Number of electrons in bonding minus number of electrons in anti-bonding molecular orbital. I'll show you this in detailed format in some time, right? Now, remember, if the bond order comes out to be 1, it represents a single bond between two atoms. That means between two atoms, there is a single bond. If bond order of the species comes out to be, let's say, 2, that means there's a double bond present between the atoms. If the bond order comes out to be 3, it means that there's a triple bond between the atoms. If by chance bond order comes out to be less or equal to 0, that means molecule does not exist. Molecule is not viable. Molecule does not exist. Molecule is not viable. And my dear students, once we get the bond orders of different species, what kind of other information do we get? Remember, bond order means the number of bonds between two atoms. More the bonds, more the attraction between two atoms. Bond order is directly proportional to bond strength. It is directly proportional to bond strength. More the bond strength, more is going to be the bond dissociation energy. More energy is required to break that bond. More the bond dissociation energy, or I'll say more the bond order, lesser is going to be the bond length. So from bond order data, anything can be discussed. I'll explain this in detail in some time. First of all, I'm making you write all this stuff in detail, right? All this stuff in detail. My dear students, one more point I'm giving you over here. then we'll see its application one-on-one. See, if the bond order of two species is same, if the bond order of two species is same, how do we check which one is more stable or not? If the bond order of two species is same, how do we check which one is more stable? For two species which have got same bond order, if number of electrons in anti-bonding molecular orbital are greater than number of electrons in bonding molecular orbital, if number of electrons in anti-bonding are greater than that of number of electrons in bonding, its stability of that particular species will be less. If number of electrons in anti-bonding are less than that of number of electrons in bonding, you say the stability of that species is going to be more. This is one more thing, but this is only valid for those species which have got same bond order. You will see after few minutes, you will see there will be some species which will be having same bond order, yet their stabilities will be different, right? That is explained by this particular point. That's explained by this particular point. Now, people, as I told you few things. Energy of anti-bonding molecular orbital is greater than that of energy of bonding. As number of electrons in bonding molecular orbital increases, stability increases. As the electrons in anti-bonding molecular orbital increases, stability decreases. While filling electrons in molecular orbitals, Abbas principle, Hund's rule, Pauli's exclusion principle are followed, right? This is something which we discussed. Bond order is equal to by this formula. A bond order is this. We have discussed this in detail. Now, let's try to understand one more thing. My dear students, remember, as per molecular orbital theory is concerned, atomic orbitals of the bonding atoms, they combine. They lead to the formation of molecular orbitals. Now, which atomic orbitals of bonding atoms combine? Those atomic orbitals on the bonding atoms, they combine and form the molecular orbitals, which have got almost the similar energy. For example, 2s of one atomic orbital will combine, 2s of one atom will combine with 2s of one more atom, right? And will form two molecular orbitals. They have got same energy. 2s-Tp, almost same energy. They can combine. 2s and 5p, they cannot combine, right? So the combining atomic orbitals must have similar energy, almost similar energy, right? They should have almost similar energy. This is the criteria for combination of these atomic orbitals. Perfect? Perfect, guys? Now let's try to understand this in detail. My dear students, as I told you, let me take a blank slide over here, just a second. Yeah. As I told you, basically, as per MOT, atomic orbitals of the combining atoms, they combine and lead to the formation of molecular orbitals, right? If two atomic orbitals are combining, it will lead to the formation of two molecular orbitals. One will be bonding, one will be anti-bonding. Now we are going to actually see how these molecular orbitals are formed, how these atomic orbitals combine and lead to the formation of molecular orbitals. Let's get to know about that first. So, we are going to discuss the combination of atomic orbitals to form the molecular orbital. My dear students, how atomic orbitals combine and lead to the formation of molecular orbitals? It is explained by LCAO. What is LCAO? LCAO, it stands for linear combination. It stands for the linear combination of atomic orbital. And what linear combination of atomic orbitals says? See, we know when two atomic orbitals of the combining atoms combine, they lead to the formation of two molecular orbitals. One is called as bonding molecular, one is called as anti-bonding molecular. As per LCAO, bonding molecular orbital is formed by the constructive interference. Anti-bonding molecular orbitals are formed by the destructive interference. by the destructive interference. What exactly it means? What exactly it means? What exactly it means? So first of all, let's get to know the formation of bonding molecular orbitals. Let's get to know the formation of bonding molecular orbitals as per constructive interference. As per constructive interference. See guys, understand. As per constructive interference. Formation of BMO as per constructive interference. Now guys, see what this linear combination of atomic orbitals is all about. As per linear combination of atomic orbitals is concerned. As per linear combination of atomic orbitals is concerned. Or guys, let me just tell you one more important thing. Just a second. Do not take a note of it. See guys. As per linear combination of atomic orbitals, see, this atomic orbital I'll be representing by a wave like this. This is the wave corresponding to this atomic orbital, whose amplitude I'm keeping as psi a. Let's say the wave corresponding to this atomic orbital is this. This is the wave corresponding to this atomic orbital, right? Its amplitude is psi b. It is amplitude is psi b. Perfect. Psi a, psi b. Or leave the amplitudes aside now. Leave the amplitudes aside for now. Let me first of all give you the general idea. See, the wave corresponding to this atomic orbital, let's say this is the wave. Similarly, the wave corresponding to this atomic orbital, let's say this is the wave. Perfect. Now, my dear students, you would have seen about waves. Waves either show constructive interference or they show destructive interference. Waves either show constructive interference or they show destructive interference. How do I represent constructive interference? See, positive, negative, positive, negative. Same sign on same side. So, this is going to show you the constructive interference. Or you can call it as in-phase interference. In-phase interference, right? Let's call this as positive. Let's call this as negative. Let's call this as negative. This as positive. Opposite sign on same side. Opposite sign of on same side. This is something which I call as over here destructive interference, or you call it as the out of phase interference. Now, my dear students, during constructive interference, during in-phase interference, the amplitude of the resulting wave. See, when these two waves are going to show interference, right? They are in same phase. They are in phase. They are going to show constructive interference. In constructive interference, the amplitude of the resulting wave is maximized. The amplitude of the resulting wave is maximized. And this resulting wave, it corresponds to what? It corresponds to bonding molecular orbital. Because during constructive interference, bonding molecular orbital gets formed. Now, this particular scenario represents destructive interference. In destructive interference, the amplitude of the resulting wave is minimized. Amplitude of the resulting wave is minimized in destructive interference. And due to destructive interference, anti-bonding molecular orbital is formed. Anti-bonding molecular orbitals are formed. Is this clear? So basically, due to constructive interference, bonding is formed. Due to destructive interference, anti-bonding is formed. Is this clear to everyone? Let me know once in the chats. Now, in detail, we are going to discuss about constructive interference through which bonding molecular orbitals are formed. Then we are going to discuss about destructive interference due to which anti-bonding molecular orbitals are formed. Okay? Let's get into the details of this one by one. So first of all, we'll see the formation of molecular orbitals is explained by linear combination of atomic orbitals. And due to constructive interference, which atomic orbitals are formed? Due to constructive interference, bonding molecular orbitals are formed. Okay? And what happens during constructive interference? During constructive interference, two waves combine which have got same phase, right? And the amplitude of the resulting wave is maximized. For example, let's say this is atomic orbital 1 plus atomic orbital 1. Okay? Let's say now this is the wave corresponding to atomic orbital 1. Its amplitude is psi. This is the wave corresponding to atomic orbital 2. Its amplitude is psi b. For example, these waves are in same phase. Let's say this is positive, negative, negative. They are in same phase. So over here, I'm showing atomic orbitals. They are combining, right? The waves corresponding to atomic orbitals, they are going to show the constructive interference over here. I'm just showing you the constructive interference, or you call this as in-phase interference. Constructive interference, in-phase interference, due to which bonding molecular orbital is formed. Now, since these two waves which are corresponding to these atomic orbitals, right? These are the waves corresponding to these atomic orbitals. They are going to show the constructive interference over here because they are in same phase. They are in same phase over here. They are going to show the constructive interference. And due to constructive interference, the amplitude of the resulting wave is maximized. So, I would say the amplitude of the resulting wave is nothing but psi A plus psi B. This is the amplitude of the resulting wave. Perfect. My dear students, if I take square of psi A, what this psi A square indicates? Psi A square indicates probability of finding the electrons around the nucleus in atomic orbital A. Psi B square indicates probability of finding the electrons in the atomic orbital B. Similarly, if I take the square of this amplitude, this is going to give us the probability of finding the electrons in the molecular orbital. Which molecular orbital this is? This is the wave corresponding to bonding molecular orbital. Right? Now, my dear students, if you slightly elaborate it, can I say this is going to be psi A square plus psi B square plus 2 times psi A psi B? Right? So think logically. I took two atomic orbitals. These are the waves corresponding to these two atomic orbitals. Now, these waves can show constructive interference or can show destructive interference. Right now, I'm showing the constructive interference. Due to constructive interference, the amplitude of the resulting wave is maximized. This wave is corresponding to the molecular orbital. Which molecular orbital? The one which is formed through constructive interference. Which one is formed through constructive interference? It is the bonding molecular orbital. So, this is the wave corresponding to bonding molecular orbital. If I take square of amplitude here, psi square gives us the probability of finding the electron in atomic orbital A. Probability of finding the electron in atomic orbital B. What should be normally the probability of finding the electron here? It should be psi A square plus psi B square. The probability of finding the electron here in this molecular orbital should be psi A square plus psi B square. But look at it carefully. It is psi A square plus psi B square plus 2 times psi A psi B. Plus 2 times psi A psi B. What does it mean? See guys, since two atomic orbitals are combining, forming the molecular orbital, this is giving us psi A square, probability of finding the electron in the atomic orbital A, probability of finding the electron around the nucleus in the atomic orbital B. Now, if the waves are combining, if the atomic orbitals are combining to form the molecular orbital, so the probability of finding the electron in the molecular orbital should be psi A square plus psi B square. But how much it is? Psi A square plus psi B square plus 2 times psi A psi B. It should have been psi A square plus psi B square, but it is psi A square plus psi B square plus 2 times something, right? So can I say probability of finding the electron between the nuclei, probability of finding the electron between the nuclei in the molecular orbital, has increased by this much of amount, 2 times psi A psi B. My dear students, if in this molecular orbital, probability of finding the electron has increased, so I would say it in other words, I can say electron density between the nuclei in the molecular orbital has increased. If electron density between the nuclei has increased, repulsions between the nuclei would have minimized, stability would have maximized, right? Repulsions minimized means energy minimized, stability maximized, right? That's why I told you the bonding molecular orbital which we get, its energy is less and stability is more. Why? Because the electron density between the nuclei is increased by this much of amount. If electron density between the nuclei is increased by this much of amount, what does that mean? That means repulsions between the nuclei would be minimized. Energy of the system would be minimized. Stability of the system would be maximized. So this is what we call as linear combination of atomic orbitals, right? So this is first interference which I showed you, constructive interference. So during constructive interference, when atomic orbitals combine, perfect, through constructive interference, bonding molecular orbital is formed, right? in which the probability of finding the electron between the nuclei was supposed to be psi plus psi b, psi square plus psi b square, but it is psi square plus psi b square plus 2 times psi b. So the probability of finding the electron between the nuclei in the bonding molecular orbital has increased, due to which repulsions between the nuclei would have decreased, right? Energy of the system would have decreased, stability would have increased. So this molecular orbital, right, which we get over here, that's called as bonding molecular orbital, whose energy is less, stability is more. Okay. So this was your constructive interference. This was your constructive interference. Perfect. This was your constructive interference. Now guys, understand. Now guys, understand. For example, as I told you, when two waves combine in same phase, electron density around the nuclei increases in the molecular orbital. Or you can say electron density between the nuclei in the molecular orbital increases when there is in-phase interference. Okay? Due to which molecular orbital is formed? Bonding molecular orbital is formed. Now let's have its clear visualization. See guys, let's say this is the atomic orbital 1, this is the atomic orbital 2. I've given the signs, positive, negative, positive, negative. I've shown same sign, same side. Same sign, same side means constructive interference, means in-phase interference. In-phase interference. Now, during constructive interference, the electron density between the nuclei of the molecular orbital increases. So what would happen? We have to show the molecular orbital in such a way that we have to represent electron density between the nuclei the maximum. So understand it like this. Imagine as if this part of the electron density has shifted towards this side. This part of electron density has shifted towards this side, due to which a molecular orbital has got formed in which the electron density in the middle is maximum. Okay, electron density here is maximum. So this was negative, I'm keeping it as negative. This is negative, I'm keeping this as negative. Positive, positive, I'm keeping this as positive here. So which molecular orbital this is? Since this is SS axial, so this is forming sigma 1s. What do I call this molecular orbital as? Bonding molecular orbital, which is formed through constructive interference. Okay, constructive interference. My dear students, over here in this molecular orbital, can you draw any plane on which there will be no electron density? Do you see? Can you draw any plane in this way, that way, on which there will be no electron density? You cannot draw any plane like that. So in case of your sigma 1s, nodal planes are, there is no nodal plane in sigma 1s. Okay, let's have a look on one more. Let's say you have got 2pz, 2pz. I have kept same sign on same side, right? So which interference I'm showing you over here? Constructive interference, in-phase interference. So which molecular orbital is going to get formed? Bonding molecular orbital. So between the nuclei, we have to increase the electron density. Between the nuclei, electron density has to increase. So it is as if this electron density in the lobe has shifted in this direction. The electron density in the lobe has shifted in this direction, as if, right? So how it looks like at the end? This is how it's going to look like at the end. Positive, positive. So in the middle, I'm showing positive. This was negative. This is also negative. So negative. So first of all, is this axial? Yes, axial. Axial leads to the formation of sigma. So I'll be calling this as sigma 2pz. Which molecular orbital this is? This is bonding molecular orbital. This is bonding molecular orbital. Tell me one thing. Can you draw any plane over here on which there will be no electron density? You cannot draw any plane on which there is no electron density. So here again, nodal plane is 0. Here again, nodal plane is 0. This is how when 2p combines in phase. Okay. I'm showing you the formation of bonding molecular orbitals right now. I did not show you the formation of anti-bonding till now. Okay. Perfect. Now, see guys, for example, 2py. Let's say positive, positive, in phase, constructive, in phase. In phase. What do I have to show? Electron density should increase. So what is going to happen? What is going to happen, people? Over here, understand. Over here, understand. First of all, is this going to be axial or parallel? It is parallel. Parallel leads to the formation of pi. So the bonding molecular orbital which we get over here, That's what we call as pi 2 py. Pi 2 py. Now, how you are going to show it? Imagine this lobe shifted in this direction, this lobe shifted in this direction, this lobe shifted in this direction, this lobe shifted in this direction. So over here, I'm showing one plane on which there is no electron density. Above this plane and below this plane, you'll find electron density. This is how your pi 2 py bonding orbital will look like. And there is this plane in the middle on which there is no electron density. So this plane I'm calling as nodal plane. So there is one nodal plane which we get over here in this bonding molecular orbital 2py. This is your pi 2py in which there will be one nodal plane. Okay, one nodal plane. Perfect. This is how it will look like actually. This is how it will look like actually. Nodal plane, electron density at the top, electron density at the bottom. Okay, perfect. Now similarly, let's say this is your dxy, dxy. For example, this is your 3dxy, this is also your 3dxy. I've shown same sign on same side, positive, positive, negative, negative, right? So what do I have to show? In constructive interference, the electron density between the nuclei should increase. So I would say this lobe should shift its electron density in this one. This lobe should shift its electron density in this one. This lobe should shift its electron density in this one. This lobe should shift its electron density in this one. So how it would look like? See guys, how it would look like. This is how it's going to look like. See, positive, positive, negative, negative. So this part is positive, this I'm keeping negative. This lobe, electron density shifted here. So this lobe would have shrinked a bit. This lobe also would have shrinked a bit. So this is negative, this is positive, right? Similarly, this lobe would have shrinked a bit, so positive. This lobe would have shrinked a bit, I would say, this negative. So how many nodal planes do you see? In the middle, there is one plane on which there is no electron density. So you have got one nodal plane here, number one. Number two, since this is parallel overlapping, it leads to the formation of pi molecular orbital. So this is pi 3dxy. What do I call this? Was this in phase or out of phase? Same sign, same side. This was in phase, or I would say this was your constructive interference, which leads to the formation of molecular orbital, and you call this molecular orbital as pi 3dxy molecular orbital. Okay guys, is this clear? So this was basically this was how bonding molecular orbitals are formed as per constructive interference, right? Now, when two atomic orbitals combine, they lead to the formation of bonding as well as anti-bonding. Bonding molecular orbitals are formed through constructive interference. Anti-bonding molecular orbitals are formed through destructive interference. You saw how bonding molecular orbitals are formed through constructive interference. Now it is the time to see how anti-bonding molecular orbitals are formed through destructive interference. Now it's time to see how anti-bonding molecular orbitals are formed through destructive interference. So by destructive interference, which molecular orbitals are formed? Anti-bonding molecular orbital. I've told you already, their energy is their energy is more and stability is less. Why is that? Let's get to know. Let's say I'm taking atomic orbital of one atom. Similarly, this is one more atomic orbital of one more atom. Okay. Now, as I told you, if they are showing out of phase interference, or I would say if they are showing destructive interference, which molecular orbital is formed? Anti-bonding molecular orbital. Now, understand. Let's say this is the wave. Let's say this is the wave corresponding to this atomic orbital, and this is the wave corresponding to one more atomic orbital. I'm giving the signs, positive, negative. Let's say this is negative, this is positive. So opposite sign on same side. This is just to represent, this is just to show that destructive interference is going to happen. These two waves, they're not in same phase, they are out of phase. And when the two waves are out of phase, the resulting amplitude, if these two waves are going to show interference, the resulting amplitude of the wave is going to be minimum. The resulting amplitude of the wave is going to be minimum, right? Let's say amplitude of this wave was psi A. Let's say amplitude of this wave was psi B. So amplitude of this particular wave should have been psi A minus psi B. It should have been psi A minus psi B. Perfect. This should have been the amplitude of this wave. Now, if I take square of it, if I take square of amplitude, if I take square of amplitude, right? Square of amplitude gives me the probability of finding the electron. So, this psi square gives me probability of finding the electron in the atomic orbital A. Probability of finding the electron in the atomic orbital B. Probability of finding the electron in the molecular orbital, whose wave over here I've represented. Right? So, if you elaborate it a bit, it should have been psi square plus psi b square, and this will be minus 2 times psi b. My dear students, if you look logically, carefully, the probability of finding the electron in atomic orbital first was psi square. Here it was psi b square. So technically, since these two waves are combining, these two atomic orbitals are combining, the probability of finding the electron in this molecular orbital should have been psi square plus psi b square. But look at it. It is psi square plus psi b square minus this amount, minus 2 times psi b. So that means the electron density between the nuclei in the molecular orbital which is generated through destructive interference, that is decreased by how much amount? That is decreased by this much amount, 2 times psi b. If the electron density between the nuclei is decreased, repulsions between the nuclei are increased, energy of the system is increased, stability is decreased. So this is the wave corresponding to the molecular orbital which is generated through destructive interference, right? The probability of finding the electron in this molecular orbital should have been psi square plus psi b square, but it is psi square plus psi b square minus 2 times psi b. So electron density is decreased by how much of amount? 2 times psi b amount. So if the electron density between the nuclei has decreased by 2 times psi b, so repulsions between the nuclei would have increased, stability would have decreased. So that molecular orbital which gets formed through destructive interference, as I told you already, its energy is more, stability is less. And this molecular orbital is what we call as antibonding molecular orbital. Okay? Perfect. Now, how these antibonding molecular orbitals actually are formed? Let's have a look. So first of all, when two waves combine in opposite phase, electron density between the nuclei decreases, and which molecular orbital is formed? Antibonding molecular orbitals are formed. Antibonding molecular orbitals are formed. Now, how these antibonding molecular orbitals are formed? For example, this is 1s, this 1s. Let's say they have to combine. I'm going to show you the destructive interference. Let's say I need to show you the out of phase interference, due to which ABMO gets formed. So antibonding molecular orbital is going to get formed here. How do I show antibonding molecular orbital formation? How do I show destructive interference? Opposite sign I have kept on same side. Positive, negative. Opposite sign, same side, which represents destructive interference. Now, during destructive interference, we get antibonding molecular orbital. In the antibonding molecular orbital, the electron density between the nuclei, that decreases by how much amount? 2 times psi b. So we have to no doubt make the molecular orbital over here, but we have to keep one thing into consideration, that electron density between the nuclei should decrease. Now think about it. How electron density between the nuclei would decrease? How? If this part of the electron density will shift in this direction, this part of electron density will shift in this direction. So this is how the resulting antibonding molecular orbital will look like. This is how the resulting antibonding molecular orbital will look like. Okay? This electron density has shifted in this direction, this electron density has shifted in the other direction. So electron density between the nuclei has decreased. Perfect. And this particular molecular orbital, is it axial or parallel? It's axial. Axial leads to formation of sigma. But is this going to be sigma or sigma star? It is sigma star. Sigma star which one? Sigma star 1s. Do you see any plane on which there is no electron density? Yes, there is one plane on which there is no electron density. So in this molecular orbital, there is one nodal plane. I believe this is clear. Okay. For example, let me take one more. Let's say 2p and 2p, right? They are going to combine. They are going to show the destructive interference. Out of phase interference. Now, what is going to happen? How do I represent it? We have to keep opposite sign on same side. Positive, negative. Opposite sign on same side. So, we know we have to form the molecular orbital in such a way that electron density between the nuclei should decrease. How electron density between the nuclei will decrease? This lobe electron density should shift in this direction. This lobe electron density should shift in this direction. Okay? Right? So, how do I represent it at the end? How do I represent it in the end? This electron density is shifted in this direction. So I would say one lobe shrinks, another lobe. It's, I mean, you can say its thickness increases. Similarly, this lobe shrinks like this. If this is negative, keep this as positive, right? This is negative, this is positive. Perfect. So we have properly shown that electron density between the nuclei has decreased. Perfect. So which molecular orbital this is? This is again antibonding molecular orbital. Was this axial or parallel? This was axial. Axial leads to the formation of sigma. So is this going to be sigma or sigma star? This is sigma star. 2p which one? 2px, for example. Right? Do you see any nodal plane? Yes, I can see there is one plane in the middle which we can draw on which there is no electron density. So there is one nodal plane here. There is one nodal plane here. I believe this is clear. Perfect. Similarly, let's assume that we have to show the destructive interference here. So opposite sign on same side. What should happen? It is parallel first of all. So I'll be getting pi star at the end. Which one? Pi star 2py. This is the antibonding molecular orbital which I'm getting. How come I got to know that I'm getting antibonding? Opposite sign on same side, destructive interference. During destructive interference, electron density decreases, right? So let's say this lobe shifted in this direction, this lobe shifted in this direction, this one and this one is this, right? So this is how it's going to look like at the end. Okay, this is positive, this is negative, and this is positive. This is how your pi star 2py will look like. So how many nodal planes do you see here? This is one of the nodal planes. This is one more nodal plane. So in this one, you'll find two nodal planes in pi star 2py. In pi star 2py, two nodal planes you'll see. One last case over here, which I'm going to show you. Okay, one last case. So for example, this is your 3dxy, this is 3dxy. I have to show the destructive interference. Perfect. So again, let's call this as 3dxy. Let's also call this as 3dxy. Perfect. So over here, I'll be getting the antibonding molecular orbital. Is this axial or parallel? This is parallel. So I'll be getting pi, but this is pi star 3dxy, which I'm going to get over here. This is the antibonding molecular orbital. Now, my dear students, what in antibonding molecular orbital? You know, electron density between the nuclei has to decrease by how much of amount? 2 times psi A psi B. How do I represent that? Shift this electron density in this direction. Shift this in this way. Shift in this way. Shift in this way. Perfect. So if I need to make it at the end, how would I make it? How would I make it? See, this lobe would be bigger in size. This lobe would be smaller in size. Perfect. Right? Similarly, one lobe bigger, one lobe smaller. One lobe bigger, one lobe smaller. One lobe bigger and one lobe smaller. Perfect. So this is how your pi star 3dxy will look like. And you can find two nodal planes here. There are two nodal planes in case of your pi star 3dxy. I believe I'm clear with this. I believe I am clear with this, right? So this is positive, negative. This is positive, this is negative. Give the signs properly. Positive, negative. This is positive, this is negative. Perfect. Now, negative, positive. This is negative, this is positive. At the top, positive, negative. This is positive. This is how it will look like. Perfect. Perfect, people. Am I clear till here? Am I clear till here? So you exactly saw one thing, guys. You exactly saw one thing. What is that? Just a second. Okay, so what did we get over here? You got, I mean, this is what you learned over here. What you learned exactly? You learned how these molecular orbitals are formed. You learned exactly how these molecular orbitals are formed. Either bonding molecular orbitals or anti-bonding molecular orbitals. Okay, simple. Bonding molecular orbitals are formed by the constructive interference. Anti-bonding molecular orbitals are formed by the destructive interference. Okay. Perfect. I think I gave the signs reverse. Is that? Did I give the signs reverse? Yes, I gave the reverse signs. Guys, this is positive here. Okay, this is negative here. This is positive here, this is negative. This is negative and this is positive. So make the signs like this at the end. Make the signs like this at the end. So let me quickly summarize it now. I told you when atomic orbitals combine, they lead to the formation of molecular orbitals. Out of molecular orbitals, some will be bonding, some will be anti-bonding. Bonding are formed by the constructive interference, anti-bonding are formed by destructive interference, right? In case of bonding, the electron density between the nuclei increases. In case of anti-bonding, the electron density between the nuclei decreases, right? Therefore, stability of bonding molecular orbital will be more than that of stability of anti-bonding molecular orbital. That's something which we have discussed. Now, guys, the molecular orbitals which we have got, when atomic orbitals combine, we get molecular orbitals, right? The molecular orbitals which we get, we have to fill electrons in those molecular orbitals as per your Bose principle, Hund's rule, as well as Pauli's exclusion principle. The molecular orbitals which we get at the end, we have to fill electrons in these molecular orbitals as per a Bose principle, as per Hund's rule, etc., etc. And my dear students, this is the energy order of the molecular orbitals which get generated by the combination of atomic orbitals. Sigma 1s has got the least energy, followed by sigma star 1s, sigma 2s, sigma star 2s, pi 2px and pi 2py. These are degenerate, their energy is same. Pi 2pz, then pi star 2ps, pi star 2py, their energy is same. You have to remember the energy order over here, people. And this energy order is valid for those species which have got total electrons less or equal to 14. If the total electrons are less or equal to 14, this is going to be the energy order of the molecular orbital. This is going to be the energy order of molecular orbital. Energy order of molecular orbital. Now, my dear students, let's have a look. For example, you have got H2 molecule. In H2 molecule, how many electrons are there in total? One hydrogen contains one electron, so two hydrogen atoms will contain two electrons. Okay, so two electrons in total. Every molecular orbital will contain maximum of two electrons. Every orbital contains maximum of 2 electrons. So these 2 electrons will go into 1s, right? So its actual molecular orbital configuration is going to be what? It's going to be sigma 1s2. Sigma 1s2, right? Sigma 1s2. This is the molecular orbital configuration of H2. Now, if you got the molecular orbital configuration of H2, can I calculate its bond order? Half of. Number of electrons in bonding, 2 minus. Are there any anti-bonding? No. 2 minus 0. The value is 1. Bond order is 1. If bond order is 1, that means between two hydrogen atoms. Between two hydrogen atoms, there has to be a single bond, right? Now, look at the molecular orbital configuration of H2. I told you every molecular orbital contains maximum of 2 electrons. Perfect. So, this molecular orbital already has 2 electrons. Perfect. Already has 2 electrons, as you can see. Perfect. There is no unpaired electron. And whenever molecule has got no unpaired electron, we say that molecule is diamagnetic. Diamagnetic. Its magnetic moment is 0. Its magnetic moment is 0. How do we calculate magnetic moment? Under root of n into n plus 2 Bohr magnetrons. N represents the number of unpaired electrons. The number of unpaired electrons in the molecular orbitals. N represents the number of unpaired electrons in the molecular orbital. Look at this He2 molecule. One helium has got 2 electrons, 2 helium has got 4 electrons. So 2 in the first one, 2 in the second one, right? So its molecular orbital configuration is sigma 1s2, sigma star 1s2. Perfect. Calculate its bond order. It's going to be half of number of electrons in bonding, that is 2, minus number of electrons in anti-bonding, that's 2. So its bond order comes out to be 0. And whenever bond order comes out to be less than 0, less or equal to 0, we say the molecule does not exist. So this particular species does not exist over here. It does not exist over. Yeah, it does not exist over here. Li2. One lithium contains 3 electrons, 2 lithium contains 6 electrons. So 2, 4, 5, and 6. So its molecular orbital configuration is sigma 1s2, sigma star 1s2, right? Then comes your sigma 2s2. So calculate its bond order. Its bond order is going to be half of number of electrons in bonding, 2, 4, minus number of electrons in anti-bonding. Anti-bonding means starred ones. 4 minus 2 is 2, 2 by 2 is 1. So bond order is 1. If bond order is 1, that means between two lithium atoms, there is single bond. Now, do you see any unpaired electron here? Every molecular orbital can contain maximum of 2 electrons. So 2 here, 2 already here, and 2 already here. So there is no unpaired electron. No unpaired electron means it is diamagnetic in nature. Its magnetic moment is 0. Be2. One beryllium contains 4 electrons. So 4, 4, 8. 8 electrons in total. So 2, 4, 6. 6 and 2, 8. Perfect. So its molecular orbital configuration will be sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2. Perfect. Now calculate its bond order. It is going to be equal to half of number of electrons in bonding, 2, 4, minus number of electrons in anti-bonding, 2, 4. So 4 minus 4, 0. Bond order 0. That means molecule does not exist. Molecule does not exist. I believe this is clear to everyone. Yeah. Now, let's have a look on few more species which we have. And these are the species which I'm showing you. These are the species which contain total electrons less or equal to 14. Okay. Now, B2 molecule. One boron has got 5 electrons. 2 boron will have got 10 electrons, right? So, 1, 2, 3, 4, 5, 6, 7, 8. Now, this is degenerate. Now, pairing won't happen in the degenerate orbitals unless each degenerate orbital gets 1 electron each. So, 11. After that, I'll do the pairing. After do, I'll do the pairing, right? After do, I'll do the pairing. Hund's rule, you know. Each degenerate orbital should get 1 electron first. Then, pairing will happen in the degenerate orbitals. Now, calculate its bond order. It's going to be equal to half of number of electrons in bonding, 2, 4, 5, 6. Minus number of electrons in anti-bonding, 2, 4. 6 minus 4 is 2, 2 by 2 is 1. Bond order is 1. So between two boron atoms, there is a single bond. Now, do you see any unpaired electrons here? 1 unpaired, 2 unpaired. So there are 2 unpaired electrons. N value is 2. If there are 2 unpaired electrons, calculate the magnetic moment. Under root of 2 into 2 plus 2. 2 plus 2, 2, 4. 4 2s are 8. So root of 8 Bohr magnetrons. Any species whose net dipole moment is non-zero, that species is going to be paramagnetic. So this particular species here is going to be paramagnetic because its net dipole moment is non-zero. I mean, its net magnetic moment is non-zero. Its magnetic moment is non-zero, so it's going to be paramagnetic in nature. Okay? Paramagnetic in nature. Its magnetic moment is non-zero. Talk about C2 molecule. In case of C2, one carbon has got 6 electrons. So 2 carbon atoms will have 12 electrons. So 2, 4, 6, 8, 9, 10. Now pairing will happen 11, 12, right? Calculate the bond order. Bond order is going to be half of number of electrons in bonding. Calculate 2, 4, 6, 8 minus anti-bonding 2, 4. 8 minus 4 is 4. 4 by 2 is 2. So bond order is 2. So there is a double bond between 2 carbon atoms. Remember, in case of C2 molecules, normally what happens? Normally out of 2 bonds, one is sigma, one is pi. But in case of C2 molecule, both the bonds are basically the pi bonds. In case of C2 molecule, both the bonds here which get formed, they are pi bonds. Do you see any unpaired electron here? There is no unpaired electron in the configuration. So if there is no unpaired electron, it is diamagnetic. Its magnetic moment is going to be 0. Now N2 positive, N2 negative. N2 contains 14 electrons. So 12 already we have filled, right? 13, 14. Calculate its bond order. It is half of bonding 2, 4, 6, 8, 10 minus anti-bonding 2, 4. So 10 minus 4 is 6, 6 by 2 is 3. So in case of N2, there is a triple bond. There is a triple bond. Do you see any unpaired electrons here? There is no unpaired electron. If there is no unpaired electron, that means magnetic moment is 0, diamagnetic. N2 positive. N2 positive means take 1 electron out from N2. Take one electron out from N2. One electron has to be out from here. So 13 electrons in total, right? So calculate the bond order. It is going to be half of number of electrons in bonding. 2, 4, 6, 8, 9 minus 2, 4. 9 minus 4 is 5. 5 by 2 is 2.5. Its bond order is 2.5. Fractional bond order. Now, in case of N2 positive, do you see unpaired electron? Yes, there is unpaired electron. If there is unpaired electron, calculate the magnetic moment. Under root of how many unpaired electrons? 1. So 1 into 1 plus 2. 2 plus 1 is 3. So root 3 Bohr magnetrons. Perfect. And that particular species whose net magnetic moment is non-zero, that has to be paramagnetic. Same you can calculate for N2 negative as well. Same you can calculate for N2 negative as well. N2 negative means 7, 7, 14, 1, 15, 15 electrons. 2, 4, 6, 8, 12, 10, 12, 13, 14, and 15. Right? Let me check it out again. 15 electrons we have to show because one nitrogen atom contains 7 electrons. 7 2s are 14. 14 plus 1 makes it 15, right? Makes it 15. So 2, 4, 6, 8, 10, 12, 14, 15. So calculate bond order, half of. Number of electrons in bonding. 2, 4, 6, 8, 10, 11 minus number of electrons in anti-bonding. 2, 4, 5. Wait, I think we have done some mistake here. How many electrons are in bonding? 2, 4, 6, 8, 9, 10. So this is 10 basically here. 10 minus anti-bonding. 2, 4 plus 1, 5. So 10 minus 5 is 5. 5 by 2 is 2.5. So again, bond order is 2.5. Is there any unpaired electron? Yes, there is one unpaired electron. So mu has to be equal to 1 into n plus 2. 1 plus 2 is 3. So root of 3 Bohr magnetrons. If the magnetic moment is non-zero, this has to be paramagnetic. Right? Perfect. Sir, how n is equal to for B2? For B2 means 10 electrons, right? 2, 4, 6, 8, 9 and 10. These are degenerate. Pairing won't happen unless each degenerate orbital gets 1 electron each. It should be clear. Now guys, one more thing. If you look at N2, if you look at N2 positive, if you look at N2 negative, N2 positive and N2 negative. Let me write it over here. Let's say we have got N2 positive and N2 negative. First of all, bond order of N2 we got to know as 3. Bond order of N2 positive is 2.5. Bond order of N2 negative is also 2.5, right? I told you in the beginning, bond order is directly proportional to bond strength, which is directly proportional to bond dissociation energy, right? It's directly proportional to bond dissociation energy. So first of all, bond order you can easily calculate. Now, bond order you can easily calculate. Perfect. Now tell me the stability order. If I ask you about the stability order, remember, stability is directly proportional to bond dissociation energy. Stability is directly proportional to bond dissociation energy, or you can say stability is directly proportional to bond strength. Perfect. It is directly proportional to bond strength. So first of all, more the bond order, more the bond dissociation energy, more the bond dissociation energy, more the stability. So 1 is maximum stable. Now among these two, bond order is same. Bond order is same. I told you when bond order is same and you have to compare stability. How do you do that? When bond order is same and you have to compare the stability, how do we do that? We do that by calculating the electrons, right? See, bond order of these two is same. But if you think logically, in case of N2 negative, there are more electrons in anti-bonding, right? And more the electrons in anti-bonding, lesser the stability. So 2 would be more stable than that of 3. Perfect. So my dear students, till now, I showed you the electron filling order in case of the species which contain less than 14 electrons. Now, what about those species which contain greater than 14 electrons? What about those species which contain greater than 14 electrons? Like you have got O2, O2 positive, O2 negative, O2 di-negative. O2 contains 16 electrons. This contains 16 minus 1, 15 electrons. This contains 17 electrons. This contains 18 electrons. Perfect. Now, how do you calculate their bond orders? Again, you have to write the molecular orbital configuration. So, 16 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Right? So, calculate the bond order. It is half of number of electrons in bonding. 2, 4, 6, 8, 10, 11, 12. Minus number of electrons in anti-bonding. 2, 4, 6. I think we have calculated wrong here. Just a second. Bonding 2, 4, 6, 8, 10. Right? Minus 10 minus anti-bonding. 2, 4, 5, 6. So 10 minus 6 is 4. 4 by 2 is 2. Bond order is 2. Bond order 2 means between two oxygen atoms there will be double bond. Now, in this particular configuration, do you see unpaired electrons? 2 unpaired electrons. If there are 2 unpaired electrons, magnetic moment is going to be under root of n into n plus 2. So 2 plus 2, 4, 4 2s are 8. So root of 8 Bohr magnetrons. So this is the species which has got the magnetic moment. So it is going to be paramagnetic in nature. O2 is paramagnetic. Similarly, when you calculate O2 positive, 15 electrons. Say this is the electronic configuration for 16 electrons. Now write for 15 electrons. So take one electron out. When you take one electron out, bond order, you can easily calculate half of number of electrons in bonding. 2, 4, 6, 8, 10, minus. How many anti-bonding? 2, 4, right? 2, 4 and 5. 10 minus 5 is 5. So 5 by 2 is 2.5. Perfect. So the bond order is 2.5. And there is one unpaired electron. So you can calculate the magnetic moment under root of n into n plus 2. So it comes out to be root of 3 Bohr magnetrons, right? So magnetic moment is non-zero. So it's paramagnetic again. Paramagnetic again. Similarly, when you calculate for O2 negative, you can easily calculate its bond order. Perfect. And O2 di-negative also you can calculate. Now guys, there is one trick also to calculate the bond order. And I would want you guys to remember that trick. That even N2 negative has got 15 electrons. See guys, first of all, I'll tell you. See, this is the order. This is the order till 14 electrons. Till 14 electrons. And this is the order for more than 14 electrons. For more than 14 electrons. Now, for example, you have got N2 negative. For N2 negative, there will be 15 electrons in total. For N2 negative, there will be 15 electrons in total, right? But if you see few minutes back, I filled electrons in case of N2 negative as per the first configuration for the less than 14 one, or less or equal to 14 one. Why is that? See, no doubt we have to calculate for N2 negative, which contains 15 electrons. But what is the parent molecule for it? Parent molecule is N2. N2 contains 14. N2 contains 14. So whatever category this particular species lies in, same category has to be applied for this. Same configuration has to be applied for this. Same order has to be applied for this. For example, you have got O2. You have got O2. Right? You have got O2. O2 is a 16 electron species. Now you have got O2 di positive. For example, O2 di positive. O2 di positive comes in 14 category. But O2 di positive comes in 14 category. I'll see its parent one. Parent one is O2. O2 is 16, right? So this particular one will also follow the 16 electron configuration. I mean, it will follow that energy filling order, which is used for electrons more than 14. Perfect. Am I clear with this? Did you understand? Did you understand, people? So for example, you have got N2 and you have got, for example, N2 negative. N2 negative. Here you have got 14 electrons. Here you have got 15 electrons. Which order you will be following here? Less or equal to 14. Which order you will be following here? Are you going to follow greater than 14? You are not going to follow greater than 14 order. You will be following less or equal to 14 only, because you have to check the parent atom. If the parent atom is following this will follow the same. Yeah? Got it? Okay. Now comes one more thing. Now comes one more thing. I hope you know about isoelectronic species. If you talk about the isoelectronic species, my dear students, in case of isoelectronic species, remember, bond order is same. Isoelectronic species means same number of electrons. Species which contains same number of electrons. Species which contain same number of electrons, their bond order is going to be same. For example, let's say you have got N2 and you have got CO. Okay? N2 and CO. Or let me simply write this one. For example, you have got NO positive and CN negative. NO positive, CN negative. Calculate the total electrons here. This is 8. 8 plus 1, 7, 15. 15 minus 1, 14. So it's a 14 electron species. 7 plus 6, 13. 13 plus 1, 14. It's also 14 electron species. So both contain same electrons. So they are isoelectronic. And all the isoelectronic species, they have got same bond order. And you know, 14 electron species, their bond order is 3. So their bond order is same, which is equal to what? Their bond order is equal to 3. Simple. Now guys, one trick I'm going to give you over here first of all. One trick, one simple trick, which is going to help you out in order to calculate the bond order. Now, if the total electrons can be 14, total electrons of the species can be 15 also, 16 also, 17 also, 18 also. Total electrons in the species can be 13 also, 12 also, 11 also, 10 also. Remember, if the total electrons in the diatomic species is 14, its bond order will be 3. Now reduce by 0.5. Reduce further 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 by 0.5. These are the bond orders, right? N2 is the 14 electron species, right? N2 is the 14 electron species. For example, you have got N2 positive, 14 electron species. Let's say you have got N2 negative, 15 electron species. Let's say you have got O2, 16 electron species. O2 negative, 17 electron species. O2 dinegative, 18 electron species. Correct? Let's say you have got C2, 2 electron species. Let's say you have got C2 positive, 11 electron species. Let's say you have got B2, 10 electron species. Perfect. This is how you can remember their bond orders. Perfect. This is how you can remember their bond orders. And guys, based on bond order, you can give the answer of the questions based on bond length, bond dissociation energy, bond strength, etc., etc. I hope I'm clear with this. Am I clear with this? Am I clear with this, guys? Perfect. Now, before understanding one more topic, that is your hydrogen bonding, there's one topic which I would want to tell you over here. What is that? That is bond parameters. Bond parameters, which includes bond angle, similarly bond length, questions based on bond angle, bond order. See guys, first of all, whenever you'll be asked a question related to bond angle, whenever you'll be asked a question related to bond angle, this is the diagram which you'll be following. Apart from this diagram, you are not going to follow anything. Whenever, I'm repeating the same, whenever, my dear students, I'm not able to find your telegram, sir, kindly help. Just search it, Wassim Bhat Chemistry Official. Wassim Bhat Chemistry Official, just search on Telegram, you'll get my Telegram ID. You'll get my Telegram channel. Okay, whenever you have to, you have got the questions wherein you have to check the bond angles basically. Okay, how do we check the bond angles? In order to compare the bond angles of different species, this is the table which has to be remembered. First of all, this is the important one. This is the important table. From this table, every single thing which is based on bond angle, any question which is based on bond angle, you can answer that. Now, what this table exactly is all about? My dear students, whenever you have to compare the bond angles in different species, first of all, you will be considering VSEPR. What is meant by that? Considering VSEPR. First of all, you'll be checking whether if there is any molecule which is of the type AB2L0 or AB2L3. If there are 3 molecules given to you, out of which, let's say, one molecule is of the type AB2L0 or AB2L3. You know AB2L0, AB2L3, they have got linear geometry. Their bond angle will be maximum 180. So first of all, you'll be considering VSEPR, right? You'll be checking whether there is any molecule of the type AB2L0 or AB2L3. If there is any molecule of the type AB2L0 or AB2L3, its bond angle will be maximum 180, right? Now, after VSEPR, go to hybridization. I mean, if you are unable to answer as per VSEPR, right? If you are unable to answer as per VSEPR, then go for the hybridization. Check the hybridization of the central atom. If hybridization of the central atom is different, let's say one central atom sp, another sp2, another sp3. You know, in sp3 hybridization, bond angle is 109 degree, 28 minutes. In sp2 hybridization, it is 120. It is 120. In sp, it's 180. If the hybridization of the central atom is different, then the central atom which has got sp hybridization will have the bond angle of 180, followed by sp2, followed by sp3. Then you'll give the answer as per hybridization. Now, if the hybridization is same, if the hybridization is same, then what? If hybridization of the central atom is not different, if it is same, then how do we answer? How do we answer the questions? See, over here, if hybridization is same, 2 cases will arise. Hybridization is same. Lone pair is absent on the central atom and lone pair is present on the central atom. If lone pair is absent on the central atom, give the answer as per hybridization. Give the answer as per hybridization. If hybridization is same and lone pairs are absent on the central atom, give the answer as per hybridization. For example, you have got BF3, you have got BR3. For example, you have got BI3. Okay. Hybridization of boron everywhere is sp2. Hybridization is same. No lone pair on the central atom. Give the answer as per hybridization. sp2, sp2, sp2. Their bond angles will be same, equal to 120. This is what I meant. This is what I meant. Okay. Now, if hybridization is different, if hybridization is same, but there is lone pair present on the central atom, then remember, bond angle is inversely proportional to the lone pairs, number of lone pairs. If hybridization is same, but lone pair is present on the central atom, then bond angle is inversely proportional to lone pairs. More the lone pairs, less than the bond angle, right? Now there comes one more case. If hybridization as well as number of lone pairs are same, if hybridization is same as well as number of lone pairs on the central atom are same, then you'll be talking in terms of size of surrounding atom and size of central atom. Remember, bond angle is directly proportional to size of surrounding atom. Similarly, bond angle is inversely proportional to the size of central atom. Okay, when do we use these particular two? These particular two formulas are used when the hybridization as well as the number of lone pairs are same. So first you will check your answer as per VSEPR. If you are not getting from VSEPR, then go to hybridization. If hybridization is different, SP will be having more. If hybridization is also same, right, then there are 2 cases. Central atom carrying no lone pair, central atom carrying lone pair. If central atom carries no lone pair, give the answer as per hybridization. If central atom carries the lone pair, so bond angle will be inversely proportional to number of lone pairs on central atom. If hybridization as well as number of lone pairs are same, then bond angle directly proportional to size of surrounding atom, or bond angle inversely proportional to size of central atom. Now let's do certain questions and understand all these things one by one, where they are used. See guys. First question, CO2, NO2 positive XCF2. Check first of all VSEPR. The type of this molecule is going to be AB2L0. Type of this molecule is again going to be AB2L0. When you check it, type of this molecule is going to be AB2L3. As I told you already, whenever you have got the molecule of the type AB2L0 or AB2L3, their bond angle is maximum. So they will have equal bond angles of how much? 180 degree. They are linear. Okay. Now, the type of this molecule is AB2L0. Here it is AB3L0. Here it's AB4L0. So you cannot decide on the basis of VSEPR. You cannot decide on the basis of VSEPR. Now, when you cannot decide on the basis of VSEPR, go for hybridization. What is the hybridization of carbon here? SP. What is the hybridization of boron here? SP2. What is the hybridization of carbon here? SP3. Right? In case of SP, the bond angle is maximum 180, followed by SP2, followed by SP3. Correct? Look at the next one. First of all, look at the type. This is AB4L0, AB3L1, AB2L2. The type is different. The type is different. Type is not same. Go to hybridization. SP3 for this carbon, SP3 for this nitrogen, SP3 for this oxygen. So hybridization is not, it's not different. Hybridization is same. Hybridization is same. If hybridization is same, at that point of time, check are there lone pairs present or not. There is no lone pair here. There's one lone pair here. There are two lone pairs here. If hybridization is same, but lone pairs are different. If hybridization is same, but lone pair is present on the central atom, then bond angle is inversely proportional to lone pairs. Bond angle is inversely proportional to lone pairs. Bond angle is inversely proportional to lone pairs. More the lone pairs, lesser the bond angle. More the lone pairs, lesser the bond angle. So this is the bond angle order over here. Talk about this one. BCl3, BBr3, BI3. Hybridization, sp2, sp2, sp2. Everywhere, hybridization is same. Now, no lone pair on the central atom. Give the answer as per hybridization. sp2, sp2, sp2. They have same bond angles, 120. Same bond angles, 120. Perfect. Now, I believe these you can easily solve. Look at this one. CCl4, SiCl4, GeCl4. Right? Check. Check, guys. What is going to be the order? Quickly in the chats. What do you think is going to be the order here? Let me know once. Let me know once, people, quickly. Quick. You should be able to answer this. What will be the bond angle? Bond angle order. Here, quick. Hybridization is same. No lone pair on the central atom. No lone pair on the central atom. Right? Give the answer as per hybridization. sp3, sp3, sp3. Same. NCl3, PCl3, AsCl3, SbCl3. First of all, hybridization, sp3, 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 sp3. Hybridization is same. Lone pairs also same on the central atom. One lone pair on each central atom. When hybridization is same, as well as lone pair is same. When hybridization as well as lone pair is same. When hybridization as well as lone pair is same, then bond angle is directly proportional to size of surrounding atom. Bond angle is directly proportional to size of surrounding atom. And bond angle is inversely proportional to size of central atom. The surrounding atom here is same. Central atom is different. Bond angle is inversely proportional to size of central atom. More the size of central atom, lesser the bond angle. More the size of central atom, lesser the bond angle. Right? Lesser the size of central atom, more the bond angle. Now here, if you look at this particular case, here you can see everywhere nitrogen has got one lone pair. So hybridization is same, number of lone pair is same. Now talk about the size of surrounding atom. Bond angle is directly proportional to size of surrounding atom. More the size of surrounding atom, more the bond angle. More the size of surrounding atom, more the bond angle. Look at the next one. Cl2O, Br2O. Cl2O, Br2O. So hybridization is same. Number of lone pairs same. Hybridization same. Number of lone pairs same. Talk about the surrounding atom. More the size of surrounding atom, more the bond angle. More the size of surrounding atom, more the bond angle, right? More the size of surrounding atom, more the size of surrounding atom, more the bond angle. Perfect. This is how you give the answers of when it comes to the bond angles. Perfect. So this is the bond angle part. Now there are few more questions which are asked when it comes to your bond length. Bond length. My dear students, there are some questions which are asked on bond length as well. First of all, what is a bond length? How do we define the bond length? Bond length is simply defined as the average distance between the nuclei of two atoms. average distance between the nuclei of two atoms in a molecule. Let's say you've got a molecule. Let's say you've got a molecule. This is a molecule which has been formed. Whatever is the average distance, whatever is the average distance between the nuclei of the two atoms here, that is something which you call as bond length, right? Now, this bond length depends on what all factors? The first factor on which the bond length depends on, that is the size of atoms. And bond length is directly proportional to size of atoms. It is evident, more the size of atoms, more is going to be the distance between their nuclei. And more the distance between the nuclei means more the bond length. Now, give the order of the bond length here. Give the order of the bond length here. HI, HBr, HCl, HF. So iodine is maximum in size, followed by Br, followed by Cl, followed by F. More the size of the atoms, more the bond length. This is the order of the bond length. Okay. HH, CH, CC, Si. So this is the order of the bond length. More the size of the atoms, more the bond length. Simple. The next one. Oxygen, sulfur, SET. Oxygen, sulfur, they are in the same group. Down the group, size increases, right? More the size, more the bond length. As simple as that. Yeah. So, as I told you, the bond length, the first factor on which the bond length depends on, that is the size of the atoms. More the size of atoms, more is going to be the bond length. Simple. More is going to be the bond length. Number one. Number two. What is the effect of bond order on bond length? I told you already, bond length is inversely proportional to bond order. For example, you have got carbon, single bond carbon. Its bond order is 1. Here the bond order is 2. Here the bond order is 3. More the bond order, lesser the bond length. More the bond order, lesser the bond length. Simple. Third factor. Third factor on which bond length depends on. That is electronegativity difference between the atoms. More the electronegativity difference between the atoms, lesser is going to be the bond length. Remember this particular thing as well. And this is observed generally. Similarly, effect of hybridization. See, bond length is inversely proportional to S character. It is inversely proportional to S character. See guys, this is sp2. Sorry, this is sp3. This is sp3 also. sp3. This is sp3, sp2. This is sp3, sp. This is sp2, sp2. This is sp2, sp3. Sorry, sp. And this is sp and sp. If I ask you to compare the bond lengths, as I told you, bond length is inversely proportional to what? As I told you, bond length is inversely proportional to S character. More the S character, lesser is going to be the bond length. More the S character, lesser is going to be the bond length. Here, sp3, sp3. What is the S character in sp3? 1 by 4. 1 by 4 is 25%. 25% S character, 25% S character. sp3, 25% S character, 25% sp2. 1 by 2 plus 1, 3. 33% S character. Here, sp3, 25%, sp means 50% S character. I've told you how to calculate the S character, right? Similarly, sp2, 1 by 3, 33% S character, 33% S character. This 33%, 50% S character. 50% S character, 50% S character. More the S character, lesser is going to be the bond length. More the S character, lesser is going to be the bond length. So the last one is going to have minimum bond length because both are having maximum S character. Followed by this, followed by this, followed by this one, followed by this one, and followed by this one. This is the order. This is the order here. Perfect? This is the order, people. So if I need to number them, this is 1, 2, 3, 4, 5, 6. So 6 is going to have the minimum bond length. 6 is going to have the minimum bond length, followed by 5, followed by 4, followed by 3, followed by 2, followed by 1. This is going to be the order of the bond length. Because bond length is inversely proportional to the percentage S character. Remember this particular thing, right? So these were the questions based on what? Based on bond lengths. Perfect. Now, there is one last topic, guys, which I need to teach you over here. What is that? That is hydrogen bonding. That is hydrogen bonding. Okay, hydrogen bonding. This is not going to take more than like 15 to 20 minutes. Maximum 15 minutes it's going to take. There are a few things which I need to tell you, that's all. Hydrogen bonding. My dear students, look at the things which I've mentioned on the screen already. Have a look. Have a look now. Nitrogen, oxygen, and fluorine. These are like electronegative elements on the periodic table. You must be knowing in the periodic table, fluorine is considered to be maximum electronegative, followed by oxygen, followed by nitrogen, right? In the periodic table, your fluorine is considered to be maximum electronegative element, followed by oxygen, followed by nitrogen, right? Now, my dear students, nitrogen, oxygen, and fluorine, they are high electronegative elements. When they are attached to hydrogen atom, when these atoms are attached to hydrogen atom to form the covalent bonds. So when nitrogen, fluorine, or oxygen will be attached with attached with hydrogen to form a covalent bond, the electrons of the covalent bond are shifted towards more electronegative element. The partial positively charged hydrogen atom forms bond with the other more electronegative element. What does it mean? Let's have a look. Let's have a look, people. Understand. For example, I've got HF molecule. Let's say I've got HF molecules over here. A lot of HF molecules we have. Okay. First of all, fluorine, which is the more electronegative element, which is the highest electronegative element in the periodic table, it is attached with hydrogen with a covalent bond. Fluorine attached with hydrogen with a covalent bond. Fluorine attached with the hydrogen with a covalent bond. Right? So, the most electronegative element of the periodic table is attached with hydrogen with the help of what? Covalent bond. Now, my dear students, if you look about this covalent bond, it is between fluorine and hydrogen. Fluorine is more electronegative. So, this electron pair will be shifted towards what? Towards fluorine, due to which fluorine gets delta negative. Hydrogen gets delta positive. Fluorine everywhere gets delta negative, hydrogen delta positive. Fluorine delta negative, hydrogen delta positive. Right? Now, since this fluorine is getting delta negative, this hydrogen is getting delta positive. No doubt, this fluorine is attached with this hydrogen with the help of covalent bond. But at the same time, fluorine of this molecule and hydrogen of this molecule, there can be attraction between them because there is positive negative here. Similarly, fluorine of this molecule, hydrogen of this molecule, there can be attraction between them. Perfect. And this force of attraction between the two molecules over here, this is something which you call as hydrogen bond. This is what you call as hydrogen bond. Perfect. This is what you call as hydrogen bond. For example, you talk about water. Let's say this is one water molecule. Perfect. This is one water molecule. Let's say similarly, over here you have got one more water molecule. Similarly, over here you have got one more water molecule. Perfect. Right? Similarly, guys, for example, there is one more water molecule here. Perfect. Imagine there is one more water molecule here. These are a lot of water molecules which are made over here. Now tell me one thing. In case of water, if you talk about this bond, it's a covalent bond, this is a covalent bond between oxygen and hydrogen. Covalent bond between oxygen and hydrogen everywhere. But between oxygen and hydrogen, which one is more electronegative? Oxygen. So delta negative, delta positive. Delta negative, delta positive. Delta negative, delta positive. Delta negative, delta positive. Everywhere delta negative and delta positive. Perfect. Everywhere delta negative and delta positive. Perfect. Now, guys, do you see one thing? Can I say this hydrogen carrying positive, oxygen carrying negative? They can attract each other. Similarly, over here they can attract. Over here they can attract. Sorry, not this one. Positive, negative I have to show, right? These two can attract. These two can attract. Positive, negative. So between two water molecules, which kind of bonding is existing? This is what I call as hydrogen bonding. Perfect. fluorine oxygen hydrogen of one molecule, which is covalently bonded with hydrogen, will be attracting the hydrogen of another molecule. This particular bonding is something which we call as hydrogen bonding. Perfect. Now, my dear students, this hydrogen bonding is of two types, basically. This hydrogen bonding is of two types. One is intermolecular hydrogen bonding. One is called as intramolecular hydrogen bonding. Okay, one is intermolecular, one is intra. Inter means between two molecules. Intra means within the molecule. Inter means between two molecules. Inter means between the molecules, I would say. Between the molecules. Intra means within the molecule. Whenever you see hydrogen bonding within the molecule, you'll be calling that as intramolecular hydrogen bonding. Whenever you see hydrogen bonding between the molecules, you call that as intermolecular hydrogen bonding. For example, HF. For example, HF. What do you see over here? This is hydrogen bonding within the molecule. Intra. Like you have water. Like you have water. Hydrogen bonding between the molecules. So inter. Right? Carboxylic acid. For example, talk about this OH bond. Delta negative, delta positive. Right? Similarly, for example, delta negative. Sorry, not this one. OH. Delta negative, delta positive. Perfect? Right? Similarly, this is here delta negative, this will be here delta negative. Perfect? So again, there will be hydrogen bonding between the molecules. So this is again over here between these two carboxylic acid molecules, there will be hydrogen bonding, which is what I'll be calling as intermolecular hydrogen bonding. Now, if you look at intramolecular, if you look at intramolecular means hydrogen bonding within the molecule. This was hydrogen bonding between the molecules. This was hydrogen bonding between the molecules. Now, hydrogen bonding within the molecule is what we call as intra. For example, OH bond. Delta negative, delta positive. Perfect. NO bond. Delta negative, delta positive. Perfect. Can I say there will be attraction over here? This attraction is what I call as hydrogen bond. Due to this hydrogen bond, do you see a ring got formed? A ring got formed over here. This formation of ring over here is something which we call as chelation or chelation, you can say. Perfect. This hydrogen bond within the molecule. Similarly, this is negative, this is positive. This is negative, this is positive. So there will be hydrogen bond here, right? Similarly, there will be hydrogen bond here. Perfect. Whenever hydrogen bond is there within the molecule, you call that as intramolecular. Between the molecules, intermolecular. Now, what is the effect of hydrogen bonding? What is the effect of hydrogen bonding on different parameters? My dear students, first of all, when you talk about solubility, solubility is directly proportional to intermolecular hydrogen bonding. Solubility is directly proportional to intermolecular hydrogen bonding. For example, over here, alcohols and glucose, they are soluble in water. Why? Because alcohols as well as glucose, they can form hydrogen bonds with water. They can form hydrogen bonds with water, right? Alcohols as well as glucose, they can form hydrogen bonds with water. So those molecules which can form hydrogen bonds with water, they are going to be soluble in water. Perfect. So I would say alcohols, glucose, they are soluble in water because alcohols and glucose, they can form hydrogen bonding with water. So there is intermolecular hydrogen present between alcohol water, between glucose water. So alcohols and glucose, they are soluble in water. Number one. Number two, solubility is inversely proportional to intramolecular hydrogen bonding. Intramolecular hydrogen bonding. My dear students, orthohydroxybenzaldehyde is less soluble in water than parahydroxybenzaldehyde. Orthohydroxybenzaldehyde is less soluble than parahydroxybenzaldehyde. What is the logic behind that? What is the logic behind that? My dear students, in orthohydroxybenzaldehyde, what do we see? We observe intramolecular hydrogen bonding. Hydrogen bonding within the molecule. In para-hydroxy, you do not observe the intra. You do not observe hydrogen bonding within the molecule, right? So, when orthohydroxybenzaldehyde is introduced in water, already the site which was available for hydrogen bonding, that's already occupied. Perfect. That site is already used for hydrogen bonding, for intramolecular hydrogen bonding. But in case of para-hydroxy, when you introduce it in water, this para-hydroxy, it is going to form the hydrogen bond with the water. So that is the reason I must say para-hydroxybenzaldehyde, it is less soluble in water than your, orthohydroxybenzaldehyde is less soluble in water than that of your para-hydroxybenzaldehyde. Okay? Is this point clear? Is this point clear, guys? Everyone in the chats. Everyone in the chats. Quick. See, if you look here, this is your orthohydroxybenzaldehyde. Already there is a intramolecular hydrogen bond formed. Now, if you have something like this, let's say C, double bond O, H, and over here, for example, you have got OH. This is para-hydroxy. Benzaldehyde. Now, when you are introducing this in water and this in water, I would say this para-hydroxy benzaldehyde is going to form hydrogen bonding with water. This also would have formed hydrogen bonding with water, but the site is already occupied. Chelation is already formed, right? Okay, so this hydrogen is not available for the hydrogen bonding with water. So the reason is, what is the reason over here? Orthohydroxybenzaldehyde is less soluble in water than para-hydroxy. The reason you got to know, in orthohydroxy there is intramolecular hydrogen bonding, right? Perfect. Over here, there is no intramolecular hydrogen bonding. So remember, simple solubility is inversely proportional to intramolecular. Now, talking about the viscosity. Viscosity is also directly proportional to intermolecular hydrogen bond. Viscosity is directly proportional to intermolecular hydrogen bonding. Inter means between two molecules. If there is intermolecular hydrogen bonding, due to intermolecular hydrogen bonding, between two molecules there will be attraction. Due to intermolecular hydrogen bonding between two molecules there will be attraction. These molecules, I would say, they cannot flow easily because there is attraction between the molecules. They cannot flow easily. So I would say viscosity is more. So viscosity is directly proportional to intermolecular hydrogen bonding between the molecules. If there is hydrogen bonding, perfect. That means there is some force which is holding these molecules together. Perfect. So molecules cannot move freely. So viscosity is more, right? So viscosity is directly proportional to intermolecular hydrogen bonding. For example, water. You have got CH3OH. You have got CH3OCH3. Perfect. In case of water, the intermolecular hydrogen bonding is more than that of your methanol. If intermolecular hydrogen bonding in water is more, you can say viscosity of water will be more than that of CH3OH. Perfect. Right, people? Similarly, these are the three species which I have taken. Among all these three, where do you see extent of hydrogen bonding will be more? Extent of intermolecular hydrogen bonding will be more? I think here you have got more sites for intermolecular hydrogen bonding. Here you have got comparatively less sites for intermolecular hydrogen bonding. And here you have got least sites for intermolecular hydrogen bonding. More the sites for intermolecular hydrogen bonding, more will be the extent of hydrogen bonding. More is the extent of intermolecular hydrogen bonding, more will be the viscosity. The viscosity of this particular compound will be more than this. Okay? Remember this. Similarly, melting boiling points, they are also directly proportional to what? Melting boiling points, they are also directly proportional to intermolecular hydrogen bonds. More the hydrogen bonds, more the intermolecular hydrogen bonds between the molecules, more will the melting points, boiling points. Right? More will the melting points, boiling points. For example, look at this. HF, HI, HBr, HCl. So, for example, you have got HF, you have got HCl, you have got HBr, you have got HI. Generally, what should happen? On moving from top to the bottom, generally, what is the trend? Trend is boiling point increases down the bottom. Right? From top to the bottom, boiling point increases generally. Perfect? Boiling point increases generally. So I would say HI should have maximum boiling point, followed by HBr, followed by HCl, followed by HF. But HF, due to hydrogen bonding, it comes first. The boiling point of HF is maximum due to hydrogen bonding. Perfect? This is the actual order. HF will be having maximum, followed by HI, HBr, HCl. Same goes for the hydrates of group 16. Normally, what should be the trend? If you have got H2O, if you have got H2S, if you have got H2SE, if you have got H2T, generally on moving from top to bottom, boiling point should increase. So this should have maximum boiling point, right? This should have minimum boiling point. But in case of water, there is hydrogen bonding. So water has got maximum boiling point, followed by this, right? So this is the boiling point order here. This is the boiling point order, right? Is it clear? Is it clear, people? So in short, more the intermolecular hydrogen bonding, more is going to be the melting points, boiling points. Now guys, there is one more thing which you need to remember. Melting boiling points, they are inversely proportional to intramolecular hydrogen bond. Melting boiling points, they are inversely proportional to what? Intramolecular hydrogen bonding. Okay? They're inversely proportional. Why is that? What is the logic behind that? How can you understand this? How can you understand this? My dear students, due to intramolecular hydrogen bonding within the molecule, due to intramolecular hydrogen bonding, between two molecules, there will be less attraction due to intramolecular. Because the sites are already done. There is intramolecular hydrogen bonding already present. Between the molecules, there will be less attraction. Less attraction means less energy need to break it, right? So less boiling point. Perfect. So your melting boiling points, they are inversely proportional to intramolecular hydrogen bonds. Okay. See, due to intermolecular hydrogen bond, molecular weight increases. This is again one more thing. Due to intermolecular hydrogen bond, molecular weight increases. For example, if you talk about acetic acid. My dear students, acetic acid in benzene, it forms a dimer. That means two acetic acid molecules, they are going to associate and going to form one molecule. So molecular weight of acetic acid is double its molecular formula. Why? Because in benzene, it associates to form two acetic acid molecules. In benzene, they associate to form one molecule. Right? As you can see here, negative positive, there will be this, negative positive, there will be attraction. Perfect. So two acetic acid molecules in benzene, they are going to associate and form one molecule. So what is happening to the overall molecular weight? Due to dimer formation, molecular weight is increasing. So molecular weight of your acetic acid is double than the molecular weight of is double its molecular formula in benzene. The reason is due to the dimer formation due to hydrogen bonding, like you saw over here. Perfect. The molecular weight of acetic acid is double as that of its formula. Perfect. As that of its formula. CH3COH. This is its formula. Perfect. Right? This is its formula. But when you put the CH3COH in benzene, it forms a dimer. So molecular weight is double than expected, basically. Due to dimer formation. And dimer formation is happening due to hydrogen bonds. Okay. Which of the following does not show intermolecular hydrogen bonding? Where do you think there is no intermolecular hydrogen bonding? See, between two water molecules, there will be intermolecular, right? HF intermolecular, CH3OH intermolecular, orthonitrophenol, guys. Orthonitrophenol. Is there intra or inter? Orthonitrophenol. This is your orthonitrophenol. Is there inter or intra? Intramolecular. There is intramolecular hydrogen bonding present. This is the answer of the question. Arrange in the order of the boiling point. Arrange in the order of the boiling point. Normally, what should I have? Arrange in the order of the boiling point. Quickly. You should be in a position to answer this question. Everybody. Everybody quickly. HF, HCl. Let's call this as 1. Let's call this as 2. Let's call this as 3. Let's call this as 4. Arrange the following in the order of the boiling point. So 1 will be having maximum boiling point. That is something which is understood because of hydrogen bonding, because of intermolecular hydrogen bonding. Okay. Then comes your, which one? Which comes the next? I'm looking at your chats. Which comes the next? Which comes the next? Quickly. Quickly, guys, in the chats. Which one comes the next? I would want the answer in the chats. Quick. I would want the answer in the chats. Everybody. Quick. I would want the answer in the chats. Which one? Absolutely. It's going to be the fourth one, then third, then second. Now, what do you think over here? Boiling point. Tell me the boiling point order here. 1, 2, or 3. 1, 2, or 3. Normally, I believe you will say 2 will have maximum, then 1, then 3. But if this is your order, you're gone. This is not the order. This is not the order. No doubt, no doubt, no doubt. Among H2O and HF, strong hydrogen bonding is present in HF. In HF, there is strong hydrogen bonding present. So due to the strong hydrogen bonding in HF, it should have more boiling point. But, if I talk about extent of hydrogen bonding, extent of H bonding, particularly intermolecular, right? Extent of intermolecular hydrogen bonding is more in water. Is more in water. What is meant by that? See, guys, what is meant by that? See what is meant by that. In case of HF, HF can form 2 hydrogen bonds at the same time. But look at this water molecule. It can form 4 hydrogen bonds at the same time. 2, 3, 4. One water molecule can form 4 hydrogen bonds at the same time. One HF molecule can form 2 hydrogen bonds at the same time. So extent of hydrogen bonding is more in case of H2O. Extent. Wherever extent of hydrogen bonding is more, I would say boiling point there is more. So 1 will be having more boiling point, followed by 2, and at the end followed by 3. So this is the order. Okay. If I talk about extent means number of hydrogen bonds basically. In water will be more. So 1, 2, 3 is going to be the order of this one. Remember this. Okay. Tell me the answer of this particular question first. Heat of vaporization of water. Heat of vaporization of water is more than that of HF. However, hydrogen bond is stronger in HF than water. What is the logic? You should tell me the logic here. You should tell me the logic here. Guys, you should tell me the logic of this particular equation. Heat of vaporization of water is more. Why? Heat of vaporization of water is more because extent of hydrogen bonding. Because extent of hydrogen bonding in water is more. Extent of hydrogen bonding in water is more. Right? When you want to vaporize water, you have to break 4 hydrogen bonds. In order to vaporize HF, you have to break only 2 hydrogen bonds. Now think, where will be the heat of evaporation more? In water for sure. Okay? Malic acid is stronger acid than fumaric acid. Why? Why is malic acid stronger acid? Why is malic acid stronger acid? This is something which you should have studied in organic as well. Why malic acid is stronger acid? Because the conjugate base which we get here in case of malic acid, that is stabilized. That is stabilized by intramolecular hydrogen bond. And whenever the conjugate base is stabilized by intramolecular hydrogen bonding, that conjugate base is more stable. And wherever the stability of conjugate base is more, right, the corresponding acid is going to be stronger acid. Perfect? Right? So malic acid is stronger, reason being because the conjugate base which you get here, in case of malic acid, after the loss of H positive, right, that is hydrogen bonding stabilized. That is stabilized by hydrogen bonding. Which hydrogen bonding? Intramolecular hydrogen bonding. Perfect? Am I clear with this? Perfect, people? So, with this, our chemical bonding is done and dusted, guys. With this, our chemical bonding chapter is done and dusted. So, guys, one thing I would want from all of you. Just revise it completely. Revise it again. Because if you do not revise it, you'll forget this. You'll forget this chapter if you are not going to revise this. So with this, our day 10 is done and dusted. Now, what do I want in the comment section of this particular video? Hashtag chemical bonding done and dusted like never before. Why like never before? Because some of the topics which I had not taught earlier in the previous chemical bonding, those are also done here in this particular chapter now. This is something which I want in the comment section of this particular video, right? Perfect. So guys, I think this much is enough. By the way, our next chapter is going to be redox reaction.